Hi everyone, this is Dirk Groen speaking. Good morning and welcome to the Multiscale Modeling, Uncertainty Quantification and the Reliability of Computer Simulations workshop, which of course is a digital merger of the Multiscale Modeling and Simulation workshop, the Unequivocal workshop, as well as the SIAM UQ workshop. I just wanted to make sure, can everybody hear me properly?
I can hear you, Derek, loud and clear.
Okay, very good. So first of all, I want to welcome all the speakers and everybody who's participating. It looks like we have about 52 participants in the meeting today, and the total number of registrations has been beyond impressive. The last number I heard about was 240 registrations in total, but Hugh, do you know the final number basically?
Let me have a look. It is 242. Lovely.
Okay, 242 registrations. Just to give you as a bit of a comparison, so the Unequivocal workshop was of course intended to be run in person at the International Conference on Computational Science. That would have been the first edition. And for the SIAM workshop on Uncertainty Quantification, it would also have been the first edition. The Multiscale Modeling and Simulation workshop has been running for quite a few editions, I believe about 16 or 17. And normally in that workshop, when we would hold it in person, we would get, say, about 20 to 30 attendees. So the fact that we have such a huge number of registrations is, I think, very nice, and also shows that there's a lot of interest in this digital format. So I find it very encouraging. In terms of the subject matter, of course, we're going to focus on two adjacent and very important topics. The first one is multiscale modeling, focusing on modeling and simulation approaches that basically encompass different time and space scales. So we'll hear especially on the first day a lot of talks about coupling, about simulations across different levels, but also mathematical methods to basically model phenomena across multiple scales. Very adjacent to this is uncertainty quantification, taking into account uncertainty from data, uncertainty in parameters that are being put in the simulation, but also how uncertainty propagates between the micro scale, the macro scale, or different time scales, for instance. The two are very heavily intertwined because the propagation of uncertainty and error can sometimes also be a very important consideration for or against adopting a certain multiscale approach. And as a whole, of course, the workshop focuses on the reliability and the trustworthiness and the reproducibility of computer simulations. It's one thing to make a simulation, but I think, as we have especially noticed in this era of COVID-19, academic simulations can sometimes be placed in a context where very important decisions are being made. And it's very important that the results we produce with these simulations have their uncertainties quantified, but also that the results are robust and that they are indeed fit for purpose to take these kind of actions and make important decisions. We have 2 days in the workshop in total, and on the first day we will have 4 sessions, with a total of, I believe, 19 speakers. And then on the second day we have another 3 sessions. So today the planned finish is basically at 6:40 Central European time, which is 5:40 UK time. And hopefully you can map it to your local time zones for those who reside in Asia, Australia, Africa, South America, or North America. I'm working on the assumption there's nobody from Antarctica, but please correct me if I'm wrong. And every talk basically consists of a 20-minute time slot. And the format is as follows. In most cases, Hugh will basically play the talk, which has in most cases been pre-recorded as a video. And during the talk, you will have the opportunity to ask questions by basically opening the Q&A and putting questions in. The chair of the meeting, and I will be the chair in the first session, will then be able to see these questions. And we will also promote the speaker after the talk is finished to panel member status, as it's called. So the speaker is also able to answer some of the questions in text. I, as a chair, can then choose to take certain questions and actually ask them by voice so that everybody can hear about the question, and then the speaker gets the opportunity to answer the question. The idea of the videos is that they have a maximum length of 15 minutes. And after that 15 minutes, we have up to 5 minutes to go through these question and answer sessions. Of course, whether we can address all the questions depends a little bit on how many questions will arise. But yeah, I think the chairs, we as chairs will do our best to address as many questions as we can in a good quality fashion. Okay.
Sorry, Derek, can I just
yes.
make clear that everyone has access to both the chat and the Q&A. Now, please be clear, don't use the chat to ask questions of the speakers. We want specifically you to pose these questions in the Q&A. Feel free to use the chat, but for the questions for the speakers, hit that Q&A button.
So yeah, I'm starting the video as well just to make it a bit more personal. So yes, exactly. So if you have questions, please post them in the Q&A. Aside from that, we will share quite tightly because it's a quite tight packed schedule. We do not want to overrun for people who have young children like myself. So keep in mind that the time constraints are quite hard, and there are a few talks that will be given live. So then people will basically connect and present the slides one after another. Let's see. So I see one question from Heinz Wilkening before we proceed with the normal talks. Is there an intention to make the presentation available on YouTube afterwards? Yes, that is the intention, but there are a small number of speakers that have basically mentioned that they prefer not to have the talk on YouTube. So we're always happy to incorporate that preference, of course, and in that case, we would not put the video on YouTube. All the other videos will be made available, and that's actually one of our considerations why we have this setup of pre-recorded videos. Before we start, the very last thing I would like to say is that this is, of course, the very first edition of this workshop. So I hope, of course, that everything goes smoothly, but please do bear with us if we happen to have any technical issues or logistical issues. We have practiced and rehearsed this extensively, so I don't foresee such issues. But if they do arise, then I basically kindly ask you for your patience. Okay, with that being said, we're slightly late, but we'll just offset the schedule by 4 minutes. But with that being said, I would like to present the first speaker, Julian Koelemeijer. And he's from the University of Leuven, or Louvain, depending on your language preference. And he's going to talk about projective integration for moment models of the BGK equation. Julian, can you hear me?
Yes, I can hear you.
Okay, so feel free to get started. I guess your video is about to start.
Yeah, it's pre-recorded, so please start. Hello and welcome to my presentation. It's my pleasure to start with this session and present my work on projective integration for moment models. In this talk, I want to show that moment models are multiscale models for the approximation of the BGK or Boltzmann equation. And I want to use projective integration to overcome the multiscale challenge of these models and achieve speed up in simulations. So let's look at some background. So the moment models are traditionally derived to solve flow problems in rarefied gases. Rarefied gases are characterized by means of large Knudsen number. The Knudsen number is defined as a dimensionless flow parameter, which is the ratio between the mean path length, so distance that particles travel until they collide, and a reference length. And in ambient conditions, for example, in our home office at the moment, the Knudsen number is typically very small because there are a lot of particles, so the mean free path length is very small. We are on this scale here, we are on the very left, where we could just use the Euler equations to simulate the flow of air around us. However, if we are allowed to go outside again and we travel very high in the atmosphere, and or we look at small reference scales, then we are in this transition regimes for which moment models are developed. Non-equilibrium effects take place and Euler equations are no longer sufficient to simulate the flow. My goal in this talk is to look at numerical simulations of moment models in the hydrodynamic limit, which means that the Knudsen number is taken in the limit to 0. And let's look first at how these moment models look like. Moment models can be written in this hyperbolic balance law form, where we have a temporal change that balances the transport term and a collision term on the right-hand side. And the variables that are in this system of equations are including density, velocity, and temperature. These are the standard hydrodynamic variables, and then some non-equilibrium variables, F3 and so on, depending on how many variables or how many equations we want to use, depending on the accuracy that we want to have. On the right-hand side, the collision term depends on the collision frequency. It's technically the model of collisions we are looking at, and also it scales with the dimensionless Knudsen number. So the smaller the Knudsen number, the more collisions, and the larger this term on the right-hand side becomes, potentially stiff. One example for this is if we use m equals 4, so we have 5 equations, then we get the system matrix for the transport term, system matrix A here. And the first 3 equations, for those of you who are familiar with the Euler equations, it's exactly that. Euler equations and primitive variables, conservation of density, momentum, and energy. And on the right-hand side, the collision term consequently has 0 entries in the first 3 rows. However, we have this term here, which is kind of a heat flux, and this couples to the higher order equations, which are used to close the system. And these higher order equations on the right-hand side have this term, which is a relaxation with this coefficient here in front. So now we want to look a little bit more at what the properties of this system are. More precisely the spectral properties. So this is our system, and we can already see by looking at the system that it has a multiscale structure. Because on the one hand, we have a transport scale from this hyperbolic left-hand side here. These are, it's a hyperbolic matrix. We have real eigenvalues. It describes the transport of information, a propagation with the speed of the eigenvalues of this matrix. And on the right-hand side, we have this collision operator. And this scales with the relaxation time or with the Knudsen number tau. So when the Knudsen number is small, it becomes very large. And then in the limit of tau going to 0, we have a scale separation. So we have a very fast scale of collision variables. And on the other hand, we have a slow hydrodynamic scale. And this is the scale structure that we have. To quantify this a little bit better, we first look at the semi-discrete system. So we discretize the transport term, put it on the right-hand side, and then this equation has to integrate it in time. Has to be integrated in time. So we look at the properties of this right-hand side. We compute the eigenvalues of this right-hand side terms, and we do this for different values of the collision frequency here. So different collision models and different Knudsen numbers. First of all, we look at constant collision frequency. It means that we always have a similar probability of particles colliding. And in that case, for a large Knudsen number, tau equal 1, this is definitely in the transition regime, not in the regime, all the eigenvalues are in one cluster here. However, if the Knudsen number becomes smaller, then the eigenvalues go further to the left. The real part of the eigenvalues goes further to the left. And especially for the variables that are associated with the relaxation here. The other variables here, the other eigenvalues stay in this cluster. Now we have, for the first time, we have 2 different clusters. And if the Knudsen number decreases further, we have an even clearer separation of these 2 scales. It's clear that we need to do something for these values here because they're so fast. We would need to have a very small time discretization, very fine with very small time steps to integrate these variables, and this would just lead to too much effort. We would never finish our simulation. In the next step, we look at the different collision frequency. Here, the collision frequency is space dependent, and it's exactly the density. Density, of course, depends on where we are. And this is a physical model because in this case, we say when we have higher density, so more particles, we have a higher probability of collisions happening. So it's what we would expect. And we take the same model and look at the eigenvalues, and the eigenvalues now extend over a larger range here. More specifically, the fast modes extend over this range because the density, of course, depends on the maximum minimum values here. Here we use a test case with density ranging from 1 to 7, tailored to the test case that I will show on the next slide. And we have the hydrodynamic, the slow modes here, the fast modes extend over this range. The Knudsen number decreases further. We can scale the axis appropriately, and it's a similar picture. We can have a separation of two scales with a very dense spectrum that we see here. What do we do now to make sure that all these eigenvalues are integrated in a stable way by a numerical method, even though they are so different? I want to show here an example of the application of projective integration. Projective integration is an explicit asymptotic driven time integration method. It's very simple to explain. It's based on two phases. In the first phase, we do a number of small time steps. This number of small time steps serves to damp the fast modes that are in the solution. And they are usually done with a very small time step size, small delta t. And the last two time steps are then taken to compute the derivative here. So basically the slope of this line. And then we extrapolate the solution in time. This is the second phase. We extrapolate over the remainder of a large time step size, large delta t. Of course, this introduces some errors, so we need to do some more inner time steps again, and then another extrapolation, and so on. So this is how we go from one time step to the next. This is just the basic version of projective integration. There are other versions of it, for example, projective Runge-Kutta method. Runge-Kutta method means that the outer stages, so this extrapolation stage, is based on a Runge-Kutta scheme, where each stage of the Runge-Kutta scheme is again one inner integration. It can be even further generalized to telescopic projective forward Euler method, where this is like a nested approach. The lower order or the lower level projective integration is just one step of the next higher level, and this is then one step of that is one step of the next higher level. So it's like nested into each other. The question is now, how do we choose the parameters? So the large delta t, the small delta t, and the k, which is the number of inner time steps. And the idea is to exactly match the stability domain of the scheme with the spectrum of the model. I showed the spectrum of the model before. Now we look at the stability domain of a standard projective forward Euler method, which we see here. So we have one stable integration of slow modes. This is because it's extrapolation step. And we have a stable integration of this fast modes. This is because of these inner integrations. And by choosing the values of the small time step size and the large time step size appropriately, we can now shift these clusters around as we like it, or increase the size, depending on what we need for the spectrum of the model. And there's a clear theory around this, and I don't want to go too much into detail here. I just want to show the applications. So first of all, we have a shock tube problem, 1D, very standard gas dynamics test case. I here choose constant collision frequency nu equal 1, and use collision different Knudsen numbers. We start with 10 to the minus 2, then 3, 4, 5. For 10 to the minus 2 and 10 to the minus 3, we could still use the standard time integration method, which in this case we use a Runge-Kutta method. It's a third order method for high spatial accuracy. But however, if we decrease the Knudsen number further, then this method is no longer stable. So we need to use projective integration method or decrease the time step very significantly. We don't want to do that, so by using the projective integration method, we can achieve a large speed up that I will show in the end. So looking at the solution, we see from blue to red to green to gray that we clearly converge to a solution that is, in this case, exactly the solution of the Euler equations. The Euler equations have this typical three-wave structure with rarefaction wave, contact discontinuity, and shock wave in the front. And the rest is just deviation for this non-equilibrium that we find in the transition regime. Another test case I want to show is a two-dimensional test case. It's a 2D forward-facing step test. We have a supersonic flow that comes from the left-hand side with Mach number 3, and then it hits this step here. There's a bow shock forming, and we have a reflection pattern. However, in the fight case, the shocks are typically much smoother, more smoothed out, because they are less particles. In this test case, I also used a more physical model for the collision frequency, though, so space-dependent collision frequency nu equals rho, which requires to use more advanced projective integration method. In the test case with the large relaxation time or Knudsen number 10 to the minus 1, we can still simulate with forward Euler method. However, if we decrease the Knudsen number by 1, 2, or 3 orders of magnitude, we need projective integration, or even more than telescopic projective integration, because of this extended spectrum that I showed a few slides earlier. We can see from the point of view of the model, the shock wave here becomes much stronger and stronger until we arrive at a solution that is the Euler solution. And these are our steady states, and we have this bow shock with reflection and this characteristic stationary pattern. The question is, what is the speed up in these simulations? Of course, in this test case, we would need a forward Euler method with a much finer spatial discretization grid. So we would assume that we have a speed up. You can see this in this table here. The speed up of the projective integration scheme in comparison to the standard forward Euler scheme is indeed significant. For the forward-facing step test, we use the telescopic projective integration, and we already have a speed up of factor 40. And depending on the test case, that varies, of course, also depending on the spatial discretization, high order, and so on. And here we have that in the shock tube test case with constant collision frequency, we even have a speed up of up to 200, because the standard forward Euler scheme would need a very small time step size. So we see indeed this significant speed up. And this brings me already to the conclusion of my talk. A short summary. So I introduced briefly the moment equations, moment models that have this multiscale spectrum that I showed. And I presented projective integration as one successful method to achieve a large speed up, because it tackles this fast and slow modes in this particular way. Details can be found in our paper, Projective Integration Schemes for Hyperbolic Moment Equations, but we also analyzed a lot of different test cases and collision frequencies and showed how to choose these parameters precisely. Further work now focuses on an extension to space and time additivity. The goal is here to see that we can make the parameters of the projective integration change in time and space, so that depending on the flow field, we can then use more or less inner integrations or larger time steps to accelerate the simulation even more. And with this, I want to end my talk, and thank you for your attention.
All right, thank you very much for your pre-recorded talk, Julian. I will give all the participants a little bit of time to type their questions in the Q&A. Just to be clear, the way to do that is basically if you move your mouse, you'll see a range of buttons at the bottom of the Zoom screen. And then in the bottom, next to the chat, you see an icon called Q&A. You can click on that, and then you can use that to ask questions to Julian. So we'll give everyone a few seconds to basically write a couple of questions. Julian, perhaps to start off, I have a small question of my own. So I believe that most of the examples that you have shown are basically two-dimensional, and you already get a good speed up in that regime. Do you have any idea to what extent you would achieve a speed up when you do models in 3 dimensions?
Yes, thanks for the question. The test cases I showed are indeed 1D or 2D examples. In 3D, the speed up would essentially be the same, because the acceleration that I'm talking about is mostly based on the integration in time, because the spatial discretization we assume is done already before. And then it just depends on the integration in time that we are doing. So I think the speed would be comparable in 3D.
Okay, yeah, thanks a lot for your answer. So, okay, so that it wouldn't explode in magnitude, but you expect it to be more or less comparable. I'm still awaiting a few questions from the audience. Is there anyone who has questions? I don't see anything popping up in the window at the moment.
Yeah, maybe I can comment a bit more on the speed up. You mentioned it. I showed the speed up is depending on the method and depending on the test case that we're using. The speed up that I showed up to 200, this is in principle the theoretical speed up. So that means the speed up that we achieve in comparison to a very standard implementation. and that might depend also on how this method is implemented. However, that means also if we have a clever way of implementing the method, we could even achieve a larger speedup. So the speedup is not limited to a factor of 200. It can be an even higher speedup for Knud's numbers that are closer to the equilibrium region.
Okay. At this point, there's actually one question from Ben Hurahin, who asked, Julian, your method is reminiscent of predictor corrector algorithms. Could you perhaps say something about the differences between the two approaches?
Yeah, in principle, the method is using a prediction of the slope of the rate of change that is happening, but the we choose the parameters is tailored to this way the projective integration works. So there's a lot of theory for this specific methods on how many initial steps you need to do and what the size of this initial step needs to be in order to achieve stability. So I think it is similar, and the method is tailored such that we achieve the stability.
All right. I have one last very quick question for you, and then I think we'll have to move on to the next speaker, which is from John McCullough from UCL. Do you think this approach would have applicability for higher Knudsen problems too, for example, Euler or Navier-Stokes?
Yes, very good question. So in this talk, I consider basically the coupling of moment models for the low Knud number case. But the overarching goal is to achieve have a method that also applicable for large Knudsen numbers. And in that region, it's not about the time discretization, it's more about the computational model, which means that we need a moment model with more equations. So I showed examples with 4 equations, but we can also increase the moments to larger number, and then the equations are just more. We have more physics in the model, and then we can achieve flows with higher Knudsen number. Very good question.
All right. Thanks a lot for your presentation, Julian. Thanks a lot for the very clear answers that you've provided. We move on to the next talk, which is by Emil Löfbach. It's about bridging timescales in diffusive kinetic equations for multi-level Monte Carlo. Emil is active in the Department of Computer Science and also in the numerical analysis and applied mathematics section of the Catholic University Leuven. So are you in the call, Emil?
Yes, I'm here.
Okay, excellent. So there's one small thing that I would like to note. So unfortunately, my dean has scheduled a talk with me in exactly 20 minutes about my promotion. So I've asked Diana to basically chair the very last bit of the session. So Emil, it may be that Diana will do the Q&A after your talk, just to be clear.
Okay, that's fine.
Okay, with that being said, let's start the talk. And yeah, let's learn more.
Good morning, everyone. So today I'm going to present you some work that we've done in recent years at KU Leuven, and it's all about bridging timescales and highly collisional kinetic equations using multi-level Monte Carlo and particle-based simulation. So the setting of this work is in the simulation of tokamak fusion reactors. So we have these toroidal reactors with a plasma moving around inside them, and inside this plasma you have fusion. And neutral particles are then used to control this plasma. We want to simulate these neutral particles. This is a difficult problem because on the one hand, the models are highly collisional, so we have lots of collisions with the background plasma. Meaning we have to take very small time steps, but we are interested in things that evolve at much slower time horizons. For example, the density of particles or the energy distribution. So we have to take very, very many time steps to compute what we want. On the other hand, we have high dimensionality. This comes from the fact that we have both position and velocity in the models, which means that we have twice as many dimensions as the use case. So for example, a 3D realistic simulation, once you add time dependency, gives you 7 dimensions in the model. Hence we use Monte Carlo simulation. And then mathematically speaking, we can say that these particles, so their distribution F is described by a kinetic equation. Now the simple kinetic equation is here on the slide. So what's going on here? Well, the distribution of particles changes in time. We have some transport, so that means that particles move according to their velocity v. And then we have on the right hand side a collision operator. So this collision operator is going to do the following. It's going to move particles based on the number of particles that are at a given position and a given velocity v, and then it's going to reintroduce that same number of particles at the same position it had before, but using a velocity distribution m, and this is the steady state velocity distribution, and then here we have rho being the particle density. Now I already mentioned that we have vastly different timescales, and we want to quantify this in some way. So what we're going to do is introduce a timescale parameter epsilon, and when epsilon goes to 0, then the timescale separation is also going to go to infinity. So that's what we do here. And what do we do? On the one hand, we divide the right hand side by epsilon. This means that we drive the collision rate up to infinity. On the other hand, we multiply the time derivative with epsilon, meaning that we look at longer time horizons. And why do we do that? Well, you can picture a particle that just keeps changing direction, it keeps undergoing collisions. It's going to take a very long time before it actually goes anywhere, and we see long-term behavior. Hence, we look at longer time scales so we can still see net drift effects, for example. Okay, so the next thing I'm going to do is divide out epsilon in the whole equation. This gives us this, which is a diffusively scaled kinetic equation, and is going to be what we are going to use throughout the rest of this talk. At the particle level, particles follow a velocity jump process. So what does that mean? Well, they move in a straight line given their velocity for an exponentially distributed amount of time. The expected time between collisions is epsilon squared, the same epsilon squared that we find here. And then at the end of this time interval, what we're going to do is just resample the velocity v from the distribution m, the same m that we have here, and then the particle just travels in a straight line again. So it's a very simple model. Now, in both of these cases, we have nice mathematical behavior if we look at the infinite timescale separation limit, or epsilon going to 0. In terms of the kinetic equation, we can show that in terms of the density, we get convergence to the heat equation. And at the particle level, we can show that particles follow a Brownian motion. So that means that if we have a fixed time step and we update the position like this, then we draw a normally distributed number and multiply it by a diffusion coefficient and then the time step in the square root. So if we want to simulate something like this with particle-based schemes, one way to go about it would be to do operator splitting. So we take a fixed time step, delta t, and first we look at the transport effects. So we assume velocity remains fixed in this time step, and then we just do a forward step with the fixed velocity. At the end of this step, we can then decide, was there a collision or was there not a collision during this time interval? We do this based on the probability of a collision occurring, which we can compute analytically. And if we decide there was a collision, then we resample the velocity from m. Otherwise, we just keep it as it was before, going into the next time step. Now, this is a very simple scheme, but it's not quite going to cut it in our setting. And why is that? Well, we see here, right here, that there is a 1 over epsilon term in the transport step. What's going to happen is as epsilon goes to 0, this whole thing is going to blow up, unless we take very small time steps here to compensate. And that's going to be how this multiscale behavior pops up in these schemes. So the rest of this talk is then going to be about how we can devise a new scheme to avoid this issue. To do this, we're going to make use of a framework called asymptotic preserving particle schemes. So I'm going to say something about that. What these schemes are going to do is allow us to take large time steps in a stable way, but this is going to come at the cost of introducing a bias in the results we compute. Then we're going to use multi-level Monte Carlo to estimate this bias and try to get rid of it. To do this, we're going to need to be able to generate correlated particle paths, so I'll say something about how we do that in practice. And finally, I'll present you some very preliminary results with our newest scheme. So first off, the asymptotic preserving particle schemes. The basic idea is the following. So instead of simulating our original kinetic equation, which I showed on the previous slide, we're going to simulate a modified equation which comes out of a framework proposed in this paper here. And what's this equation going to do? Well, you can look at it as a kind of weighted sum between the macroscopic heat equation, the limiting heat equation, and this kinetic equation here. So what we see is that the simulation time step now explicitly appears in the coefficients. If the time step is large, then this term will disappear, and this term will also disappear, and we're left with this fraction going to 1, i.e. this results in the heat equation. If the time step is small, on the other hand, then this term disappears. This becomes V over epsilon, as we have above, and this becomes 1 over epsilon squared, as we have above here. So we get convergence to the original kinetic equation. This means that if we take large time steps, we can simulate a model which is simulatable in a stable way with large time steps. But as we take smaller and smaller time steps, we gradually get the behavior that we actually want to simulate for a given value of epsilon. So we gradually transition to the right regime. With this model, we can simulate pretty much as before. So what we do is we do a forward time step. We have a velocity, and note now that this term, where the 1 over epsilon was before, now has a fraction which remains finite for all values of epsilon. And at the same time, we're going to also have to do some Brownian motion because of this extra term that's popped up here. And then at the end of this time interval, delta t, we then again compute the probability of a collision and decide whether or not to resample the velocity. So this occurs just as before, just with some different constants. And the key thing here is then, like I said, that this fraction remains finite. Okay, so this scheme can take large time steps, but it simulates the wrong model when we do this. To use this, to correct this, we're going to use multi-level Monte Carlo. So first off, Monte Carlo in general, I'm just going to say something about that. So let's say we have some quantity of interest y at time t star. This will be an expected value of some function of the particle position at that same time t star. And how can we estimate that with Monte Carlo? Well, we just take p particles, we simulate them until time t star using a fixed time stepping method. We apply the function to each position one by one, and we average over the results. Now, this is going to produce errors, of course, because on the one hand, we're using a fixed time stepping method, so we have a bias in what we compute. The smaller the time step is, the more accurate the results of each trajectory will be, but the more expensive each simulation will be. On the other hand, there's some statistical noise, and this comes from the fact that we have a finite number of samples p, and the more samples we take, the more trajectories we simulate, the smaller this noise will be. And then in typical applications, you then say you have to make a choice because you have a fixed computational budget, and you have to then choose, do we do many cheap simulations with large time steps, resulting in a large bias but low noise on the result, or do we allow there to be more noise, but then use smaller time steps but we can't take as many samples? And the idea behind multi-level Monte Carlo is that you don't have to make this choice explicitly. So what you do instead is we define a hierarchy of time steps. We start out with a very coarse simulation with delta t0, and because this simulation is so coarse, we can do very, very many samples, p0, and compute with very high certainty a result which is going to have a large bias. But the bias will be predictable. Now we just have to find a way to estimate this bias, and we're going to do this by computing with this same coarse time step some results, and then we're going to at the same time try to simulate the exact same path with a finer time step. And if we can simulate the same path somehow with two different time steps and compare the results, then we get an indication of what the effect of this time step is. And then assuming that the fine time step is much more accurate than the coarse time step, the difference of the two will give an estimate of the bias in the coarse simulation. So if we do this many times, we get a bias estimator. And if we do many of these bias estimators, refining and using finer time steps, then we get a sequence of estimators which we can sum to get a multi-level Monte Carlo estimator, which should be able to compute the same thing as a single level Monte Carlo estimator at a much lower cost. So we need to generate correlated particle paths somehow, and the idea behind this is the following. So what we're going to do is span a time step delta t L minus 1, so it's a coarse time step in two different ways. On the one hand, we have a coarse simulation, this one here, taking a single time step. On the other hand, we have a fine simulation here and here, taking m fine time steps. And what we're going to then do is first perform the fine simulation. This gives us m sets of random numbers as we do our time steps. So that's these velocities on the one hand, and these xi's, these normally distributed increments, on the other. And then what we can do is find a way to combine these m sets of random numbers into one set of random numbers that we can plug into the coarse simulation, and that way the coarse simulation will follow a similar path to the fine simulation. Now, I mentioned before that in very fine simulations, this term here will become dominant, whereas the diffusion will not have such a large effect, and vice versa in very coarse simulations. Then diffusion will have the main effect, and there won't be so much going on here. So if we want this large effect from the velocities in the fine simulation to also have a large effect in the coarse simulation, then in addition to using these xi's from the fine simulation to generate a coarse xi, we also have to use these velocities in some way here. And then we're also going to use a little bit of information from velocities to generate some kind of coarse velocity. So that's exactly what we do. So we have a coarse xi we want to generate. That comes on the one hand from a term coming from fine diffusion, and one coming from the fine velocities. The exact way we do that is as here, with a couple of caveats I'm leaving off the slide. But the key thing is we take the sum and we do a variance rescaling. And this variance rescaling is important because if these things both have mean 0 and variance 1, and we combine them in such a way with a theta between 0 and 1, then this also has mean 0 and variance 1. So we have what we call weak Brownian motion, and that's because of the fact that these velocities may not necessarily be normally distributed. There's some technical caveats that come from that as well, but again, I'm going to skip that for now. Okay, in terms of the collisions, what we're going to do is basically look at each fine time step and see if there's at least one fine time step where there was a collision. And if that's the case, then there's also going to be a large probability of there being a collision in the coarse simulation. If both have a collision, then we're going to take the final velocity generated in the fine process and plug that into the coarse process in such a way that both simulations have then the same velocity going into the next time step. So now to wrap up, just one quick simulation result. What we have to do first is pick a sequence of time steps, delta t0 through delta tl, and a set of weights, theta 1 through theta l. And the goal is then going to be the bridge coarse time steps to time steps smaller than epsilon squared to resolve these fine features. On the one hand, in terms of the time steps, what we're going to do is start with something very coarse, then do a correlated simulation where we sample coarse things and fine things and compare them to each other to bridge our timescale separation. And if we need, then we can add extra levels based on the tolerances we've set on the simulation. In terms of the weights, what we're going to do is in fact not do this cross correlation at the fine levels. So the fine diffusion at the fine levels is going to influence the coarse diffusion, and there's going to be no influence from the fine velocities. But this is only going to happen in level 1. So there the fine velocities influence coarse diffusion. And that is for technical details, which I'm skipping here. And then the result itself. So what we're doing is doing some simulations with Gaussian velocities, estimating a quantity of interest, which I have here. And we list some results in a table. So on the one hand, we have the updates at each level. The sum of all these levels gives us our computed result. We have the variance of samples at each level. We have the number of samples we require at each level, and then the overall cost of the level. And if we look at level 1, a key thing we can see here is that the variance of samples is much smaller than the overall variance of the process. So that's what this is here. This translates into the fact that we only need 10 to the 6th samples instead of 10 to the 8th samples in this expensive regime, and fewer for the even finer levels. And this is going to result in an overall reduction in cost. So if we look at that explicitly, the multi-level simulation costs almost 10 to the 9th, while a single-level simulation would require the same number of samples we have at the coarse level at the finest discretization to get the same bias, and then the cost would end up being 10 to the 12th. So we have a speed up of a factor 1,000. Now obviously this is just one simulation result on a simple case, but it shows how much potential there is in these methods. And with that, I would like to end these references. So most of what I said is listed in these papers here, and there's going to be one more paper appearing on arXiv soon, and I welcome any questions you have.
Thank you, Emil, for your presentation. So now we can actually take questions. We already have a couple of questions here. So first question is from Anton Lebedev. Has this approach been considered in 2 3-dimensional special dimensions and in the grand scheme of plasma simulations with EM components? Specifically, is SD simulation practical in the given context of plasma simulation, given that there is generally also EM field component included and that the simulations are already very expensive?
Yeah, so thank you for the question. So what we're working on here is specifically looking at the simulation of the neutral particles, so not the plasma itself. The motivating work behind this is the simulation code Irene. So what's happening there is basically there's a coupled simulation going on. On the one hand, you have a PDE model working on the plasma simulation, and then this is coupled with the stochastic model for the neutral particles. So that's a code that's already been used for a while now, where they use Monte Carlo simulation, and our goal is to accelerate what's going on there. I know there are other approaches where people try to do everything at the PDE level, but yeah, this sort of consists of different approaches, and I'm, to be honest, not exactly an expert on the practical codes in the grand scheme of things. So we're specifically looking on request of the people developing this code on how to accelerate what they have at this moment in time. So I don't know if that clarifies the question.
There's also continuation of the another question from Anton. Is the collisions are assumed here the distributed according to a given distribution? Would it be possible to use, for example, practical in-cell simulations to derive empirical distributions for this process? And would it be usable here, or does the method require a uniform or normal distribution to work?
No, so the method does not require a normal distribution. The analysis that we've done so far has assumed symmetry, but we don't see a reason why this is necessary in practice. So this is the next stage, in fact, of this work, is to look at non-symmetrical cases and try to simulate a more practical example. So we already have some discussions going on how we can do that in practice, because obviously, yeah, at the moment we're looking at 1D simulations. We've done 2 speeds, that's plus minus 1 velocity, and we've done a normal distribution. But we're interested in plasma edge simulations, and there you typically have the case of indeed non-symmetry even. It's not just the fact that it's not normally distributed. So yeah, I mean, you can, and like I already said from the previous question, so typically we have inputs coming from a coupled simulation of a plasma, which gives us the parameters in this setting. And often, and in the actual practical simulations, we also have source terms and sinks, which I haven't gone into it all here. So yeah, there's a lot of extra stuff that we still need to do. We don't see any reason at this moment in time to think that we can't do it, but I can't say we have done it yet. So it's going to be a matter of waiting and seeing how we make progress.
Thank you. Thank you, Anton, for the questions, and Emil for the answers. I think this thorough and you can understand. So if you have any other questions, please put them on the Q&A section, and we can also answer them by typing. So I think next we can go to the next presenter, who is, please welcome Wouter Edeling, who will be demonstrating WECMA toolkit live today.
So hi, I guess I should share my screen now, right?
Yep.
Let me go ahead.
So Wouter is from SWI and working with the WECMA project.
So you can see my screen now?
Yes.
Okay, cool. So hi, I'll be demonstrating the WECMA toolkit, or at least the easy VVUQ part of it. And this is a tool that is used for forward uncertainty propagation. So you have some model, it has some coefficients, they have a distribution on them, and you want to see what the effect of that distribution on the input has on the output of your model. So I will demo this live. I made this last night, but it's just my model, my quote-unquote model is just a simple polynomial function, right? Because I can run that quickly. You can see it over here. It's nothing special. The only thing I want to make clear is that I have this coefficient here that multiplies my input variables. And so I make this large for the first variable and make it a bit smaller for the second, etc., etc. So this means that I'm hard coding into the problem that the first variable is the most important, then the second one, then the third one, etc. And this will come back later. But overall, so now I have this model, it has a bunch of inputs, and I want to see what the effect of the uncertainty has on the output. And so to do that, I can make what's called an easy VVUQ campaign. So let's make it a bit bigger so you can perhaps see it better. And so the campaign is like the overarching object in this simulation. Everything will be connected here. And so the first step is to actually define the parameter space. So in this case, my model has 20 parameters. I won't make all of them uncertain, but they have 20 parameters. All of them are floating points, and all of them have a default value of 1/2. And I define a bunch of other things as well. For instance, the name of my output file. Right, my polynomial model will write the result on output, and EasyVQ will read that in. And I can select what column of that output file I want to select. And so then the next step is to actually create what we call encoder, decoder, and collation element. And this basically deals with the input and the output files. So the encoder will read an input template. And in the case of my polynomial model, I'm basically just reading a dictionary, right? It's very simple, but it can be anything else as well. And what EasyVVQ will do, it will just pick up on any value with a $sign, and then will insert a random value for this particular variable. Right, so I've created this template. My model will read it, and EasyVQ will seed the different values. So, the decoder just reads the output files, in this case a CSV file, and the collator will gather all the simulation results and put them into a single data frame. So then I have my parameters, I have my encoder, decoder, and collator. I add everything to the campaign in this step over here. And then the next step is to decide which one of my variables I'm going to make uncertain. And in this demo, I will make the first two uncertain. And I will select a uniform distribution for that. We're actually interfacing here with something called ChaosPy because we don't want to reinvent the wheel. So there's this library ChaosPy. There's a large number of different probability distributions that we can select from. But in this case, we just select a uniform distribution, which is uncertain between 0 and 1. Next step is making a sampler. And so in this case, in this demo, I will show you a couple of different stochastic collocation samplers. And if you're not familiar with stochastic collocation, you can just think of this as, let's say, something that creates a polynomial approximation of your code output. Right, so it will sample a bunch of inputs, and this will give you samples. And the stochastic collocation expansion is let's say, a polynomial approximation of your code output. The first thing I give it is my uncertain distributions, which is varied. These are the uniform distributions. The polynomial order that will, let's say, decide the order of my my stochastic collocation expansion, and will also determine how many points I have to sample. I can select a quadrature rule. In this case, C stands for Clenshaw-Curtis. That will decide where the distributions are sampled. I can also use Gaussian or something else. And these other variables I will get back later. But basically what I've done now is I have set my sampling plan. And so if I have specified the sample in this way, I have a certain sampling plan, and at those points I will have to evaluate my code. This step just draws all the samples that haven't been drawn before. In this case, it's all of them. And then it's time to actually execute the ensemble. Now, EasyVVQ itself doesn't handle job execution, but there are multiple tools in Vecma that do. In this particular case, I'm using FOPSIM 3. And so that's an automation toolkit for scientific computing that is geared towards HPC resources. It's mainly a command line tool, but we've also made a simple interface so you can run it inside a Python script. So that's just a one-liner over here. It will execute the ensemble that I made. In this case, it will run on localhost, but if I want to submit to an HPC supercomputer, I can just change the name over here. So we have access, for instance, to the Eagle machine in Poland. And if I change this to Eagle, it will just submit all the jobs to that machine. And the reverse is also a one-liner. So this will retrieve all the results from the remote machine. And then here I activate my collator. So that's where I take all the samples and I put them in the data frame. And then finally, when you have all your samples back, it's time to do some post-processing. And in this case, I'll just compute the output mean and the output variance. So that's like a prediction and an uncertainty in the prediction. I guess I can just execute now. Over here, you can see the output. So this is the FOPSIM runs that you see executed. Won't take too long. And so this is the sampling plan that I talked about. And over here, I'm not sure if you can see this very well, but I have an analytic mean because it's a polynomial function. I can just compute the exact result. And then the computed output from each VVQ is exactly the same. Again, this is just a polynomial test function, so this is not really a surprise, but you can see that you get information on both the prediction and also on the standard deviation. So that's the uncertainty. And now the nice part about things like stochastic collocation or polynomial chaos is that they can show much faster convergence than, let's say, standard Monte Carlo methods. And however, there's some caveats that you have to consider. So there's always some underlying assumption on the regularity of your code output. So if it's very stochastic, let's say, it's not a good idea to use these types of methods. But perhaps more importantly, there's something called the curse of dimensionality, which many of you will be familiar with. And so how these sampling plans are made, in this case, it's a two-dimensional one. So I selected a polynomial order of 2 in this case, which means I get for each input 3 points. And then the two-dimensional grid is just made by a tensor product. So 3 times 3 is 9 simulations. That's simple. But of course, the problem is if I have not 2, but I have 10 dimensions, I would get 3 to the power 10 sampling points. So the cost of this method, it will just explode if you go to the more parameters, more input parameters. So one way you can kind of, let's say, mitigate this a bit is by using something called sparse grids. And so this is still a tensor product construction, but instead of a single tensor product, it will make a linear combination of different tensor products. And it will start from a tensor product with a very low order, and then it will build it from the ground up. And in that case, you can get much more efficient sampling plans, especially in high dimensions. And so in EasyVVQ, you just set sparse to true. I'm also going to set growth to true. And this means that I will get a nested grid. And a nested grid is something which, for a given order, it will contain all points of the previous order as well. So there's a hierarchy of points. And if I set this to true, it just means that I start with a single point, and then I start adding more points on top of that. And so that's all you have to do. You just switch a couple of flags, and now you have a sparse grid campaign, which I can run again. It will take again a couple seconds to complete. And you can see now this is my sampling plan for the sparse grid. So you'll remember there were 9 points previously, and now there's 5. And so this is not a big deal, but in higher dimensions, you can really get a large reduction in the number of samples that you have to evaluate, right? Because many of these points will start to collapse. You will get a much more efficient sampling plan. And another nice thing about sparse grid is I mentioned this nested property. And that means that you can actually refine this grid without throwing away these 5 samples that you already computed. And so you can do that in EasyView as well, very simply. So I could just say over here, let's say I do 1 refinement. And then I enter this for loop. It's exactly the same as before. I'm going to draw the samples. I'm going to use FOBSIM to execute the ensemble, etc. The only new thing here is that I call this method, which just computes the next level in the sparse grid. And so it will refine the existing grid. You can run that as well. So this is again the first round, and then we'll go into a second round of refinements. In this case, there are 8 additional points. And yeah, there we go. So you can see that it has the original 5 points that you saw before, but it has added an additional 8 points. And you can keep doing this until you're happy with the result. However, one thing you can see is that these grids are symmetric, right? And I mentioned in the beginning that I made on purpose the first variable, so x1, more important than x2. But a standard sparse grid, it won't pick up on that, right? It will just give each the same consideration to every input variable, which means you get these isotropic looking sampling plans. And so it might be beneficial to actually pick up on sensitivity while you are doing the refinements. And you can do that by a so-called dimension adaptive method. It's also implemented in EasyView, although it's still in beta, but you can just flip another switch over here. So if you set adaptive to true, it will make a dimension adaptive grid. And so now if I do more refinements, you will see it will start to pick up on the fact that x1 is actually more important than x2. So I can run that as well. Again, this is the first campaign, and then in this case, there can be a number of refinements. It'll take a little bit longer to compute. But yeah, so here's the dimension adaptive sampling plan. And you can see that it starts to pick up on the fact that x1 is actually more sensitive to my output than x2. See, there's more points in this direction than there are in that direction. And especially if you have higher dimensional problems, this can be quite advantageous because let's say many physical problems will have perhaps a large number of inputs, but only a couple of them will really matter, right? So that's a low effective dimension. So if you can pick up on that while you do the sampling, it's possible you can do with much fewer samples than you would normally do. And this
Hi,
is...
Wouter, you have a couple of minutes left.
I have a couple of minutes. Okay, well, I don't have much left to say though. The only thing I would like to stress still is that stochastic collocation and polynomial chaos, it's of course, it's not new, but I think let's say the power of the Vecma toolkit is really the coupling with the HPC resources. Like I said, it's quite easy to run the exact same thing on a local host, to test it, for instance, in low resolution, and then I can just run the samples on a larger machine by just changing localhost to equal Vecma or to some other machine that's been pre-configured. And yeah, that's the nice part about this toolkit. And with that, I am actually at the end of my demonstration. So if there's any questions, I would like to answer them.
Thank you, Wouter. We actually have a couple of questions. So first of all, yeah, we did change the agenda. Unfortunately, one of our speakers were not available to present today due to personal circumstances, and we wanted to present our Vecma toolkit. So in relation to the Wouter's presentation demonstration, we have a couple of questions. So first question is from Alfonso Santiago. Can it be assigned to non-uniform, example, Gaussian variable distribution to the input variables? And how would that reduce the sampling?
It wouldn't reduce the sampling, but it might, so it will change the sampling points. So in general, these methods choose the sampling points based on some optimality condition, and that's related to the input of your variables. And so that it's all done under the hood by chaos pi, so the generation of the quality rules. But yes, you can change this to normal or to beta or whatever. It might not work well with this example, but you will start to see that you get different sampling plans in this case. And so the number of samples will probably be the same, but where they are located will be different because you're changing your inputs. So the optimal points will change compared to a uniform case.
Next question from Philipp Maybank. Have you considered using Monte Carlo and or quasi-Monte Carlo sampling to handle cases with a large number of input variables? And what would be costs, benefits compared to the sparse grid method? Can the sparse grid method account for the correlation structure interactions between input variables?
Yes, so this is, by the way, of the normal distribution. If you remember the previous picture, they were not exactly in the same location, but for the second question, well, Monte Carlo is implemented. And so Monte Carlo is better if you use a very high amount of samples. Right? So like I said, there's this cursive dimensionality that you can that is very much present in the standards stochastic allocation. So if you're going to do a problem with 20 dimensions, you shouldn't use the standard stochastic allocation. You're better off using Monte Carlo. The isotropic sparse grid I showed you as a second example, it just postpones the cursive dimensionality. So at some point, you're still better off with Monte Carlo. But the dimension adaptive, it might be better. Because if you have 20 dimensions and only 2 really matter, it can pick up on that. And so you're effectively sampling a 2-dimensional space almost. And the last one, it can pick up on interactions because the way it doesn't refine each input one at a time, it can also refine multiple inputs at once. And so in that way, you can kind of capture correlation effects between parameters.
And we have the last 2 questions. Can we include any program as model whose influence we want to study, or are we limited to function defined in Python?
No, you just have to have an input file. So I used it in R and I've used it with C code as well. But let's say this is the input file of some function in R. It will still work. You just need to have some template with easy you can read, and where it can replace these $ variables. Right? If you have that, you can use it.
And I think we can have the last question. Wouter, would you share your code?
Yes, yeah, I have to make some tutorials anyway. So yeah, I can share this code. I can just upload it to GitHub, and you can find it there. I'll type the link in the chat once I've done so.
Diana, can you hear me?
Yes.
Can I just make a quick statement?
Sure.
Just to remind everyone who's able to listen online, and tomorrow, I think it's at 10:30 European time and 9:30 our time, we do have a presentation and talk about the new release of the Vector Toolkit, in which EasyVVUQ is featured. And I think these capabilities are also in there, Wouter. So that will be discussed tomorrow, and the links and everything will become available at that time. It's all open source.
Thank you, Peter, for that note. We'll have set of presentation, as Peter mentioned, and also the release tomorrow. So I think we can conclude the first session for today, for the morning, and we'll have coffee break now till 10:50 UK time, 11:50 Central European time, and we should be commencing then.
Well, greetings to all the participants in this virtual meeting. I'm chairing the second session. My name is David Costa, and it is my honor to do this. I would therefore call upon the first speaker, Javier, who is going to talk about running coupled simulations on HPC and cloud resources with enhanced TOSCA workflows. Please go ahead.
Can you see my screen?
We can see your screen.
Okay, so well, I'm Francisco Javier Nieto. I'm from Atos, and I'm the coordinator of the Hidalgo project. Already some people from this project has been presenting things, so you pretty much know the kind of things that we do. And what I wanted to show you is the I wanted to talk about how we orchestrate the applications, that the simulations that we have in the project, and how we could use the orchestrator we have in order to manage the coupled simulations. Okay, so all in all, this is a presentation which has to do more with how to manage the resources when you are going to run these kind of simulations. So basically, the key element here is what we call Croupier. Croupier is an orchestrator based on Cloudify, which basically provides the capability to run jobs in HPC. Cloudify is an orchestrator for cloud environments only. It has a lot of connectors, and it's very nice for that, but it does not have the capability to connect to HPC systems. And therefore, what we did is develop this kind of extension. So now we are able to send jobs to systems which are managed by workload managers like Slurm and Torque. Okay, and we also are including capabilities to use HPDA systems based on Apache Mesos. Another thing that we have been including with the time is some support for the data movement. So for example, we have included some functionality that allows you to easily move data with grid FTP. Also to publish data sets in SICAN. SICAN is a data catalog, so you generate some result with your simulation, and then you just tell the orchestrator to publish your work in this data catalog, and the data will be published there. Okay. And one of the good things that this orchestrator has is that it allows us to combine HPC and cloud resources for running these simulations. Okay. The good thing is that sometimes you can decide to optimize in the time that you're going to use, or the core hours efficiency, these kind of things. So it has some benefits, and it also includes the possibility of some built-in monitoring. So basically, we are able to take metrics from Slurman and Torque, but this is, let's say, optional, because you may have your own monitoring solution, okay, for collecting the data. So it's usual that, for example, we deploy this orchestrator together with a Prometheus monitoring solution. And the way in which you define the workflows in Croupier, in Cloudify in general, is TOSCA. TOSCA is an Oasis standard for defining workflows for cloud applications. Because of these things that we have been doing, because what we did in the end was to propose some extensions in line with the TOSCA DCL still, so it's, let's say, complying with the standard. What we have seen is that the Oasis community and the TOSCA working group is really trying to include more things. So their idea is that it won't be only cloud, but also it will support more technologies. The good thing is that okay, it's based on YAML. It's not so complex to understand. Once you see it and you have some familiarity with it, it's quite readable for anybody. And also there are graphical editors that can allow you to or facilitate the way in which you design the workflows. Alim for Cloud is an example. Okay. So about the architecture of the orchestrator itself, well, basically you have on one side some interfaces that can be used for accessing the functionality. You can do it through command interfaces or through REST APIs. There is some part which is dealing with the TOSCA files and the input files. And the center of everything is the workflow engine that basically takes care of running each task of the workflow and sending, asking this infrastructure engine to send the tasks to cloud or to HPC, depending on how you configure that. So as you see, the possibilities that this infrastructure engine is the one which takes care of the connection with the different systems. And in our case, it's possible to ask directly the workload managers to take some jobs, or it's possible to create VMs in a cloud infrastructure and send the tasks that you need to run. As I said, it has the possibility to retrieve some monitoring information, but it's usual that we have some other monitoring infrastructure in which you are collecting information with some exporters and later on to access the information from there, okay, because usually they have their own interfaces. The good thing is that they are, I mean, in our case, we are not dealing with monitoring information in an efficient way. These kind of solutions have databases prepared for time series data, and they are much more efficient. So usually it's much better if you have that kind of solution. So the simulation workflows. So a workflow is in the Cloudify language is a blueprint. Okay, as I said, it's a YAML file. And as I said, what we did is to define some extensions to TOSCA. I put here some examples. So there is a type which is Croupier nodes job, which is for defining that what you have there is a task that will be devoted to HPC. Also, there are different relationships that we have defined. These ones are pretty much in line with the standard ones in TOSCA, but just a bit adapted to the HPC part. And also we had to define the way in which you would define the characteristics of the HPC system that you are going to use, and some information which is necessary, such as, for example, where's the endpoint, your credentials, things like this. Okay. The good thing is that instead of running the jobs by yourself, once you have a blueprint like this, it's possible just to reuse it all the time, and it's not very complicated to write it. And as I said, one of the positive points for the couple simulations is the possibility to define relationships. So I just wanted to show a small example of how you define relationships, which is here in the right side. So you have, for example, just 4 tasks in your workflow. You see that that there are some relationship with respect to which task should happen before, right? So in that case, you just define that a job is depending on another job. Okay. You see that, I mean, the way to define is not very complicated. You say in the relationships that you have a certain type of relationship, which in this case will be job depends on, and it depends on the target, which is first job. So I mean, it's not very complicated in that sense. So what's the idea behind these couple simulations with Groupier, and what needs to be done? So as I said, the main objective is to be able to optimize the performance in the resource allocation, especially when we are running the applications. I mean, what we want to do is when you have two simulations which are closely interlinked, they're sharing data because of this coupling that you have. You need to be careful because depending on the data that they need to share and the way that they need to synchronize, if you are not running them all together, for example, you may have an issue because of the performance. But on the other hand, if the kind of coupling is rather weak and you want or you need to separate the execution, having part of it in the cloud, part of it in the HPC, or in two different HPC centers, because maybe you are trying to run something which is very big and you have only access to some HPC centers which have no so many resources, right? And it may happen that you need to run things in two different centers. So we want to provide some solution that could allow to do this thing. So one way to do it is to use this relationship part and this relation that we can define right now, which is the job depends on. The problem is that it only is useful. It's only useful when you are defining some acyclic coupling, in the sense that it's clear that you have a task which is going to happen before the other one, and they need to share the data. And actually, even if they are running in parallel somehow, you may need to know which kind of data they need to share. The problem is that if, for example, in the example we had before, we have two tasks running in parallel, and you want to model that that coupling between them. Right now, there is no way to do it, which would be the orange arrow that you can see there. Okay.
Javier, 5 more minutes.
Okay. Yeah, it's only 2 slides more. So what we propose is to define two new kind of relationships. First of all, one for a strong coupling. This is when you have two simulations that are coupled through message passing interfaces, because you are using MPI, or well, it could be also GASP, things like this. Or there is some communication set up with sockets. So basically, they are interchanging messages all the time. And the other one is the quick coupling, in the sense that they are sharing data, but maybe in files, or that one of them has to access some REST interface for downloading some data, things like this. I mean, which is not so intensive in terms of the data that you are all the time sharing. And the idea will be just to define these two different types. One could be job MPI coupled with, and you will define in the target part which is a task you are related with, and job data coupled with, which will be working in the same way. So the question would be, okay, so what does it mean in terms of how to allocate the resources, how things should work? So the point would be that in those cases in which we think that we have a strong coupling mechanism, the first option would be always to allocate the both tasks in the same HPC center, no matter if they are acyclic or cyclic, because you know that they are going to be exchanging a lot of information, and especially with MPI, that we are supposed to have a very good network infrastructure based on InfiniBand and things like this. That otherwise you are losing a lot of performance, right? In the case of weak couple mechanism, we could differentiate between acyclic and cyclic, in the sense that in cyclic ones, we expect both of the tasks or simulations to be interchanging a lot of information pretty much all the time. So the traffic could be high. And in that case, the preferred option would be to put them in the same location, but still, depending on the data flow they have and the kind of mechanisms that we have available, it could be possible also to allocate them in different locations. And for the acyclic case, it could be possible to enable this part of allocating one in HPC, another one in cloud, or even if we see that the data to move is too much, then we can force to have them in the same location. Because in the end, this combination of HPC and cloud, or HPC plus another HPC center, is only valid if the amount of data that you need to manage is not too high. Okay, you need to see that there is a trade-off, because the time you lose moving the data will eat this time that you gain when you are running in parallel. And this has also some effect in the monitoring side. That's just this last point, that we will need to monitor the network load in order to see if the decision that we have made is good in terms of the kind of coupling mechanism, and in terms of the allocation of resources, and also the data movement, just to see how much data we are moving in the end, how these are working. Okay, and that's all.
Oh, never mind.
Thank you very much for that very interesting presentation. Are there questions? I remind people to type them into the Q&A panel, and then I will read them out to the speaker. No questions yet. I would have one of my own.
Okay.
How much of what you presented is actually in use?
Yes. We have the orchestrator running. In Hidalgo, it's running, and also in other projects. What we have to do now is to implement these extensions that I was mentioning, more focused on the coupling mechanism part, which is something that until now we were not doing.
Thank you. I'm still waiting for any questions.
Yeah, I don't know if somebody posted something in the chat.
We might actually, so Lourens, did you want to ask a question? You see, the panelists aren't able to type in into the Q&A themselves, but...
Right, yes, I just have a question, if you can hear me.
Yes, go ahead, please.
Right, I was wondering about the difference between this job data coupled with in an acyclic relationship and a normal TOSCA dependency, because it seems to be that in both cases one step would run first and then the second step runs, and there's information passing from one to the other. Or am I misunderstanding this?
Mm-hmm. Yeah, in principle, this is the way in which it's working, but it's also true that yeah, I would say that that's the way to go right now. Yes, the point is that we can do some interpretation of it, because even if you define, because as you can see, the kind of relationship which are defined that we are using right now are not exactly the ones that are defined by TOSCA. Okay, so at some point it's up to us to define if we would like to do some interpretation in which you don't need to really wait until the end of the previous task. So you can use it like a dependency, saying that there is this relationship, but it doesn't mean that it has to be finished before the other one starts. I mean, it's up to the way in which we implement internally in the orchestrator, because we have the possibility to change that. So in that case, we could allow the, I mean, we can enable that acyclic mechanism just with the normal relationship. This one depends on.
Okay, that's clear. Thank you.
I see no questions from the general audience. So thank you very much. Javier. It was a very interesting talk.
Thank you.
The next speaker, via a pre-recorded thing, but the speaker is online, is Philipp Neumann on open boundary modeling in molecular dynamics with machine learning. Please go ahead.
Hi there.
Welcome everybody to my talk on open boundary modeling in molecular dynamics with machine learning. And thanks to the organizers for putting together this digital session. When we talk about molecular dynamics, here's what I refer to in this case as molecular dynamics. So we will look in the following into systems assembled of many spherical particles that all move according to Newton's equations of motion and that interact via force fields. We will only look at the so-called Lennard-Jones interaction potential that is given down here in a short-range case. That means particles will only interact via this force field when two particles are within a cut-off radius distance from each other. Otherwise, we will not consider any forces, so only within this cut-off distance RC. All the implementations that I will refer to in the following have been established using the software lumps. Concerning multiscale, the context that I want to make up and explain to you here is the following. We work a lot with so-called molecular continuum methods in which we look into fluid dynamics at the molecular scale. Therefore, we couple in a domain decomposition both CFD solvers and molecular dynamic solvers. The challenges that we have here are, besides consistent mass and momentum transfer between the two solvers, consistent modeling of the red-colored boundary region of our MD system. So the white domain here is all solved by a CFD solver, and here's the MD simulation, and we have to model this boundary consistently. What is the challenge here? In periodic simulations, our red particles which are inside our domain here would feel some particles that are on the other side here. That would simply be replicated to here. In our case, this is not the case anymore because we would have an open boundary here normally. And one of the essential problems here is that our particle would not feel any force contributions from particles over here because there are no particles. Thus, we have to construct a valid open boundary force that pushes back our red particles and that acts from here onto these particles close to the boundary here. These boundary force models should satisfy several constraints in the optimal case. They should first of all impose the correct average hydrodynamic pressure on our MD system. They should, in the optimal case, take into the account the molecular information of our MD system, because then you also make sure that you can construct a valid model from the molecular perspective. The boundary force model should conserve the molecular structure of our MD system close to the open boundary. And in terms of computational science, it should perform at an acceptable computational cost. There have been several approaches that have been discussed in literature so far and that are listed here. So analytical functions based on empirical parameter fitting, forces constructed from the radial distribution functions, RDFs, from our particle systems, then dynamic adaptation schemes that simply steer the force according to the density of the fluid. So if you have a bigger density, you have a bigger force that pushes the particles back, and parameter space exploration approaches that simply considered the boundary forces over a wide range of pressure and temperature values, and from these some fitting formula were constructed. I will refer to this method as the SU method in the following. And my talk will now focus on constructing a machine learning based boundary force model. We will look into whether it reaches these 4 points, these 4 goals, and I will also refer at some points to the SU method. For machine learning, we'll make use of Google TensorFlow and we'll consider the standard neural network formulations. We'll look at a very simple network, so we just get started with working with neural networks and machine learning at the chair, so any inputs from your side are here also highly appreciated. So we look at a simple network with one one hidden layer, 5 neurons, standard settings in Google TensorFlow. And what we use for input and output are on the one side the distance of the particles from the open boundary, which is sufficient as we have spherical particles and they are thus rotationally invariant. So we just look at the distance from the boundary. And our network should deliver us back the orthogonal boundary force pushing the particles orthogonally from the boundary back into the MD domain. How do we do the training? Well, we start a simulation with periodic boundaries, and in this simulation we introduce a so-called virtual wall. This allows us for every particle that is close to this virtual wall to detect which force contributions come from the other side of this virtual wall and act onto this particle. For example, if a particle is placed to the right of the virtual wall, then we can find out which particles from the left side of the virtual wall in this periodic simulation interact with this particle, and from this we can generate pairs to train our neural network. That is, for every pair of distance force values for a particle that is close to the virtual wall, we can feed our neural network with and train it. We focus particularly on homogeneous particle systems sampled at this thermodynamic state. We have a cutoff radius of 2.5 sigma, which is also rather standard. And what we do is, after training our network, we introduce in our periodic MD simulation on the left and on the right reflecting boundaries that simply hinder our particles from escaping. And on the other side, we add the machine learning based boundary force model to push the particles even further back so that we get the right thermodynamic pressure for amongst others. The other boundaries are left periodic. What you can see here in these graphs are now the force values that were obtained with different models. So on the one side we have the predicted force, which is our machine learning based force, and the continuous line is the SU method based force model. And all the dots that you see around here are the strongly fluctuating MD values for boundary forces. So the forces that we obtained from our virtual wall experiments. If you have a close-up on the forcing values, then you see that both models are qualitatively similar, but they do differ significantly, especially when we come close to the open boundary. So here, both models differ. In this case, we used 80,000 samples to train our network over 30,000 epochs of training. Let's look into the physical properties of this approach. Therefore, we looked at the density profile of our simulation with open boundaries in a boundary strip of thickness of 1 cutoff radius close to the open boundary. Normally we would expect a flat line because we have a homogeneous particle system, but close to the boundary we observe some slight oscillations in our density. This holds for both the SU force and our machine learning based force, and this is also seen in basically all open boundary force models that are out there. But still we get the same, basically the same quality as the parameter space exploration SU force. We also looked into the radial distribution function sampled in this boundary strip only, and we see that both models do a good job here compared to the periodic simulation. We further looked into the velocity distributions of our particles in this boundary strip, and also here we see that both our machine learning based force and the SU force do a good job and predict the right and normal distribution of the velocity component in x direction. We also did a close-up look here by looking at an even narrower boundary strip. That means we restricted fuse once to a boundary strip of half a cutoff radius thickness and 1/8 of the cutoff radius. Here you again see that both the radial distribution function and the velocity distribution in this case are matched basically perfectly. If we are very, very, very close to the boundary, as we have it on this side here, we see that we have slight differences in the peak of the radial distribution functions and very slight perturbations in here in the distribution of the velocities, but it's really only slight deviations. As you might have observed, these data were taken from the best run that we had with our machine learning model, where we used 19,000 samples only, trained over 30,000 epochs, but also for the other cases that delivered us valid configurations, we obtained similar results for these plots. Next, we thought about how to reduce the overall sampling cost and looked into binning. That is, within the boundary strip close to our virtual wall, we took this boundary strip, we divided it into several bins, and per bin we took a certain number of samples. In this case here, we took 100 bins to discretize our boundary strip and collected 512 samples per bin. You see that based on this kind of training, we still obtained very good results, similar to the regular sampling that you see on the right again for comparison. And we could do this by using about 36% less samples than in a regular sampling case. Concerning the runtime of our model, here you see the overall runtimes for periodic MD simulations and simulations with open boundaries. In the last column, you see the number of time steps that you can carry out per second in each of these scenarios. You see that the periodic simulation takes about 42 MD steps per second, while the Zoom model performs even slightly faster at 43 time steps, and our machine learning based force model performs at about 40 time steps. So the machine learning model is slightly more expensive, but it's really only slightly more expensive. I mean, 2 time steps per second is not so much in this case. Concluding, I have presented to you our machine learning based boundary force model for molecular dynamic simulations in the context of multiscale settings. We are pretty happy with the results, but yet we would like to have an even better understanding of the underlying machine learning technology that we use. And also we would like to be interested in applying our methodology to multi-site molecules where we do not have this rotational invariance of the particles anymore. This will be also interesting from the machine learning based point of view, because then we have a higher dimensional space that we want to explore. Besides, we would like to look into on-the-fly training and evaluation. That is, it would be interesting to introduce this virtual wall on the fly during the multi-scale simulation, in particular in case that we have a transient simulation, and thus on the fly generate our neural network model and improve our neural network model basically and adapt always to our simulation state. Thus, I've come to the end of the talk, and I think that this approach of combining our machine learning based boundary forcing with the multi-scale simulation is another nice example of combining a data-driven approach with a multi-scale simulation and putting both together in an effective and efficient way. Thanks a lot for your attention. Looking forward to your questions and comments now in the question round.
Thank you very much. We have 2 questions so far. The first from Javier Dominguez. Has the speaker taken into account errors due to the size of the numerical box? This is important when one performs MD simulations with fully periodic systems.
Can you hear me first of all?
We can hear you.
Yeah, great. We have not explicitly determined and checked that, but all the simulations that we carried out there were all based on standard setups that we have used for quite a while. Let's put it like that. So basically, if you look at other works on the boundary forcings, then typically people use the same size of boxes for their experiments. However, yes, I know that there are, or we know that there are dependencies on the box sizes. That's true. At the end of the day, with these multi-scale simulations, the idea is simply to really cut down the MD domain as far as or as much as you can, restricting considerations to small portions of MD just for the sake of computational expense. That you introduce some additional errors here is clear. In our case, it's not so dramatic, but it really depends on what you want to measure with the MD system. So sometimes this can be crucial. I agree.
Okay. The next question from Ben Hurricane. I apologize if I'm butchering your name. Have you thought about non-equilibrium situations with energy or particle flow over the boundary? Presumably other variables than distance are needed.
Well, so sure, we did think about that. So actually our goal is also to integrate this approach in our coupling tool that we have used for real flow scenarios where you have mass fluxes, where you have to insert particles, remove particles, and so forth. We did not integrate it there yet. What we did already integrate there was the SU method and used that one for the forcing. And SU and colleagues have already shown that their approach works for these kinds of scenarios as well. But sure, this is more challenging. And then again, you have to go back and revise the analysis once again, just to make sure that you're on the safe side with what you're modeling at the boundary. Sure. So this was like the first shot, and then you have to go into more details if you go into the real fluid flow scenarios.
Thank you. The next question is from Aaron Ho. Neural network models tend to get predictions worse near the edges of training set space. Since there's no negative distance, perhaps the discrepancy near d equals 0 could be adjusted from biasing the training set with more samples there. In that sense, have you tried using non-uniform number of samples per bin to see the effect of biasing on your results?
Thanks for this remark. To be honest, we did not do anything more than what we presented so far, basically. So this is really for us the first shot on using neural networks for this case. So any comments on this is highly appreciated, and I would really be very happy to receive this comment from your side once again, maybe a little bit more detail via email. That would be very helpful for us to just improve on our methodology. I will also just take out that and copy that from the questions and answers part if I find it, so that I keep this on our list. So very, very big thanks to that.
Then from Andre Bruckno. Thank you for an interesting talk. Could you comment, please, on possible application of your neural network method to multi-component systems? For example, binary mixtures. Would it be feasible, and what complications do you expect?
Ooh, good one. First of all, I don't see a reason why it should not be applicable. Let's put it like that. However, I can definitely not comment on how good it will work at the end. So for that, we just didn't do any experiments on that. So this would be a very, very interesting point to find out. So we can just get in touch and discuss it in more detail, and also think about potential setups that we could go through together to evaluate that. Would be a very, very interesting thing. So, but at least I don't see a reason why it should not work. I mean, it would probably boil down to having two neural networks being trained for two components or something like that. Why not?
Thank you. And the last question from Javier Dominguez. The speaker mentioned he uses a Lennard-Jones potential. Has the speaker considered the use of TOSCA, ZBO, EAM, Gaussian, and approximate potentials, and SNAP?
Considered yes, done no. So as I said, so this is what I presented here is really like the very, very first shot on using this methodology, and many scenarios that are carried out in terms of fluid dynamics at the nanoscale really make use just of the Lennard-Jones potential. So that's why we took this as a first shot here. So that's the main line of argumentation from our perspective. What we do plan on top is not only to look at these test scenarios, but we also have some interactions and collaborations with process engineers who again look at entirely different setups, but where it would be interesting to incorporate this molecular continuum scenario. And they are automatically coping with absolutely different kinds of potentials. It's not only TERSOF, what they are also interested in, but they also have dipole, quadrupole, and so forth, and then also multi-site molecules that are already mentioned in the conclusion. And so going in this direction would also be a very interesting point of view, but yeah, you can't do everything at the same time, right?
Well, thank you very much. On behalf of the audience, I would like to thank you for that very interesting talk. We move on to the next talk on easing multiscale model design and coupling with muscle 3 by Lourens Veen. Please go ahead.
Hello, everyone. My name is Lourens Veen. I'm an eScience research engineer at the Netherlands eScience Center, and I'm here today to talk about Muscle 3. Muscle 3 is the third version of Muscle, which was developed at the University of Amsterdam Computational Science Lab. And Muscle 3 specifically is a product of the EMUSC project, which is a collaboration between the university and the Netherlands eScience Center. So today we are going to talk about multiscale coupling multiscale models. And to do that, we need to have some kind of example of a multiscale system. So what we have here is an artery. At the top and the bottom, you can see the walls of the artery in orange. That's not entirely realistic, but we'll go with it. And in the middle is the lumen, which is the open area through which the blood flows. You can also see two gray squares, which are a stent, which is a wire mesh device that can be inserted into an artery and extended outward to push the artery open if it is clogged. Now that damages the artery. So as you can see on the right, the body responds to that with a healing response, which entails the cells in the wall growing to cover the damage. If you're interested in that model or want to know why you would want to simulate it, see the paper. What's important for our present purposes is that there are three processes here. One is the stent deployment, the second is the growth process of the cells, and the third one is the flow of the blood through the artery. I'm going to assume that we have three programs that each simulate one of these processes, and that we want to couple them together into a linked simulation that simulates the whole thing. Now, in order to do that, we first need to figure out how we need to connect those models together. We can do that by using the multiscale modeling and simulation framework. This has been developed previously at the University of Amsterdam and at the University of Geneva. And all the details are in the papers referenced here. I'm just going to show you how it would apply to the model I just presented. So at first we have to look at the domains on which these processes take place. You can see that on the left here. In space we have two domains. We have the wall of the artery and we have the lumen. On the wall the stent deployment takes place because it deforms the wall. And also the cell growth process takes place on the wall. Blood flow goes through the lumen, so of course that is in that domain. In time, on the horizontal axis, we can see that there's first a deployment phase, and after that there's a healing response. During the deployment phase, only the stent deployment model needs to run. During the healing response, both the cell growth and the blood flow need to be simulated because they influence each other. On the right, we have a scale separation map. This shows how large the processes are in space and in time, but not where they are. So what we can see here is that the blood flow model is quite fast. It has a time step of about a millisecond and it converges in less than a second simulated time. The cell model, the cell growth process, is much slower. It has a time step of about an hour and it takes weeks to months of simulated time to complete the process. So what we can see here is that these models are timescale separated. With respect to space, they are actually similar. The resolution is about the same at around 10 microns, and they both simulate an area of about a couple of millimeters in size. So this is actually all we need to know in order to be able to couple our models. But there's one more thing, and that is that we need to know what a model is. A simulation model, so a computer program, what it does and when it can exchange information. Now, according to the multiscale modeling and simulation framework, this is modeled by the submodel execution loop. And the submodel execution loop says that a simulation model starts with initialization, during which it can receive information from another model, from the outside world. Once it has its initial state, it can produce intermediate output, which can be sent somewhere else. Then it needs to update its state to get to the next time step. And it may need to receive information like boundary conditions from somewhere else to do that. And then it goes back, produces another intermediate output, and it keeps looping until it reaches its final time step. At which point, on the right, there's a final output produced, which can again be sent somewhere. Now, any model with a time integration step works like this. And if you do the loop in the center 0 times, you can also you can also have models that are simply a function. Putting all of that together, we get the following solution for our model. On the left, you can see the submodels and the connections between them. On the right is the timeline of the simulation. So the stent deployment happens before before the healing response. And that means that the final output of the stent deployment model needs to be sent to the initialization phase of the cell model. By the cell model, not the blood flow, well, because they share a domain. You can see that on the right as well, that the stent deployment runs before the cell model. Now, the cell growth and the blood flow happen simultaneously, but they are timescale separated. That means that the blood flow model needs to do a full model run for every time step of the cell growth process. We can see that on the right here. That can be achieved by wiring the intermediate output of the cell model, which is produced for every time step, to the initialization step of the blood flow model. That allows the blood flow model to do a full simulation, produce a final result, which is then fed back into the state update of the cell model as a boundary condition. The cell model loops back, and the blood flow model is run again, and that's how the whole simulation proceeds. Now that's the theory. Of course, we need to implement this. We have our programs, and now we're going to use Muscle 3 to tie them together. This is what that looks like. We have our 3 programs at the bottom, and each of those programs are linked to libmuscle. Libmuscle is a perfectly ordinary library. It doesn't require you to do anything special. You just link to it as you would any other library and call functions to be able to exchange information with other models. There's also the muscle manager, which is sort of a coordination component. It reads a configuration file that says how the model should be connected, and then it talks to all the running programs and tells them who they should connect to. The different programs then set up peer-to-peer connections between themselves and exchange messages and run the simulation. This configuration file is in the YMMSL format. I was recently told that that is a complicated name, and I guess it is. But fortunately, the file itself is not so difficult to understand. It's simply basically a textual version, a YAML, of the diagram I showed before. So we have the different components of the simulation. They have a name through which they can be referred to, and we have to specify which program needs to be run to actually run the simulation. Then there are the connections, which are called conduits, and they are specified like this. They connect a particular port on a particular submodel to another port on another submodel. In this case, the final state out of the deployment process is connected to the initial state in of the cell growth process, and the other 2 connections are here. This configuration file can also contain settings, so all your model parameters and other things can go in here, and Muscle will distribute them to all the different submodels, so you don't have to manually generate many different configuration files or keep them in sync manually. Makes your life a lot easier. Now, of course, we need to couple our models to libmuscle. For a full example, I refer to the paper or to the muscle documentation, but I want to give a quick taste of it. This is the state update loop of the cell growth model. So it's just going to step through time until it reaches a final time, which has come from a setting. And for every run through the loop, we first have to produce our intermediate output. So we create a message object with the current simulation time, the simulation time of the next message, and the geometry of the artery, which is what we need to send to the blood flow model. This can be represented using any Python built-in type, lists, dictionaries, NumPy arrays. You can mix and match, so it's actually quite flexible. Once we have our message, we can send it on a particular port, and that's all we need to do for an intermediate output. Then it's time for the state update. So we receive our boundary conditions and we use them to update our model in some kind of model-specific way, and that gives us the next simulation time step, and we can loop back and do it all over again. So the goal of the EMUS project is to do uncertainty quantification and have more efficient uncertainty quantification. So that requires some advanced algorithms, and that means that we want to be able to rewire our models easily. This is an example of this. So we have a plain Monte Carlo uncertainty quantification of the model that I just showed. On the right, you can see that model. It's all the original code, no changes. It's wired up in exactly the same way as before, but we have an extra component, a sampler. And what the sampler does is it produces a sample of the uncertain parameters. So if you want to have, say, 1,000 samples in our Monte Carlo ensemble, it will produce 1,000 sets of values for the uncertain parameters. Now, since we don't have that exascale machine yet, we may not be able to actually instantiate 1,000 copies of our model simultaneously. So instead, we're going to instantiate n of them for whichever value of n will fit your cluster. And we're going to insert a load balancer in between, which is going to take the 1,000 runs and distribute them over these n instances. The parameters that are generated are sent to the muscle settings in port, which is a special port that receives them and overlays those parameters on top of the ones from the central configuration file. They'll be passed automatically to all the other models as well. And that means that each of these runs in a slightly different universe with slightly different parameter settings as required for an uncertainty quantification. Results are produced by the models and mapped back by the load balancer to the original sample ID, and then passed to the sampler, which can calculate the summary statistics. Now, this is only the beginning. You can do much more advanced things with surrogate modeling, training those surrogates on the fly. But the nice thing is that you can do all of it without having to rewrite your code and without having to maintain different versions of the code for doing different things in parallel. So, Muscle 3 is not the only framework for coupling models out there. In fact, there are very many of them. Way too many to discuss here, but I want to pick out two and compare them to Muscle to give you an idea of where Muscle sits. The first of these is Precise. Precise was developed at the technical universities of Munich and Eindhoven. It's a multi-physics framework and is mainly intended for modeling solids in flows. So it has adapters for CFD and FEM solvers. It has scale bridging and coupling schemes that are appropriate for solving such problems. And all information that is exchanged is defined in terms of variables on meshes. So that's actually quite a different problem from what Muscle tries to solve. It's scale overlap, not scale separated, and it's fairly specific, where Muscle is completely generic. But the technical solution is actually quite similar. In Precise, the submodel is linked to a library. They run in parallel. There's a central configuration file, and there's no manager, but beyond that, the setup is pretty much exactly the same. So it's the same technical solution to a different problem. Now, most coupling frameworks are actually intended for multi-physics simulations, but there are some others for multiscale as well, including AMUSE, which was developed at the University of Leiden Astrophysics Department. It comes with a library of astrophysics models, pretty much all of them, and they are wrapped in Python. You couple them by writing a Python script, and that Python script then says, I'm going to take some data from one model, I'm going to put it into another model, and then tell that model to update to the next time step. So you have to write the whole simulation behavior in that Python script. AMUSE offers some extra facilities for handling units, converting data types for describing grids and particle collections. And altogether, it's actually fairly generic. There's a version of it for oceanography as well. So this is a similar problem to what Muscle solves, but it approaches it in a very different way. You have your Python script, which is more flexible. You can do anything you want, but you have to do it, and you have to maintain and debug that code. So there's a bit of a trade-off there. And I'm not actually sure for which cases one or the other would work better. We have to kind of see and experiment, I think, to find out. So if you're going to pick a framework, my advice would be to have a look around, see the references at the bottom for a start, and find the most specific solution that does what you need, because that will save you the most time. If what you need is multiscale, so scale separated, you like this idea of modularity and flexibility, You maybe have your own models that still need to be connected to something, so you want to have a lightweight system that's easy to link to. And or you want to do efficient UQ or some other advanced algorithm, then maybe you're going to end up in Muscle 3. So to wrap this all up, Muscle 3 is open source under the Apache license. It's developed in the open on GitHub. There's no secret development version on my laptop. It's all out there. It's well documented. There are tutorials and API documentation for all supported languages. It's still in somewhat early stages. We are currently porting the first models from Muscle 2 to Muscle 3. Also some models that have not been connected to Muscle before. And it's actually going quite smoothly, so I'm quite happy with that. But of course, that doesn't mean that we're already done. I'm currently working on instantiating models via pilot jobs so that it will be easier to start up the simulation. We want to have some more advanced UQ support still. That's the goal of the Emacs project. Profiling is partially implemented but needs to be finished. There are some logging improvements to be made. And of course, once we get that exascale machine, we wanted to work on that as well, which will require some more performance and scalability improvements. With that, I thank you for listening. And if there are any questions, I'll be happy to answer them. Thank you.
Thank you very much. I found that talk very interesting indeed. The first question is from Jörg Unger. Is the coupling of different models always explicit? Or is there the option to iterate over the models until convergence is reached, in particular for fully coupled problems?
So I'm not sure I understand you correctly here, but indeed any model, the example I showed had a model that ran for a fixed number of time steps, and that is not the only option. So you can actually have a model that detects convergence and then stops. And if you have a macro-micro coupling, then if the macro model stops at some point, this will be detected automatically, and that means that the micro model will also not run again. But both programs will run simultaneously, and Muscle actually takes care of making sure that the micro model is run the same number of times as the macro model has time steps, even if you suddenly decide to stop running because you have converged, for instance. And this is something that was actually not so easy to implement. So that's why Muscle does it for you. So all you need to do is connect the models to Muscle and run your time integration loop for any number of steps, and Muscle will take care of the rest. I hope that answers your question.
If the audience member, Jörg, would like to post a follow-up, please do so. Are there any other questions?
I think there's one in the chat, actually.
Oh, yes. From Dara. How is resource allocation arranged per submodel? Is heterogeneous distributed computing supported?
Well, to start with heterogeneous distributed computing, oh, sorry, no, I'm confusing this. Right now, you have to start your submodels yourself. This is the ongoing pilot job work that is still in progress. So how this is going to work is that in the configuration file, you will be able to say how many cores and other resources each submodel needs. And then Muscle will be able to start these. At the moment, it assumes that either things are running locally or within a single allocation on a cluster. So we do not have support for running on multiple clusters and doing communication between them. That could be added in the future. So it's designed in such a way that it can be added. But so far, I haven't seen a use case for it, or at least I haven't had any people ask me to add it. So it's not currently yet possible.
Okay, there's a thank you from the analyst on that. Are there any other questions? We have about a minute left. In that case, I'll take the opportunity. What was the biggest challenge in actually in moving from Muscle 2 to Muscle 3?
I think actually the making sure that models run exactly the number of times that they need to run. That was pretty tricky. And the other one is addressing, because we have sets of instances, and that means that there are very many simultaneous programs running, and all that needs to be coordinated. And in particular, getting all the parameters to go to the right place, and making that intuitive, kind of designing that in such a way that it does what you expect, even if you didn't think about it so much. That was also quite tricky, but I think that it's working out well so far.
Thank you very much. The next speaker is Onnie Luk on time bridging techniques for multiscale fusion plasma simulations. Please go ahead.
Good morning. My name is Onnie Luk from the Max Planck Institute for Plasma Physics. In this presentation, I will talk about the work we have done on time bridging techniques for multiscale fusion plasma simulations. To begin, I want to give a bit of a background and motivation behind our work. To answer the question, what is fusion? It is a process in which lighter, positively charged particles fuse together to produce heavier particles. And in such process, energy is released. This is exactly how the sun and other stars power themselves, and we want to bring this power source to Earth as there are two major advantages. Number one, fuel availability. Heavy hydrogen isotopes such as deuterium and tritium required for fusion can be extracted from seawater and produced from the fusion process itself. Number two, it is a clean process, no contribution to greenhouse gases, and it doesn't leave behind dangerous long-lasting radioactive waste that we see from nuclear fission plants. In order for the nuclei to fuse, we need to heat the charged particles or plasma to about 100 million degrees. One way to contain a hot plasma is to guide the charged particle trajectories with a magnetic field. Tokamak is a confinement device that uses this method. There is an international effort called ITER to build an experimental tokamak reactor that can demonstrate the feasibility of fusion power. This reactor is expected to produce 10 times the input heating power. Currently, there are 7 members in this project: the EU, China, India, Japan, South Korea, Russia, and the US. There's a saying in our community: fusion is always 50 years away. Fusion research has been going on for a very long time, but we still haven't demonstrated its feasibility. As it turns out, the micro-instabilities developed in plasma turbulence can affect the overall transport and ultimately destroy confinement. To fully simulate the impact of turbulence on fusion device performance is challenging. Let's take a look at the continuity equation to see why that is. The density is described by the transport process here, while the particle flux right here is determined by the plasma turbulence process. Now, if we take a look at the scale map on the right, we will see that the turbulence happens at millimeters in space and microseconds in time, while the plasma transport happens at meters in space and seconds in time. With the scale disparity between turbulence and transport, we need numerical models that can bridge those two to fully understand the dynamics of fusion plasmas. We have constructed a workflow that takes the component-based approach. It couples single-scale models and allows them to pass information from one to another. In this graphic here, it shows that we have a transport code that calculates the plasma profiles such as densities and temperatures. This information gets distributed to the equilibrium code, which provides an updated equilibrium geometry, and to the turbulence code, which calculates the fluxes. This information is then passed on to this module that converts fluxes obtained from the turbulence code into transport coefficients required by the transport code. We use this workflow to simulate the plasma inside the Aztecs upgrade tokamak. Here we show the time history of the electron heat flux at the top panel, the time step size of each iteration in the middle panel, and it's fixed at 0.01 seconds, and the electron temperatures in the bottom panel. Each color trace represents a measured quantity on a magnetic flux surface or flux tube. The flux tube is visually illustrated in the tokamak schematic on the right. The normalized rotor values right here in the legend is the toroidal flux coordinate for each one of these flux tubes, with the lowest value representing the innermost flux tube and the highest value representing the outermost flux tube. The electron temperature, which is calculated by the transport code, experiences large fluctuations in time. These fluctuations do not allow the plasma to converge to a steady state. It is especially apparent for the flux tubes closer to the core of the plasma. On the other hand, if you look into the heat flux, you can see that, which is calculated by the turbulence code, experiences rise and drops in a short period of time, and these forms bursts. The time evolution of the electron temperature displayed here is not physical, but instead it is artificially produced from the timescale mismatch between turbulence and transport codes. To tackle the timescale mismatch, we have created a way to bridge the turbulence and transport codes. Instead of having a fixed time step size for each iteration, we made it adaptive. Specifically, the time step size of each iteration would depend on two parameters. A limit set on the change of electron temperature, and a limit set on the change on electron temperature gradient. Basically, we study the value from the previous time step, and then we take the difference from the current time step and divide that by the previous time step. If this is less than the limits we set, then we deem that the current time step okay. But if it's not satisfied, that means the change is too large, so that we have to divide the time step by 10 and then perform the test again until it's satisfied. With the adaptive time step implemented, we run the Aztecs upgrade case again, with the limit on the change in electron temperature set to 0.1, and the limit on the change in temperature gradient set to 0.05. And we can see here in this time history that the large fluctuations in electron temperatures that we observed before has disappeared. Now we look into another tokamak scenario. We take a case from the jet tokamak, and we set the limit to 0.2 for electron temperature, and the change in electron temperature gradient limit to 0.1. And here we also see that the fluctuations in temperatures are confined, are not large fluctuations. Now that we have the adaptive time step implemented into the workflow, we can continue the simulation for a long time. However, it is a good idea to know when to terminate the simulation so that we don't waste computing resources. Therefore, it is important to realize when the plasma has reached a quasi-steady state. Our approach is to take a number of time steps at a time, let's call it capital N, and then assign it a time group ID little n. Then we take the electron temperature from these capital N time steps and take an average of that and calculate the standard deviation for each of the flux tubes. Now that we have the average electron temperatures, we can then compare that to the previously calculated values from the previous time groups, and we give it a number G, and we call it G. If the previous average electron temperature from all G time groups are within the current time group's average electron value plus or minus plus/minus its standard deviation, then we said the quasi-steady state has been determined. Here we apply this method to the Aztecs upgrade case, and we try different time steps per group. We tried 200, 500, and 1,000, and we compared that to the previous 5 time groups. And the electron temperature profile from each test show agreeable results, especially at the outer flux tubes. But overall, the profiles have similar shapes. Now we apply the same method to the jet case with the number of time steps per group set to 500 and 1,000. Again, we compare that to the previous 5 time groups. The results are almost identical, except especially for the inner and the outer flux tubes. We also try another approach. We basically take every second worth of data, and then we find the minimum value and the maximum value of electron temperatures. And then we take an average of those two values. Now for this is done for every flux tube. Next we look back into every second of the previous m seconds worth of data. And then there we calculate the percentage difference of the previous electron temperature average and the current temperature electron temperature averaged. If this value is below the threshold limit L, then we say this is, and also if it is true for every flux tube, then we claim that this is, we have reached quasi-steady states. Here we show this approach being applied to the Aztecs upgrade case. We have the limit, the threshold limit set to 5%, and we look into and compare this with the previous 4, 6, and 8 seconds worth of data. Again, we see similar profiles like as we saw in the first method. Again, we apply this to the jet case using the second method, and we set the threshold limit to 5% and extend it to 10% as well. And we look into previous 2 and 4 seconds worth of data as comparison. Again, the profiles look very similar to each other. Now that we take the quasi-steady state electron temperature profiles from both methods, now we can compare them. The electron temperature profiles from the Aztecs upgrade case are plotted on the left and the jet case on the right. In the Aztecs upgrade case, we can see that the electron temperatures at the outer flux tubes are well in agreement. The electron temperatures at the inner flux tubes are as well in agreement, but they are more or less within 1 standard deviation away from each other. As for the jet case, we see more variations from the profiles using different methods and different parameters. To determine whether these methods are agreeable with the experiments, we need to perform validation. Here we take the Aztecs upgrade results using the first quasi-steady state method and plot it into as the thick blue line here. The left panel is the ion temperature profiles, and the panel on the right is the electron temperature profiles. The UQ results are also plotted into these plots. The thin blue line here is comes from the results using electron source and boundary as the uncertain parameters, and the red is basically results using UQ results using the ion source and boundary conditions as the uncertain parameters. Now we compare them with 2 experimental data from 2 different shots. They're plotted in purple and green, and those are taken at quasi-steady state. We can see that on the left panel, the ion temperature profiles have somewhat agreeable results. However, if we look at the electron temperature profiles on the right, we can see that there is no universal agreement towards the core region. The UQ results especially are far from agreement with the experiments and the simulation before UQ is introduced. This can be explained by the fact that the turbulence code used in the UQ simulations here it's a simpler model that doesn't require much computing resources. versus the results in the simulation without UQ uses a more complicated stochastic model. For more information on the UQ studies, please channel in for Jalal's talk tomorrow. To give you a summary, a component-based multi-scale fusion workflow is introduced, but the issue is there's time scale disparity between transport and turbulence code. Time bridging methods are introduced here using adaptive time steps. We introduce two different parameters to control these adaptive time steps. We look into the limits on the electron temperature change and the limit in electron temperature gradient, in the change in electron temperature gradient for the time scale bridging method. Quasi-steady state is also defined using two methods. One is the time average on fixed number of steps, and the second method is taking an average on the maximum and minimum electron temperatures for every second worth of data. And we look into both aspects of grade and jet token max scenarios. For the next steps, what we see right now is that the adaptive time step method and techniques I showed here today are applied to electrons only. The next step is to apply these methods to the ions as well. Not only do we apply the limits on the change in electron temperature and electron temperature gradient, we will also apply these limits to ions. Another task we will tackle is to validate and apply UQ and sensitivity analysis to these production cases. That way we can give a more qualitative comparison between simulations and experiments. And that's the end of my presentation. Thank you very much.
Thank you very much. Are there questions? I don't see, there's one. Lera is asking why a different turbulence model was used for UQ. The discrepancy is striking. Could it be improved?
Hi, Lara. Thank you for, can you hear me first of all?
We can hear you.
Okay, good. Fantastic. So the reason we're using a simpler model for UQ is because we're testing the method, and the stochastic model is much more expensive computationally. That's why we didn't use the stochastic model in our UQ tests. That's our next step as well. So yeah, that's planned.
Are there other questions? If not, then I will ask one. To do these investigations with the full-scale model, how many compute hours are required to do essentially, let's say, 1 second of simulation?
So for me, in these productive cases, I use either 1024 cores or 2048, so depending on the situation. And so of course, that's only for one case. If we want to do UQ, we require many more samples. That's probably, I think in the current UQ simulations, we use about 250, I mean, to do the entire workflow, we use about 200, 300 samples. It can be more. So using PCE, and that would be a lot. And our goal is also to replace this stochastic model with a surrogate model. So that way we don't have to use all these computing resources when we do UQ. Does that answer your question?
Thank you very much. Yes.
Thank you.
Last chance for some questions. If not, then we move on to the last speaker in the session on development and application of the statistically similar representative volume element for numerical modeling of multiphase materials. Please go ahead.
Good morning, my name is Łukasz Rauch and I represent AGH University of Science and Technology from Krakow. And together with my colleagues, I would like to present today our work, development and application of SSRVE idea for numerical modeling of multiphase materials. At first, I would like to show you the motivation and short introduction to our work, and then I will explain SSRV with gradient properties, application of sensitivity analysis, and I will shortly discuss obtained results and conclusions. The main motivation of our work is the development of advanced steels. What you can see in this slide is so-called banana plot, which presents many grades of steels which were developed from 80s through 90s, 2000 and 2010. Our goal is a group of DP and CP steels. They are called dual phase and complex phase steels, which were developed in fact long ago, because this is the first generation of advanced high strength steels. But what we would like to show you today, that we can still obtain, still use these steels in industry, and we can still design optimal processes to use these steels in heavy industry. DP and CP steels, as I said previously, dual phase and complex phase steels are composed of phases with different properties. For example, dual phase is composed of ferrite, which is soft, and martensite, which is hard phase. And on the right side, we can see complex phase, which is composed of more than two phases, hard martensite and binite, and soft matrix, ferrite matrix. We have also some retained austenite inside different phases. So two phases with different properties results in very sharp gradients of properties between these phases. This results in low local fracture resistance. This leads to an interesting question: whether it is possible to achieve more balanced mechanical properties of multiphase steels by tailoring the microstructure gradients. The answer is yes. We can theoretically use so-called smooth gradients. And in fact, obtaining of the smooth gradients is a technological problem, but what we want to do is to apply multiscale modeling methods to design these processes of steel manufacturing and exploitation. As I mentioned previously, we used multiscale simulations composed of macro and micro scale, between which we can exchange some information, for example, temperature, strain rates. And we have two options to model these simulations: mean field models and full field models. But if we are talking about modeling of gradient properties, we have in fact only full field models to be used. But excuse me, before application of these models, we have to answer two questions. We want to address two main problems. The first one is high computational intensity, which is caused by large number of elements and difficult process of parallelization or distribution of calculations in a whole domain. Here we want to apply SSRV idea. And the second problem, how to return information about gradients of properties from micro to macro scale. So if we want to go back from lower to upper scale, we have to pass some information in form of scalar value. As I mentioned, to solve the first problem, we applied SSRV idea, which is called statistically similar representative volume elements. This approach was proposed 7 years ago by Brent, Schroeder, and Balzani. What we proposed in this idea is algorithm of generation of this statistically similar representative volume element for different grades of steels. What is SSRV? This is an approach which approximates a real microstructure called RV, representative volume element, in such a way that rheological responses in macro scale after homogenization are the same. We can see example of this approach in the upper right corner of this slide. The algorithm of SSRV construction is composed of two steps. The first step is focused on preparation of data analysis of micrographs, which we obtain from microscope, optical, or EBSD. In case of this paper, we have EBSD. And on the right side, you can see the algorithm based on a genetic approach of optimization procedure. So, as I mentioned, the first step is analysis of images which we have from EBSD microscope. Here you can see the example of such micrograph, and you can see that we can easily divide this picture into three different phases. And what is the most important for us is bainite in the middle and martensite in the lower part of the slide. Because, as I mentioned previously, ferrite is treated as a solid matrix in the background. So what we will take in the further analysis is bainite and martensite phase. When we have these phases, we can calculate reference shape coefficients, and we can mesh and deform this virtual material to obtain its rheological properties. Here in the slide you can see examples of coefficients on the left side, and on the right side you can see how do we do virtual deformation of this material. In the upper part you can see the RVE, which is simulated, compressed by compression test, and during this, from these calculations, we obtain the reference of rheological material behavior, and then in the lower part you can see the deformation of SSRV, which should behave in fact the same. Then we can pass this reference information, the coefficients, shape coefficients, and meteorological data to optimization procedure as the reference values, and they are passed to objective function. The procedure is based on genetic algorithms, and the grains of SSRV are composed of NURBS functions. So what we have in our genetic algorithms, we have control points of such NURBS, and we have functions between NURBS which can be easily passed to modification, like for example mutation or crossing operation, and we can easily obtain new shapes of SSRV grains. Here in this slide we can see our results which we obtained for two variants which we performed on the basis of two sets of images. First variant with images of steel with 40% of bainite, 7% of martensite, and 53% of ferrite, and on the right side the second variant, quite similar because the soft phase ferrite is about 55%, but with different fraction of bainite, 30%, a little bit lower, and 15 of martensite. And you can see from A to C results for variant 1 and D to F results for variant 2. You can see the differences which with red martensite a little bit bigger. Okay, and these results were passed to compression test, 5% compression test, to obtain the stresses inside material phases, which will be passed further as a gradient properties, because on the basis of these stresses we calculate hardness of this material, which is in fact its property in microscale. And obtained results, as you can see, were passed to calculation based on sensitivity analysis. We thought that we can apply sensitivity analysis because sensitivity analysis methods and gradients can be analyzed very similarly. We can describe the gradients on the basis of ratio between model outputs and components of a position vector. And then we can apply Morris design method, which is very well known sensitivity analysis method, which results in one scalar value which will describe our properties, gradient properties in microstructure domain. Morris design has also its specific sampling method, which is used for generation of sampling points in microstructure. What we obtained here from A to C for variant 1 and from D to F similarly to upper results, we have results for variant 2. We can see that we have two values. The first one is μ, which is average gradient of stress for the whole domain, and μ 0.05, which is average gradient, stress gradient for only 5% of material with highest stresses. And what we can see here that even if μ is quite equal to each other, we obtain for μ 0.05 in the first case quite different values, which is not really satisfactory result. And in the second case, we have also differences for μ as well as for μ 0.05, which means that this idea is maybe not so good to describe the gradient of properties by one scalar value, because we obtain different values, but probably we do not prepare SSRVE in the right way, and maybe some other statistical measures should be introduced to objective function, and maybe we should repeat the optimization procedure once again. As I said, we obtained quite good convergence in this optimization procedure, because the value of objective function was near to zero, which means that shape coefficients as well as rheological character of the material was the same for SSRV and for original material, but we conclude that we should add some more information to objective function, and maybe we should change a little bit coefficients, characterization of shape coefficients, to obtain better unique results, which after application of Morris design will result in similar values of μ and μ 0.05. Thank you very much for your attention.
Thank you very much, Łukasz. Are there questions? Please drop them in the Q&A panel if you have questions. There's a question from Javier Dominguez. Is the speaker considering a numerical error criteria to say that the results are convincing?
Okay, can you hear me?
Yes.
Okay. Well, yes, we thought about it. In fact, it is the next step of our analysis, because now we wanted to be sure that application of this Morris design, the sensitivity method, sensitivity analysis method, would be good enough to characterize in unique way the gradients properties in the microstructure. But the problem is that we received quite different values, specifically for me 0.05 feature. And now we have to go back a little bit and we have to rethink the way we calculate SSRV to put new statistical measures probably in the objective function. And now we have the first step to improve the calculations of this gradient properties characterization, and then we will think about the error measures to characterize the differences between these predictions. I suppose that will be the way we will do now.
Okay, thank you. Are there further questions? I have a basic question. From these techniques, how much do you think you can improve the performance of the steels?
What of steels?
The performance. In other words, if you're trying to optimize for a particular measure of performance, how much do you think you can improve the performance of the steel?
Okay, but you mean the performance of steel or performance of calculations in optimization of processes?
I'm talking about of the actual steels themselves.
Steels themselves. Okay. Well, basically, we'll improve the properties. Yeah, the basic problem is in costs, as always, in heavy industry. And if you look back in the banana plot, you will see that we can obtain very good properties, but this will be very expensive because it will cost a lot of money because of microalloying elements. And what we want to obtain, we want to use the same steels as being used all the time from 90s, the first generation of advanced high strength steels, where the expenses were very low, but we want to obtain much better properties because of these gradients. And I suppose that that the improvement will be at least 20–30% in this case. On the properties, of course.
Yes. Okay. Thank you very much.
And the cost of production will be really low in comparison to advanced steels of the second generation, which can be very expensive because microalloying is on the level between 15 and even 40%. Yeah.
Okay, thank you very much. I don't see any further questions. So I'd like to thank Łukasz, and I would like to thank all of the speakers of this session for their presentations. We now break for lunch and start again in a little over 1 hour's time.
Hi, everybody. It's 2:30 here, so I guess we can start now. So I'd like to welcome you all to the first ever session of Unequivocal, so Uncertainty Quantification for Computational Models. And just as a reminder, if you have any questions, you can ask them down at the bottom. There's a special Q&A button down there. I guess you can always already do that when the speaker is talking. You can type your questions. And so the very first speaker is Nikishova from the University of Amsterdam. She's going to talk about doing inverse uncertainty quantification using Bayesian inference, where the expensive model is replaced by a Gaussian process surrogate. So Anna, if you're ready, it's all yours.
Good afternoon, everyone. My name is Nikishova. I'm from the Computational Science Lab at the University of Amsterdam. And today I would like to present you our work on inverse uncertainty quantification of a red blood cell model using a Gaussian process metamodel. This work was a master thesis project of Kevin De Vries. I and Ben Chaya were daily supervisors of Kevin, and Gabor Zavodsky and Alfons Hoekstra were the scientific advisors of this project. I will start my talk with the motivation of the study, then I will introduce you the model with which we worked. Then I will mention the methods for inverse uncertainty quantification that we applied. I will then present you our results and will finish with some conclusions. In the human body, blood performs crucial functions like delivering to the cells necessary substances like nutrients and oxygen and transporting metabolic waste products away from these cells. Sometimes, due to various pathological conditions, some properties of the red blood cells may change, and therefore it's very important to have a reliable model of red blood cells. Since a part of reliability is uncertainty quantification, in this study, our goal was to obtain uncertainty measurements of inputs of such a red blood cell model. We used a material model for red blood cell from the HemoCell library. HemoCell is a framework for simulating dense suspensions of deformable cells focusing on blood. In this framework, red blood cell membrane is simulated using discrete element method, blood plasma is modeled using lattice-Boltzmann method, and coupling is performed using the immersed boundary method. So our goal was to obtain uncertainty in the inputs for this red blood cell model. We considered three uncertain inputs. First is link force coefficient that defines tensile properties of the cell membrane, then bending force coefficient that defines response of the cell surface while undergoing bending, and viscosity ratio. Prior distributions for all these three inputs were taken as uniform distributions, and the limits of this distribution are shown in the table. In the experiment that we performed, a red blood cell was undergoing deformation due to shear, as it is shown in the left figure. The quantity of interest was elongation index, that is this ratio where A is a major axis, B is a minor axis of the deformed cell. On the right figure, there are measurements of elongation index for different shear stress. And we had two pairs of measurements, one for treated cell and another, treated cell is orange line and healthy cell is blue line. Therefore, our goal was to find two values for each of the inputs that would allow us first to obtain the HemoCell output that would fit blue line for healthy, with experiments for healthy cell, and then obtain values of the input that would allow us to obtain HemoCell results that would fit the orange line. So in inverse UQ, we start with some prior assumptions of uncertainty in the inputs. Then this uncertainty is propagated through the model and simulation results are collected. Additionally, we must have measurements of the quantity of interest. Then we employ this data in Bayesian analysis that allow us to correct our prior assumptions and receive posterior distributions of the uncertain inputs. In order to implement inverse uncertainty quantification, we used Bayesian annealed sequential importance sampling. This method is a combination of sequential importance sampling and transitional Markov chain Monte Carlo. In transitional Markov chain Monte Carlo, one uses the resampling method in order to update samples from one intermediate distribution to another. This method is shown to be efficient in terms of exploration of input space, and additionally, it is possible to implement the method in parallel. However, in these publications, authors show that the original transitional Markov chain Monte Carlo produced results with some bias, and in the basis method, authors propose to use additional parameter of Markov chain length that would remove the bias. Additionally, we applied sensitivity analysis in this study. Sensitivity analysis tells us how uncertainty in uncertain inputs affect the uncertainty in the output. In order to implement sensitivity analysis, we use Sobel sensitivity indices that are the ratio between partial variance and total variance of the model output. The results of sensitivity analysis were used in order to build the link between good identifiability of the input parameters and their Sobel sensitivity indices. Thus, in this publication, it was shown that if an input parameter has a low value of Sobel sensitivity indices, most likely it will be very difficult to obtain reliable measures of uncertainty in it in uncertainty quantification study with given quantity of interest. So our HemoCell model requires 1 hour to execute, and as I mentioned before, one Markov chain step would require several measures for different shear stress. Therefore, one step would require multiple hours, and for us, this would be computationally very expensive, and therefore we build a Gaussian process metamodel that produces an approximate results, however significantly faster. So we use Gaussian process regression with the following covariance function, where the first term is squared exponential kernel and the second term is noise level. For training, we use 500 samples, the same samples we used in sensitivity analysis, and we implemented the Gaussian process with using scikit-learn Python library. As a result, we obtained a surrogate that was producing us the results in microseconds. So first, I would like to present you the results of sensitivity analysis. So the results for link force coefficient show us sensitivity index very close to 1, to its maximum value. The results for bending force coefficients were very low and close to 0. And sensitivity analysis results for viscosity ratio shows us moderate values. From this, we concluded that both link force coefficients and viscosity ratio will be identified in this experiment, and bending force coefficient will be an unidentifiable parameter with the current quantity of interest. Now on the slide, there are our main results of inverse uncertainty quantification. First row are the results for healthy cell. Second row includes the result for treated cell. Each plot contains the results from experiment with HemoCell model. In this experiment, we used 1,000 samples, and the second distribution is the results from experiments with Gaussian process, where we used 10,000 samples. So for the healthy cell, we saw that both experiments produces a similar distribution for identifiable parameters. And from this, we conclude that the model is reliable. Probably we already, with 1,000 samples, achieved a good convergence in experiments with hemocell. However, for treated cells, these distributions are slightly different, and this could be due to error in Gaussian process approximation. However, later we will see that probably this is due to fact that 1,000 samples in the experiment for treated cell were not enough, and in the experiments with Gaussian process we reach a better convergence, and these results are more reliable. We did not draw any conclusions from the results for the bending force coefficient, since we were expecting that this parameter is non-identifiable in the current experiment. And the last plots are showing the distribution for modeling error. And since we saw that the peaks of these distributions are closer to a lower bound of the prior, we concluded that on average these models produce a correct result. Same results for inverse uncertainty quantification. Now in the table we show mean value, standard deviation, and maximum a posteriori. That is the mode of the posterior distribution. First, indeed, we receive quite significantly different results for healthy and treated cells, and also the results from hemocell and results from experiments with Gaussian process regressions are also quite different. Therefore, now I'm presenting you the results of forward uncertainty propagation where we run hemocell model with the values that we received from experiments with hemocell and from experiments with Gaussian process. So on the top graph, we are showing first measurements, black and gray dots, for healthy and for treated cell. Then we show the two lines that are results of the hemocell model when input values were taken from the experiments first with hemocell model and then with Gaussian process metamodel. And the violin plots are showing the distributions of the results from the hemocell. The second row includes the results with absolute error for healthy and for treated cell, where the difference is between the measurements and the hemocell results with inputs from the experiments with hemocell and then the results from experiments on inverse uncertainty quantification with Gaussian process. From here we see that for most values of shear stress, the Gaussian process experiment produces as a better values of uncertainty of uncertain inputs. However, we also see that the errors are comparable for both results with inputs from both experiments, and probably the experiment with hemocell already gave us a good enough approximation of the values of the model inputs. So we conclude that in the current experiment we obtained a good approximation of inputs of link force coefficient and viscosity ratio. On the contrary, for results for bending force coefficients are not reliable, and we must perform another inverse uncertainty quantification study with another quantity of interest. Also, we saw that Gaussian process regression results were producing us a better estimation of values of uncertain inputs, and we conclude that for this red blood cell model, such metamodel is a valid approach to improve efficiency of inverse uncertainty quantification. Thank you very much for your attention.
All right, thank you, Anna, for the nice talk. I think thus far we have one question in the Q&A. If anybody else has one too, please start typing. So Antonio Figueroa asks, can you use the length scales on the squared exponential kernel for sensitivity analysis?
Thank you very much for the question. I, with my co-authors, discussed a bit this question, and we're probably not sure with the answer. So maybe later we could also have a chat with Antonio and discuss this. But if I understood it correctly, it's about to also study sensitivity for the output of our surrogate to the value of the length scale. And here we are, at least we perform sensitivity analysis to the uncertain inputs to which measurements were not given precisely, not to the, let's say, model parameters, model settings. So probably the answer would be no, but if Antonio feels that this I understood wrongly his question, I will be happy to discuss it later.
Okay, thank you.
Wouter, actually, George wanted to ask a question, but he's one of the panelists, so he'll have to deliver it verbally.
Yes, thank you. I have one comment and one question. The comment is, I think that the reference for basis is not correct for the algorithm that you mentioned before. You don't have the slides, right? So we cannot see the...
Yeah. But actually, this is very important because we're now publishing this work. So if you could share with us correct, so we would check it. Thank you.
Yes, so I know that because it's from our group, so I think it's not the correct one.
Okay,
and the other question is, why did you use Gaussian processes and not any other surrogate model? And how did you validate the training of the Gaussian process?
Yeah, I think I would ask Kevin to answer this question because he's very kindly agreed to also participate in the question and answer session. Kevin, could you reply?
Yeah, so if I understood the question correctly, so first, why this specific metamodel? Well, that is mostly because it's a it's been quite a while, so yeah. In the first place, it's mostly because kriging is a rather popular method for these kinds of simulations to use as a metamodel. So I've originally used that as a first reference, or at least as a first model to try, and it already gave quite good results. So that's why I went through with that. The way we validated the training data was mostly because, or it was mostly by using the data from the sensitivity analysis, the output data from that, to use as a test set for the surrogate model.
Okay, Kevin, thank you. I guess we're right in time for the next speaker now. So the next one is Georgios Arampatzis from ETH, and I'm guessing you're going to present live, right? If I'm not mistaken. So yeah, he's going to talk about the very relevant topic of doing UQ for epidemic models.
Exactly. Give me a second to connect to share my iPad. Okay, so welcome to my presentation. Today I'm substituting for Petros Koumoutsakos, who due to an accident was not able to be here today. I'm going to present our results on uncertainty quantification for epidemic models. And this is a collaborative work with people from the Computational Science and Engineering Lab in ETH Zurich, under the supervision of Professor Petros Koumoutsakos and in collaboration with Professor Kostas Papadimitriou from University of Thessaly. In this work, we considered the well-known SIR model. In this model, the population is divided into 3 compartments: the susceptible, the infected, and the removed. Removed can be either recovered or dead. And then gamma is the rate at which the infected are being transformed into remove, and R0 is the probably at this time well-known parameter that shows the expected number of infections that can be directly generated by a single infected person, assuming that the whole population is susceptible. And the equations that describe the evolution of each of these 3 compartments is a set of ordinary differential equations described here. And in this work, in order to model interventions from the government, we consider the R0, the basic reproduction number before the interventions, and after the interventions, this number is multiplied by a number k that is less than 1. In general, what we want is R0 to be less than 1. In this case, the infection is under control. When R0 is more than 1, and the bigger it is, the more aggressive the infection is spreading. Between the 2 states, before and after the intervention, we consider a linear transition of the basic reproduction number R0. So in total, the parameters in the model is the R0 star, the reproduction number before the intervention, it's the intervention time, it's the reduction factor K, the duration of the transition delta, and the removal rate gamma. So our goal is to infer the posterior distribution of this parameter condition on observation. And for this, we consider publicly available data of daily infected for various countries. And we consider as a quantity of interest that model the daily infected from the model, and we denote it by F. And the model is connected to the data through a negative binomial distribution with mean, the model output, and dispersion coefficient R. In this study, we fixed 2 parameters, the duration of the transition and the removal rate, using values that we found in literature. And for the rest of the parameters, we considered uninformative priors, which we modeled with a uniform distribution with a relatively large interval. First, we validated our results. We sampled the posterior distribution of the parameters for data from Germany, and we compared our results with a paper that was recently published in Science using a model with 3 interventions, where in our case we used a single intervention. And we propagated the uncertainty from the parameters to quantities of interest, like the effective growth rate. And qualitatively, our results are in good agreement with results from this paper. The same qualitative good agreement we get for other quantities of interest, like the daily reported or the cumulative number of reported infected people. Next, we perform the same computations for all countries in Europe. And we can see, for example, that Switzerland and Netherlands, after the intervention, they managed to reduce the basic reproduction number to values well below 1, while Sweden, for example, even after the interventions, the basic reproduction number is reduced to a value close to 1, but not below 1. And this is also evident from the daily infected data that they still have an increasing trend, small one, but still increasing. Now on this slide, we present the basic reproduction number for all the countries in Europe before and after intervention. And you can see that most of the countries after the interventions, they managed to reduce the number to values below 1. And some of the countries like Armenia or Sweden or Bulgaria, they are close to 1, but still not below. The same result plotted on a map of Europe, you can see that before intervention, the whole map is red. It's that corresponds to values above 1, and after the interventions, almost all of the countries are less than 1 or even close to 1 for these countries. I will skip this slide and I'll go directly to the GUI. This publication that it's right now under review, you can find it. You can find the preprint here. Comes with an online graphics user interface that you can find here. And in this page, you can choose between countries in the world and choose some parameters like the percentage of the credible intervals or the number of samples. You can get samples from the posterior distribution, and the GUI automatically propagates the uncertainty in the parameters into quantities of interest and automatically computes credible intervals. And in order to do this, we used software that we have recently developed in our lab that it's called Corally. And now I will briefly talk about this software, which you can find a preprint here. Now, Corally is a high-performance framework for uncertainty quantification, optimization, and machine learning. And it can be seamlessly integrated with C++ or Python and precompiled models. It has an easy-to-learn interface. It is compatible with parallel computational models. It is adapted to extreme scale studies. It provides resilience in the sense that it can restore jobs in case of failure. And it's highly documented at open source. So Corally's interface is descriptive in the sense that the end user defines what wants to be solved and not how. So for example, in this simple Corally application, the user defines the type of the problem, that in this case, it's an optimization problem, and also the objective function that wants to be optimized. Next, the user defines the parameter space by giving names to the parameters and values, lower and upper values. And finally, the user defines the type of the solver that wants to be used. And finally, with a two-line command, two-line code, the user can run this Corally experiment. Now, with this approach, we require minimal programming knowledge from the user, and there is no need from the end user to know how Corally operates internally. In addition, we consider this as a modular approach because once the problem has been defined, and in this case it's simple, but it can be much more complicated, then the user can easily change the solver from the list of available solvers provided in Corally. Right now, Corally solves optimization, sampling, Bayesian inference problems, learning, reinforcement learning problems. For each one of these problem modules, there is a corresponding list of solvers. For example, for optimization, right now there's this list of optimizers that is provided by Corally. This list is under development. It's constantly populated with new solvers.
Hi, George. Just 5 more minutes.
Yep. The way Corally works, it's a generation-based engine. Once the experiment is defined by the user, then Corally takes over, checks for termination. Then the solver module generates samples that are passed to the problem module. The problem module pre-processes the samples and calls the computational model. The computational model does whatever computations. This is Corally agnostic, and then passes the results back to the problem, to Corally. And the problem module takes these results, post-process the results, sends it back to the solver. The solver updates the internal state and sends the results back to the engine. And then the engine stores the internal state of Corally and checks for termination. And this is one generation of Corally. Now, how Corally handles the execution of computational models, we provide 3 conduits. The simplest one is the sequential, which is suited for computational models that are computationally not expensive, simple functions that have seconds or milliseconds for execution time. The concurrent is designed for legacy code or precompiled applications, for example, LAMPS or MATLAB code or legacy Fortran code that can be used as black box. And the last one is the distributed, where the user has access to the computational model and can write an interface between the computational model and Corally. So for us, it's really important that we provide a solution for black box computational models, because there are many applications that are not open source, and it's very complicated to have an interface. And in this case, the black box, the user has to write a computational model that calls the black box, and the black box write the results in the file, and the results go back to the computational model. The computational model processes the results and then passes a simple vector back to Corally. Finally, there's the scheduling of multiple experiments. Instead of running when you want to run multiple experiments, instead of running the experiments sequentially one after the other, Corally provides the capability to run them all at the same time. And this way, the conduit orchestrates the execution such that there's never an idle worker. And in this case, for example, when we had to run an inference on 5 experiments on Bayesian inference on a red blood cell model for the uncertainty quantification of parameters of a red blood cell model, when we ran the experiment, the 5 experiments sequentially, we were able to go up to 74% average efficiency, while using the simultaneous execution of experiment, we were able to go up to almost 98% of accuracy.
Hi, George.
Finally,
1 more minute. Oh, and
yeah.
you're saying finally, so that's good.
Finally, I conclude, yes. Corally enforces fault tolerance because Corally saves its internal state at each generation. So in case there is a fatal failure, the user can easily restart the experiment at any generation, leading to minimal loss of information and waste, minimal waste of computational resources. So with this slide, I conclude. I presented results on uncertainty quantification of an epidemiology model, and especially on the basic reproduction number, and I briefly presented our new framework for uncertainty quantification, optimization, and machine learning. Thank you for your attention, and I'm open to questions.
Thank you. It was a very interesting talk. We have one question up to this point from Sergei Gologenko from University of Stuttgart. And he asks, may I ask you shortly to list the key benefits of Corrali compared to other HPC compliant frameworks like the Coda?
Like which one?
Dakota, the one from Sandia Labs.
Yes. So one thing that we tried to do, and I think that it's not provided by Dakota, is that we try to have a very easy user interface that can be used by someone with minimal knowledge of programming. Our interface is based on JSON, and I think that we try to do this as easy as possible for the user to write uncertainty quantification or optimization applications.
Okay, thank you.
You can find in our preprint, you can find maybe a more detailed list. In our preprint we have a comparison with almost all, at least to the best of our knowledge, softwares for uncertainty quantification, and we try to be as fair as possible to have a comparison between what we provide and what it is in the in other libraries.
Okay, thank you. If there are no other questions, I have one related to the epidemic model.
Mm-hmm.
So it's quite general. So you did inverse UQ on a SIR model. How do you see the role of this types of analysis in the current situation? How can it be of use?
How can it be of use?
Let's say you have to give advice to a government to implement kind of certain policies or not.
Right. Okay, we haven't been there. We didn't do that. We're not epidemiologists, and we didn't go there yet. But one thing that you can do is, for example, you can after inferring the parameters, you can find a best intervention that gives you the result that you want. You can, for example, you can infer all the parameters and leave the intervention time as a free parameter, and then tune this parameter and see what are the results in the spread of the disease, for example.
Okay, and you did a Bayesian inference on this, right? Were you able to get informed distributions on all parameters, or did some were not informative at all?
No, these are the distributions that we get. And yeah, exactly. This is the reason why we had to fix these two parameters, because these two parameters being free, they lead to an unidentifiable problem. And we followed the approach like in other publications where they have to fix these parameters. It's well known that R0 is linked to gamma, or there is a straightforward relationship, which sometimes is linear between these two. So one of the two should be fixed.
Okay. Well, thank you very much. And if there are no further questions, I think it's time for the next speaker.
Thank you.
And the next speaker is Jigar Parekh from the University of Groningen. And he actually did intrusive UQ. So you don't see that a lot, I guess, because it's quite a lot of work. But if you're doing CFD, I think he made a toolkit in OpenFOAM that you can use to do intrusive polynomial chaos. So Jigar, can start the video, I guess.
Hello everyone, my name is Jigar Parekh and I'm a PhD student at University of Groningen. Today I will be talking about intrusive polynomial chaos for CFD using OpenFOAM. First, I will introduce you to the topic of uncertainty quantification, followed by an overview of generalized polynomial chaos expansion. Then we will look into how intrusive polynomial chaos can be used for computational fluid dynamics, followed by some test cases including laminar and turbulent flows, and at the end some conclusions. Whenever we have to make high-impact decisions based on modeling and simulation predictions, it is important to evaluate the confidence. UQ can help to mathematically determine these confidence intervals. In CFD applications, UQ serves as a formal procedure to construct a composite error bar, including the discretization errors and the contributions due to the imprecise simulation inputs. There are lots of applications of UQ. I have listed 3 of them here. The first one is decision making. For example, the hurricane predictions with uncertain initial conditions as shown in the figure. The second is the validation. Here the example of uncertainties in reported measurements of speed of light is shown in the figure. One another major application of UQ is design and optimization. In the figure you can see the example of transonic wing shape optimization. The central idea of UQ involves 3 steps. The first step is data assimilation. Here we identify and characterize the sources of uncertainty. For example, uncertainty in physical model parameters or in initial or boundary conditions. The second step is uncertainty propagation. Here we develop a UQ solver accounting for the identified uncertainties in step 1. There are a lot of UQ approaches out there. One may make a use of the existing deterministic solver or even develop a surrogate model. The third step is the certification. Here we quantify the confidence interval, check for the validity of physical and mathematical models. For example, the quantities of interest may be mean, variance of velocity, etc. In CFD, there can be a lot of sources of uncertainty, as listed in this table. My work mostly concerns with uncertainty in physical modeling and boundary conditions. Monte Carlo method is one of the most commonly used methods for UQ analysis. In this method, we take a lot of samples from the distribution and run the deterministic solver for all these sample points in order to compute the mean and the variance of the solution. Monte Carlo method converges independently of the number of random variables. Also, it is non-intrusive, meaning that we did not have to make any changes to the deterministic solver. However, the standard Monte Carlo method requires a large number of samples, making it not suitable for the already expensive CFD simulations. As an alternative, we can use generalized polynomial chaos expansions. In generalized polynomial chaos expansion, the random variables are decomposed in terms of basis polynomials containing randomness and the unknown deterministic expansion coefficients as shown. Once these expansion coefficients are determined, the evaluation of mean and variance is straightforward. The random basis functions are orthogonal with respect to the probability density function of the input random variables. There are two different methods to determine the expansion coefficients. The first method is called the non-intrusive polynomial chaos. Here, we use the Galeckin projection on the polynomial basis to obtain the coefficients. The inner product here can be computed using some quadrature rule, where n is the number of the polynomial order and d is the number of random variables. This method is much cheaper than the Monte Carlo method and also embarrassingly parallel. However, it suffers from the curse of dimensionality because the number of quadrature points grows exponentially with the number of dimensions. The second method is the intrusive polynomial chaos method. Here, we insert the expansion directly into the original PDE and use the Galeckin projection on the polynomial basis to obtain a system of coupled PDEs. This method is cheaper than the non-intrusive variant and also more accurate. However, it also suffers from the curse of dimensionality. I will now discuss the use of intrusive polynomial chaos for CFD. We start with the Navier-Stokes equations for incompressible flow and expand the velocity and pressure in terms of polynomial basis. We then introduce these expansions into the governing equations. After taking Galeckin projection onto each polynomial, we obtain a system of equations for the evolution of the modes of velocity. Finally, using the orthogonality of polynomials, we obtain the following coupled system. This system is very much similar to the original set of PDEs. Note that Mij and Dik are constants and can be computed before solving these equations. Here is a representation of the evolution of velocity and pressure modes between two time steps. For every explicit iteration, the system of equations is decoupled by sequentially updating the velocity and pressure modes. This method is implemented in OpenFOAM using an existing deterministic solver for the incompressible Navier-Stokes. I will now discuss some test cases using this stochastic solver. The first test case is of Pursey flow. The Reynolds number is 100 and the kinematic viscosity has a normal distribution with coefficient of variation as 10%. Fifth order one-dimensional Hermite polynomials were used for the polynomial chaos expansion. These are the profiles of mean and standard deviation of velocity. The mean depicts a gradual transition in the flow along the channel length from a uniform inlet profile to a parabolic profile. The uncertainty in the velocity at inlet is 0, which is indeed the consequence of the deterministic boundary condition. In the developing region, a higher standard deviation is realized in the channel center, as well as in the boundary layer. The figure in the bottom left shows the axial profile for with the confidence in region of ±2 times standard deviation at different locations in the downstream direction. The uncertainties tend to 0 in a fully developed region, which is in accordance with the analytical solution, where the velocity is independent of viscosity. In the top two figures, we compare the velocity modes obtained from the intrusive method with those obtained from the non-intrusive variant. As evident, the results are very close to each other. The figure below shows a comparison between the estimated and analytical modes of pressure gradient normalized by mean pressure gradient along the center line. As you can see, after the recirculating regions near the channel inlet, these ratios gradually reach their constant values further downstream. Before moving on to the next example, let us understand what changes do we have to consider when we deal with turbulent flows. Here is an example of a stochastic Navier-Stokes equation with Smagorinsky-Elias model. In the Smagorinsky-Elias model, the effective viscosity is a sum of the kinematic viscosity and a turbulent viscosity. This results in a modified constant called dik effective, which is updated at every time step. The next test case is the turbulent channel flow. The shear Reynolds number is 395 and the Elias model parameter has a uniform distribution with a coefficient of variation as 15%. Third order one-dimensional Legendre polynomials were used for the polynomial chaos expansion. The results obtained are compared with the results from the non-intrusive method, DNS data, as well as the deterministic simulation. The top right plot is the normalized time average streamwise component of the velocity along with the mean and the confidence interval. The stochastic mean from the intrusive method is close to the DNS and the deterministic solution. In the figures below, the normalized square root of the second order velocity moments and the Reynolds shear stress are plotted together with their confidence regions. As evident, the stochastic mean of the stresses are close to the non-intrusive method and the deterministic solution. The slight deviation from the DNS can mainly be attributed to the use of relatively coarse mesh and the choice of Elias model. Both the intrusive and the non-intrusive methods predict high variance near the wall and almost zero uncertainty in the channel center. This is expected as the Smagorinsky model parameter Cs usually affects significantly near the wall as compared to the bulk region. The third test case is the flow over a cylinder at Reynolds number of 3900. Here we present two examples, one with an uncertain Elias model parameter and another with an uncertain inlet velocity. For both these examples, second order one-dimensional Legendre polynomials were used for the polynomial chaos expansion. These are the contour plots for the stochastic mean and standard deviation of the instantaneous and the time average velocity fields. The experimental values for the pressure coefficient is close to the stochastic mean and falls within the confidence interval of plus minus 2 times the standard deviations. From this study, we realize that the uncertainty in the Elias model parameter mostly affects the regions of high turbulence, that is, the wake region in this case, while the effect of uncertainty in the inlet velocity is reflected throughout the domain. The intrusive polynomial chaos method involves solving lesser number of equations as compared to its non-intrusive variant. This can be of great use when the simulation is computationally expensive. In the current work, a new stochastic solver was developed for the incompressible Navier-Stokes equation using an existing deterministic solver in OpenFOAM. The intrusive solver developed so far has been successfully tested with various standard CFD problems involving laminar and turbulent flows. These results are found close to the non-intrusive variant. The future work includes model form UQ analysis using random fields, for example, directly injecting randomness into the eddy viscosity or the Reynolds stress tensor. I will also look into different truncation techniques to avoid the curse of dimensionality for faster and cheaper UQ simulations. That concludes my talk. Thank you.
Thank you, Jigar, for the nice talk. We have two questions. First one is from Julian Kuhlemeiler. Can you explain how you decide on the number of basis functions used in the PCE a priori? Would it be possible to change the number of basis functions during computation?
I cannot hear you, Wouter.
Wait,
can you repeat?
Can you hear me now?
Yeah.
Hello? So you can also read if you go to the Q&A. So Julian asked if you can change the number of basis functions adaptively in a PCE.
Okay, so do you mean as the simulation is already running?
I would assume, yeah.
Okay.
Let's say you
as of now, no, I did not use that right now, but I can do that once I have a something like a API between my Python script and the OpenFOAM. Because right now I'm using ChaosPy, which is in Python, and then I just calculate the constants, which are the inner products of the polynomials beforehand, and just use them as the constants in the OpenFOAM simulation. So right now I'm not updating those constants at every time step, but I think I can do that in future once I am dealing with the random fields.
Okay, thank you.
Yeah.
The second question is from Federico. He says, thanks for the nice talk. May I ask if the method can be applied easily to other OpenFOAM solvers?
So this method is applied right now with the OpenFOAM solver called PimpleFOAM, which is, I think, one of the most widely used solvers in OpenFOAM. But if you just look through the code, you can easily see that you can actually translate my code to any other solvers like multiphase solver like EulerFOAM or something else. So it's possible to like understand my code and develop it for some other solver as well.
Yeah, because if I understand correctly, you don't have to actually recode very much, right?
No.
Even though it's intrusive.
Yeah, so that is what I wanted to do at the first place, because the intrusive method, as everyone knows, that you have to make a lot of changes in the solver. But if you're using OpenFOAM, so the good part about OpenFOAM is that at the top level code, you have access to Laplacian or other kind of tensor functions. And from there itself, you can just code your expanded PDEs directly at the top level of the code. So you don't have to go into the libraries and make changes, but only at the top level.
That was quite nice. Thanks. I think it is time for the next speaker. And that would be Philipp Maybank. And he's going to talk about doing MCMC for Bayesian UQ from time series data. He's from the numerical algorithms group, and I think he's going to talk about applying these types of methods to computational neuroscience.
This talk is aimed at C++ developers who have their own code base for a computational model and who need to do Bayesian uncertainty quantification.
Yeah, we are.
So a typical workflow, if you have a computational model that you want to use to make predictions or model future scenarios, is first to develop the model and then to calibrate that model to some data, perhaps using optimization to find the best fit parameters. And then to start doing uncertainty quantification, you might define ranges for each input parameter and then search for best case or worst case scenarios within those ranges. So to take an example that's dominated the news for the last few months is COVID-19, which is an area where computational models are used to predict future infection rates. Those models are calibrated to data, and reasonable worst case scenarios are produced by defining ranges for each of the input parameters and then finding the most extreme behavior within those ranges. So Bayesian uncertainty quantification is kind of useful as a next step for defining what the likelihood of those scenarios are. So using Bayesian methods, you can say how likely the reasonable worst case scenario is, for example, COVID-19. So I'm going to jump over to my slides now after that general introduction. So I work for the Numerical Algorithms Group, which is a company based in Oxford, probably best known for the NAG library. We have a lot of Fortran expertise, and I joined about 2 years ago after I finished my PhD in computational statistics. So actually, before I joined NAG, during my PhD, I became interested in algorithmic differentiation because it turns out it's a very useful tool for doing Bayesian inference efficiently. And NAG is helps to develop one of the leading AD tools, which is DCO C++. And that has been used in a wide range of settings outside of Bayesian inference, so for climate models, fluid dynamics for cars, and for risk management in finance. So I'd just like to do my acknowledgements now. This presentation is based on a paper that was accepted for ICCS, so I just want to thank my co-authors, especially Patrick Peltzer, who did a lot of coding and benchmarking, and also to Yui Naumann and Ingo Boyak. I also want to thank the STAN community. So STAN is a piece of software for Bayesian inference. And they have a very active user community. So this presentation is actually a development of a presentation I gave last year at the sort of STAN user conference. And I also want to thank the ICCS chairs and reviewers. It's been a very unusual year, and I just want to thank them for organising this online event, and I really value the opportunity to present this work. So what is Bayesian uncertainty quantification? So one level, it's very simple. It's just an application of Bayes' rule. If you want to know the probability of model parameters given data, then that's proportional to the probability of the data conditional on the model parameters times the prior probability of the parameters. So the setting where I've mainly worked is mechanistic models, where non-Bayesian methods can typically only give you a point estimate of the most likely parameters. So Bayesian methods give you a lot more information about what the probable ranges of parameters are that's consistent with your data. And that's useful for making probabilistic predictions, for example, in expected ranges. So in this presentation, I'll just be using a very simple model as an example to illustrate the ideas, and that's the noise-driven harmonic oscillator. So this has some similarities with models that are used in computational neuroscience, in that it's a linear state space model. It has noisy input, and we observe some component of the system at discrete time points with some observation noise. And the inference problem that we're trying to solve is that we want to know the posterior distribution for the omega 0 and zeta parameters. So they're the parameters that drive the dynamical system. And the method that we're going to use as the likelihood is called the Whittle likelihood. So that defines a likelihood in the frequency domain, and it needs the spectral density to be computed. So it's kind of a non-trivial numerics in that you need to find the eigenvalues of the system and use complex arithmetic. So there are many other methods for time series analysis, such as Kalman filters and so on. And the software that I'm going to talk about, it would be possible to generalize it to those other methods as well. So once you've defined a likelihood, then you can plug that into the Markov chain Monte Carlo to sample from the posterior. MCMC is used when you cannot get a closed form solution to the posterior. The simplified manifold Mahler is an MCMC algorithm that's relatively simple and tends to work without much tuning, and also with approximate derivatives. The other MCMC algorithm I'll be talking about is Stan's one, which is a variant of Hamiltonian Monte Carlo. So people often ask about how do you know whether MCMCs converged. So the measure that I like to use is called the effective sample size, or NF. And I'll give an example of that later. Another useful test for convergence is whether you can recover known parameters from synthetic data. So the Stan software has been developed in the last 10 years, and it's named after a guy called Stanislav Ulam, who was a pioneer in Monte Carlo methods. And so Stan users will typically write their statistical models in a .stan file, and then the Stan compiler generates C++ code from the .stan file. And then the C++ is compiled, and the executable will run the Markov chain Monte Carlo sampling. And so under the hood, Stan has an AD tool within the Stan math library, and that computes derivatives efficiently and accurately, which is needed for Hamiltonian Monte Carlo. So as well as using the Stan API, you can write models in C++ and use the Stan MCMC sampler to do inference for those models as well. So in terms of derivative computation, there are several different options. I've already mentioned the AD tool and the Stan math library. There's also finite differences, which typically requires a lot less user effort. Certainly if your starting point is a C++ code, it tends to be fast for a small number of input variables. It doesn't really scale well. And then there's NAG's DCO C++ tool, which is developed along it's based on similar ideas to the Stan AD tool. So it scales very well with a number of input variables. But it's also possible to do performance optimization in a way that doesn't require a huge amount of effort on the part of the user. So here are just some results for running the MCMC sampler on some synthetic data for the harmonic oscillator. In this first column, we have the actual parameters that were used to generate the data. And then the following three columns are kind of a summary of the posterior distribution. So you can see credible intervals for each parameter. And the true parameters are within those credible intervals. On the right, I've plotted the spectral density, so you can get a credible range for the spectral density. And here I'm comparing it with a non-parametric estimate of the spectral density, which is the Welch method. So this is another useful check that estimates that came out of the Bayesian inference using the model are consistent with estimates of the spectral density that don't depend on the model at all. So in the ICCS paper, I benchmarked two different MCMC samplers, the SM Mahler and the NUTS, which is implemented in Stan, and also compared finite differences and AD implementations. So I found that Stan's NUTS sampler did accelerate the MCMC sampling, but also the performance was kind of adequate with SM Mahler with finite differences. So for simple models, such as the noise-driven harmonic oscillator, you can sort of get away with the simple MCMC algorithm and the very approximate derivatives. But as the model complexity increases, it's more likely that you'll need to use the derivatives calculated using AD and the NUTS sampler. So the software that I use to generate those results is available on GitHub, so you can download that, and it's got a BSD license. And the target for that software, as I said at the beginning of the presentation, is C++ developers who have an existing code base and a statistical model for their data. So in terms of the specific model that I talked about in this presentation, that's a stochastic differential equation with a stable fixed point. So models that fall within that kind of base class can be implemented within the software quite easily. But also other models that are nothing to do with time series analysis or spectral analysis can be used in the software by deriving from the computation base class. In terms of which methods to use, the SM-Mahler is sort of the first thing I'd recommend trying, because it would be quite easy to get started. And then stands and UTS can be used if acceleration is needed, and the AD tools also provide a lot of scope for acceleration. Yeah, in terms of what NAG can do, if you follow these steps, at some point you might find that it becomes challenging to do the performance optimization that you need to get the derivatives efficiently. So this is something where NAG can provide training or support. So yeah, thank you for listening, and any questions?
Thank you, Philip. Thus far, there are no questions. If you have, please type them. In the meantime, I have one question. So a lot of the other methods like polynomial chaos, they clearly have a curse of dimensionality. And I think, correct me if I'm wrong, but MCMC does not really have it. But in practice, I still notice a difference between calibrating, let's say, 2 parameters, calibrating 10 parameters. So can you say something about the scaling of these methods?
So it's true that plain Monte Carlo, sorry, I'm getting quite an echo here. Could you mute, Wouter?
Sorry.
So plain Monte Carlo scales independently of the dimension, but there might be quite a large constant there. In terms of Markov chain Monte Carlo methods, there's sort of theoretical results in the literature where you find that there is a dependence on the problem dimension. So the effective sample size will be less for high dimensional models. I think the interesting point to make in this context is that the MCMC samplers that I've used that use the gradient and the second derivatives, those samplers have better convergence properties. So they scale better with the number of input variables than MCMC methods that don't make any use of derivatives or gradients.
Okay, so is that because you take account for any correlation in the parameters?
Yeah, both the SM-Mahler and the NUTS samplers definitely take account of the correlation structure in the parameters. So it's a bit like you're doing a rotation. So that's part of it. But you can do that without derivatives if you just run an optimization solver to get to the optimal parameters in your model, then evaluate the Hessian at the optimum, then you can design a covariance matrix for your MCMC sampler that will take account of correlations. So that will improve convergence. But actually the results about the dimension are sort of on top of that. So as well as taking account of correlation, the sort of theoretical reasons why using the gradients, it sort of reduces the random walk behavior, and it does converge faster even compared to derivative-free methods that take account of the correlation structure.
Okay, thank you. We have one question from Jurk Unger, and he asks, how would you consider model bias and correlations in the noise term in your Bayesian identification?
Model bias and correlations in the noise term. If there is not, I'm just reading the rest of the question. If there is not model parameter configuration that actually represents your data. So I guess this is sort of getting at the point where the example that I gave in the presentation was on synthetic data. Sorry, can you mute again, Wouter? I'm getting the echo. So yeah, model bias, I don't really have any suggestions for that, but I think it is important to take account of the fact that when you specify a likelihood for your model in a way, that is a prior belief that you're inserting, as well as your prior beliefs about the input variables. I think correlations in the noise term, you know, a Bayesian framework is very flexible, so you can add all sorts of bells and whistles to models to account for correlation structures. And I think that in general, Bayesian inference generalizes quite well in that sense. It's not something that I've specifically explored in my work.
Okay, thank you very much. If there are no further questions, I think we can move on to the final speaker of this session. And that is Evan Baker from the University of Exeter. He's going to be talking about future-proofing a building design using history matching inspired level set techniques. So that is about making buildings more energy efficient, I think. And so we can start the video.
Hi, I'm Evan, and I'm from Exeter in the UK, and I'm going to talk about future-proofing building design, blah, 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 blah. I'll just get stuck straight in to try and explain what this really long title means. So most of us live in a building, and we probably work in a building, although these are probably the same building at the moment. And buildings cost money to run. What I specifically mean by that is that heating costs exist. In winter, it costs money to heat, and that depends on how well designed your building is. Buildings also get too hot. Hopefully your home doesn't, but I know people whose offices gets too hot in summer, and that's bad. These are both bad. So what we want is a building that uses less than 15 kilowatt hours per meter squared, which is already a requirement for very high standard houses. And we also want a less than 1% chance of overheating in summer. And these two goals often go against each other. We want the building to be hot in winter and cold in summer. So what we can do is we can simulate many different buildings and find the good ones. So Energy Plus is a simulator for simulating buildings, and here is an example building I've designed or taken the design for. And Energy Plus requires a few inputs here, say the window size and the thickness of the wall insulation, and so on. And these little inputs are the things we're going to change to try and make this building be up to scratch. So rather than simulate hundreds and hundreds and hundreds of times to try and find all the good possible designs, we can build emulators. I assume I don't need to talk much about this, but very quickly, rather than simulating loads of times, we simulate a few times, and then we interpolate and discover what all the other buildings do as well. What's interesting about Energy Plus is that our version of Energy Plus is noisy. So usually Energy Plus requires you give it the building, but you also need to give it the weather. And in practice, people tend to just give it fixed weather. There'll be a fixed time series of hot in summer, cold in winter, rainy whenever, set days. But this is kind of silly. Weather is clearly not known. We don't know what the weather's going to be. To me, it's clearly random. I at least don't know what it's going to be. It's random to me. So we link up Energy Plus with a weather generator, specifically UKCP09, which is an old weather generator, but it's one for the future. It's conditional like climate change effects. And so what we're doing is we're looking for a building that will be good in the future, not just today. And every time we run Energy Plus, we get a different weather file, and so Energy Plus is now stochastic, it's now noisy. So every great presentation needs a cute picture, and this is one of my birds, and I think he's really cute, so I've included him. He's not relevant, he's just there to look cute. This slide is actually about what emulators we build. So one of our outputs we're interested in is the energy usage. We want to keep that low. We want the cost of the building to be low. And this is continuous, but also noisy. So we model this with a Gaussian process for the mean, but also a Gaussian process for the variance, the intrinsic simulator variance caused by the random weather. And so what this means is that we allow the mean to be a flexible shape that changes, but we also allow the variance to be a flexible shape that changes. So a building that has low wall insulation, say, can have a different mean and also a different variance to a building that has a high wall insulation. This emulator is quite a popular method for stochastic computer models. We didn't come up with it, but it's quite a good method. The other output we're interested in is the overheating risk. So overheating for us is binary, either a building overheats or it doesn't. And we're interested in the probability of it overheating, so we want a probabilistic classifier. We also want it to be flexible and it to include uncertainty estimates. I think most people, when you say classifier, think of logistic regression. You can use logistic regression here, but we've opted for a Gaussian process classifier, where you stick a GP on that probability, and then you stick a Bernoulli likelihood on top of it. But whatever method you want to use is fine. These are just the emulators we used. So as the last little bit of background, history matching is a method for calibrating computer models. So if you have some real-world observations and you want to pin down what the parameters were that caused those observations, history matching is one method for doing that. It seems to be only a method in the UK, hence why I included a little slide here about it. But basically it's a design scheme and analysis tool wrapped up in one. You figure out what parameters are possible or non-implausible at the same time as allowing yourself, figuring out what future simulations would be good. And yeah, so it's based on this idea of implausibility. We're not trying to find probable answers, we're trying to reject the implausible answers instead. And the history matching has already been adapted to optimization problems, so it seems sensible to adapt it to level set estimation, which is what we're doing. So history matching level set estimation. If you're familiar with history matching, this should look like a really familiar equation. If not, it's a really simple one. Basically, L is our threshold, our goal. So for energy usage, that's 15 kilowatt hours per meter squared. This term here is the expectation of the emulator for a specific building X. So maybe for a specific building design, the emulator thinks it'll be 17 energy usage. So then the difference between that and your threshold is 2. And then that difference is weighted by the uncertainty you have, by the standard deviation of your emulator. So in that case, the implausibility I would be 2 for a building that had 17 energy usage. And the more implausible a building is, the bigger this I is, the less likely that building satisfies the criteria. It's just a weighted difference of what the emulator says and what you're aiming for. So 3 is often used as a conservative cutoff point in standard history matching for I, and that's what we use here. It's based on Puckelsheim's 3 sigma rule, but it's basically just saying any I more than 3 is a really bad building. So to try and make things a bit more clear, I have this pretend drawn up picture that I think I made in Paint. And basically, say x1 is one input, say wall insulation thickness, and x2 is size of windows. This black line here is where the emulator thinks the line is for when you're at 15 kilowatt hours per meter squared. That's what it thinks it is. And so there's a trade-off, right? So big X1 and small X2 is okay, but vice versa is. This red region is when the implausibility is bigger than 3. It's when we're really confident this building is bad. These buildings, any building up in this red region, are terrible. And so we rule them out. They're not good. The opposite is this blue region. These are places where the implausibility is really small. And so we rule these in. These are buildings that are really good. We're certain they're good. We're really confident they're good. This white region in between is where we're not really so sure. The buildings up here are probably not good enough, and buildings down here are probably good enough, but we don't know with enough confidence to say for certain. So any buildings in this white region are candidates for future simulations. If we can simulate more from Energy Plus, we should do so in this region. So on this slide, I have a really complicated looking plot. I'll try and run us through it, but these are the results now. After obtaining an initial wave, an initial set of simulations and fitting the emulators, this is what we end up with. So x1 to x8, these are our inputs. Just looking at the diagonal now, say this one here for x3, this histogram here says big values of x3 are good buildings that probably meet the requirement or haven't yet been ruled out from meeting the requirement. But then we see buildings that have a small x3, they're clearly no good. We don't like those buildings. We can't build those buildings. And you can see for the different inputs have different importance, right? So x4 has a similar relationship but flipped. Small x4 is good, big x4 bad. But then something like x1 or x6 are just, they don't do much. They do something, but nothing much. Then the off diagonals, these colorful rainbow plots, which should not be rainbowy, but this is kind of the standard colors for history matching. These show the interactions, how they try their best to show the two-dimensional interactions. The actual shape of what buildings are okay is some weird 8-dimensional shape, and this is one way of trying to present it. So if we look at x4 and x5, you can see there's a trade-off going. You can get away with a big x4 if you also have a big x5. And then there's this diagonal line where red is no good, green is not bad. The green is essentially the white from the previous slide. And so you can see that there's different shapes that are going on. And you could spend ages looking at these, but more interestingly, I think, is that we can just look at how many, if we get from a whole set of candidate buildings, what percentage have been rejected immediately in the first round of simulations. And in the first round of simulations, we can immediately reject 83% of buildings, of possible building designs. So we're left with only 17% that are either in the white region or the blue from the previous slide. This tiny number, this 0.0084%, is the percentage of building designs where we think we meet the criteria. Our best guess is that we meet the criteria. And we essentially think at the end of the first simulations, our emulators think essentially no buildings are good enough. Some are, but very few. But that's okay. We can run more simulations in the not ruled out yet space for not ruled out yet buildings, and we can improve these emulators. So that's what we do. This is wave 2. We've added some more simulations. The immediate change here is that we have these blue bits on these colorful rainbow plots. Blue, as you can see from this scale, is where you're approaching the ruled in space. We're not yet ruling in buildings, but these are buildings that are probably good. We're starting to get to good buildings. The diagonals have changed slightly, and the shapes of everything has changed a little bit, but this is the most obvious change, is after adding some more simulations, we're now gaining confidence. So after that, we have rejected another 10% of buildings roughly. It's not quite as impressive as the first wave, but it's still quite an improvement. And we've now got about 1.49% of possible buildings. So nothing, but not loads, of buildings are probably meeting the requirement now. This is great. We've got some buildings. We've found some buildings. We can repeat the whole procedure again. And so this is another wave of simulations. and not much changes. There's been some minor changes, but nothing huge. So we've rejected like another 1% of buildings as being obviously wrong. We've obtained a small percent, a very tiny amount of buildings that are probably good. So yeah, so this is kind of where we stop now. We've not made much improvement, and it does cost time and effort to run Energy Plus, so let's not bother anymore. From this point, we can then look at this 1.53% and say these are buildings where we think we meet the criteria. We can hand this to a practitioner. We have emulators, so we can provide the probability they meet the criteria. We can say, this building has a 90% chance of meeting the criteria. This one has a 55% chance, and the practitioner can use that to design their building, because maybe they want to accept the reduced chance of meeting the criteria, but they want big windows, right? Like, energy usage and overheating risk is not the only things. There's many things that come into it. Art style is one of them, right? And practicality is another. But we've done our job as statisticians, basically. So that all works quite well. I'm quite happy with how that all went out. What's next? If we were going to continue this sort of stuff, 1% of chance of overheating is what we targeted before, but that's not fantastic. If I said your house has a 1 in 100 chance of overheating, it's quite good, but we often talk about things like 1 in 1,000 or 1 in 10,000, right? Can we find these mythical 1 in 1,000, 1 in 10,000 buildings that meet these criteria? It's a really small chunk of the input space that would be, if that does exist. It'd be really hard. But is that something we can do? Is that something we want to do? Compared to other methods, there are other methods for level set estimation. We didn't come up with the idea of level set estimation, so how do they all compare? This is really true for calibration, more so than level set estimation. History matching and other methods for calibration exist, are in widespread use. People need to compare these. We'll compare them if no one else will. And we want this to be useful for practitioners. So having some code that does it all automatically for them, does all the checks, make sure the emulators fit well, would be really useful and provides like nice, presentable information. So that would be something that would be good to actually obtain. But yeah, thank you for listening and have a good day.
All right, thank you, Evan, for the nice talk. If anybody has a question, you can start typing it now. In the meantime, you made an emulator, a building emulator. I was just wondering, if you start drawing random buildings, is it possible to get like some building that's good for energy efficiency, but which breaks some other constraints, which would not be possible to build?
Wait, do you mean like it's good for energy usage but bad for overheating?
Yeah, or it's good for both, but it would fall apart if you actually build it. Yeah.
I see. Yeah. Possibly, I'm not sure. The simulator does fail at some points, and the intervals we selected were within the intervals of preventing failing. Possibly, okay. I'm not sure.
Yes, I was wondering about this too. So Jörg Unger also asks how you generate the second wave in the third. What changes from these waves?
So in the initial wave, we just had a big candidate set of like 1 million buildings, and then we ruled out, I can't remember what the numbers I said in the video, but something like 80% of buildings. That meant we still had 20% of those buildings lying around. I just randomly picked from those buildings to then resimulate. So only the good buildings have been resimulated. There are some techniques out there that if that million, if you do enough waves, you eventually run out of medium buildings to run, and you can resample some new buildings. But we never got to that point with just 3 waves. So we just like random. Yeah, sorry. Yeah.
Is it like a genetic algorithm, something where you kill off the weak and then only start with the strong, or?
I guess it's a lot less clever than that, though. It's just a sort of a rejection-y thing in between each wave.
Yeah, and wait, there's another question from Jörg. Resampling means a Markov chain starting from the previous good ones?
No, so so in wave 1, we build an emulator on So imagine it was just one-dimensional and it was just insulation. So we had small insulation, medium insulation, big insulation as our, that we'd run simulations. And then in the first wave, we'd rule out big insulation. We know big insulation is bad. But we've also checked, oh, we know that small and medium insulation is good or not bad. So then we just run Energy Plus for the small and medium ones. We would just literally have a matrix of buildings that we could run the simulator from, and we check the goodness of each one and then randomly pick some ones to simulate in the next wave. It's not enough simulations for something like Markov chain, Monte Carlo, or anything like that.
Okay. And could you tell me more about the weather model you coupled? Is that like a model, a computational model, or is it just data, or what is that?
Yeah, it's a model. It's quite an old model now, but it is a weather generator that will simulate random weather, and each time it's the output of a previous model that we're plugging into the Energy Plus model.
And then you simulate for a year or longer?
Yeah, we just simulate a single year. We're aiming for like the year 2080 or something that we're sort of treating.
Okay.
But then obviously the average energy usage for a year is then you know, over a period of time is still the average energy usage for a year. Right?
Yeah. So you target 2080, and so how do you estimate the weather then? You just add 2 degrees, or?
This specific weather generator spits out the weather for the year 2080.
Okay.
It doesn't necessarily have to be the future, right? Because you could just do this for today, but.
Okay, I see. Yeah. Oh, all right. Thank you. And I guess if there are no further questions, we can go for coffee.
I believe that we are ready to start the second session of the first edition of the unequivocal workshop on uncertainty quantification for computational models. I would like to remind that everyone is welcome to use the Q&A function and ask the questions during the talk and right after the talk. And we open the session with a talk by Professor Jan Minczuk from Polish Academy of Science and Warsaw University of Technology.
Good afternoon. I will speak about novel ways of conditional independence testing and their applications. So my main objective would be to construct a measure of conditional dependence and use it for a testing of the following null hypothesis. So I will be concerned with testing that X and Y are conditionally independent given a bold Z. Z usually will be a vector of the random variables. So all this will be done for discrete random variables. And such a problem is very frequently encountered in machine learning. So let me mention feature selection, determination of Markov blankets, and structure learning. To set the scene, here Y would be usually target variable, bold Z, those would be chosen predictors, and X is a candidate variable and would like to test whether it is worthwhile to add X to Z. And usually we are using to the same conditional mutual information, which will be defined in a moment. But the problem with conditional mutual information is that when the dimensionality of Z becomes large and the number of observations per cell of Z is becoming smaller, so the test based on conditional mutual information lacks power, which results, for example, in small recall of reconstructed Markov blankets. So we'll look at the alternatives to replace conditional mutual information, and that will be, in fact, concordant with the subject of this session. So let me recall very quickly main concepts from information theory. So here you have the definition of mutual information, and I will be mostly concerned with conditional mutual information, CMI, which is conditional, which is information, mutual information calculated for conditional distribution and averaged over distribution of the conditioning variable. So this popular measure of conditional dependence in view of the following property. And I will also need the definition of interaction information, which is defined as a difference between mutual influence of X and Z on Y minus individual influences of X on Y and Z and Y. And this definition has its multivariate analogs, which are used in the following important expansion, which is called Möbius expansion, which shows that conditional mutual information can be decomposed into unconditional one and the sum on information interactions between X and Y and the subsets of Z. Okay, so here the summation is over all subsets, non-void subsets of coordinates of Z. So the main idea here, which is known, is simply to truncate this sum to obtain different measures of dependence. Let me show you two such examples. So the first is called CIFE, so this conditional info max feature extraction measure, which simply truncates this sum only for and also retains only the terms of the first order. So we have interaction information between X and Y and ZK, and also we have JMI, which is the analog of Z, but of this, but with this sum dynamited by dividing the sum over the number of elements in the sum. So we're dividing this over P. And there are many other measures. And what is important, it was in fact important observation of Brown and his collaborators, that all those measures can be written down using this general formula when we look at the measures having two parameters, beta and gamma, and the measure is defined as unconditional mutual information minus beta, the sum of those unconditional information between X and elements of Z, coordinates of Z, plus gamma and those conditional informations. So this, of course, depends on beta and gamma. And for example, we will obtain CIFE for beta gamma equal to 1 and JMI for beta gamma equal 1 over P. And of course, this can be easily estimated from data by plugging in fractions instead of probabilities. So now, in order to use such measure for testing, we need to look at the asymptotic distributions of this measure, and it is done in the following result, which looks pretty complicated, but let me explain the main idea here. So the result says that, in fact, what we can expect when looking at distributions of this guy is simply that we can expect either normal distribution or the distribution of quadratic form. And when the switch occurs, so simply the switch occurs when this variance is equal to 0. So in this case, this normal distribution degenerates, so it is equal to 0. And in this case, distribution of quadratic form takes over from the normal distribution. So the first important message is that simply in this case, we have dichotomy of asymptotic distribution, and also the norming constants here are different. So here we have square root of n, and here we have n. Here, this variance, as we will see in a moment, can be easily estimated from the sample. So now the question is, okay, so how this result can be used for inference? So let's look at the special case of GMI. So JMI. So we focus on JMI is a sequel. So here we have alternative definition of JMI. So here we have the formula for the variance of JMI, which follows from the theorem. And once again, okay, so what happens is that if this variance is not equal to 0, so we have normal distribution, and if the variance is equal to 0, so also it is known that in this case JMI is equal to 0, and we have convergence to distribution of quadratic form. So distribution of quadratic form can be, for example, chi-square or scaled chi-square, or even more complicated, but the representatives of this family is chi-square and scaled chi-square. So how can this be used, and what are the consequences of this result? So if I look at the variance, asymptotic variance of JMI hat, so it turns out that in fact this can be very easily estimated from one sample, and that's very important, because it means that on the basis of one sample, I can estimate the variance of asymptotic distribution. How this can be done? If you look at this, so if I look at this formula, and if I plug in fractions instead of probabilities, so this will be calculated for one observation. And if I calculate the variance of those guys, so this will be a reasonable estimator of my asymptotic variance. So that's one observation. The second one is will come in a moment, but let me show you what are the main problem here. The main problem here that if I look at my objective, and my objective is testing such null hypothesis, so in this case, I still can have both these asymptotic distributions. So that's the main problem here. And this stems from the fact that if I look at this formula, so I can, in this case, I can have either asymptotic independence given zk, individual random variables, or those two guys not necessarily are conditional independence given zk. So this conditional independence does not imply this conditional independence. So under null hypothesis, I can still have both distributions. So the question is not whether to switch or not to switch, but the question is how to switch. And the switching is based on the following observation, that if this variance tends to 0, so in this case, we can have only the second part of the dichotomy. So the whole procedure will be based on checking whether the variance tends to 0 or not. So how it is done? So let's first check whether it is a reasonable idea. So we have looked at two models. They will be defined in a moment. So the first one, the asymptotic variance is greater than 0, is larger than 0. In the second case, it is equal to 0. So this corresponds to the first case, and you see that those variances behave reasonably stably. They are almost constant, at least in the mean. And if I look at the second case, when the variance is equal to 0, so if I look at the asymptotic empirical variances, so those empirical variances tend to 0 very quickly. So what is the outline of the algorithm? So simply the outline is to use permuted data of x. So we permute x on each strata of z. So in this case, we obtain the samples which satisfy null hypothesis. And for those samples, I calculate the estimator of the variance. So for each permutated sample, I have the estimator of the variance. And I am doing this for capital B samples of size n, and also I'm doing the same thing for samples of size n2, and I compare those variances using t-test. And if I reject the hypothesis that those two variances are equal, so I use chi-square distribution or scaled chi-square distribution as my reference distribution, and in the second case, when I do not reject, I use normal normal distribution. So I will consider 4 tests. Those 2 are new proposals. So here we are using switch between normal and chi-square, and here we are using switch between normal and scaled chi-square, and we are comparing those 2 tests with classical test based on conditional mutual information and the chi-square reference distribution. And the second proposal, due to Samardinos and Burboudakis, so this test based on permutations, but those permutations are used only to calculate the estimator of the number of degrees of freedom. So let me show you the setup of numerical experiments. So here we have y, which is Bernoulli, and depending whether y is equal to 1 or 0, we have the vector of x1, xk simulated from normal distribution with mean 0 or normal with mean gamma, and sigma and gamma are used simply to add additional dependence between those x1, xk's. And here you have this important variable x11, which is simply conditionally independent of y given x1, and it is simply discretized and x1 random variable. And you have also a second model in which x11 is simply disconnected from those variables, so it is simply independent from those variables. So we have the following hypothesis. So here you have null hypothesis, and we have to control size, and also we look at those hypotheses to control power. What is important here is that for the model M1, the variance is equal to 0 for k equal to 1, and for k larger than 1, the variance is larger than 0. So here we should expect chi-square distribution as a reference distribution, and here we should expect normal. And in the second case, we should expect normal distribution chi-square distribution in all cases. So let's look whether the switch works, and it looks quite nicely. So here you have the result for k equal to 1 for the model M1. So we see that we choose here in almost 100% situations we choose chi-square distribution, and if I change to k equal to 2, so we are beginning to choose normal distribution. For the second case, we almost always choose chi-square distribution. So if I look at the size and the power of our proposal, so it seems that the size is quite nicely controlled by all those methods apart from CMI, which is simply too much liberal. So alpha is equal to 0.05 here. And what is the most important is the behavior of the power. So we see that for our proposals, the power drops to 0 with k, the number of elements in the conditioning set, much more slowly than for other proposals. And if I make the problem more difficult, if I add the dependence between x's, so still we have the advantage over those proposed tests. So the last thing I would like to show you is a small application to feature selection when we have several Bayesian networks and we would like to determine the Markov blanket for several values. And what happens here, so we are looking at GMI, CMI, and CMI SP, and it turns out that GMI it does not win in all cases, of course, but we have several cases in which its behavior is quite promising. So, for example, you look at the cancer, so we are getting the result much larger than for CMI with regard to F measure, and much better than for CMI. Also, the same happens for survey. Okay, so if one looks at the results more closely, so it happens that it is due to the larger recall and in most cases comparable precision. And now what we are working on is finessing of this method by proposing new estimators of parameters of reference distributions. So we have also some references. Thank you very much.
Thank you very much for your talk. In the meantime, I don't see any questions that arrived to Q&A. Maybe there's still a couple of minutes to receive a question, and in the meantime, I will ask my question. Could you please tell us some, give us some ideas about computational complexity of this conditional independent test, and maybe you could compare your approach with some alternative methods?
Okay, good evening, good afternoon. Okay, so when you compare the time complexity, so okay, so it is known that if you look at the first proposal, so
hi.
I'm sorry, so could I speak now or?
Sorry about that. It's the video auto played there. I was just loading up the next one. Apologies.
Sorry. Okay, so could I continue or should I stop?
Please continue.
Okay, so everything should be compared to the benchmark, which is asymptotic CMI test. Okay, and if I look at the first proposal, which was done by Tsamardinos and Bourboudakis, so because we need to generate permutation samples, so it is around, okay, so it depends on the number of permutations you would like to use, but you would like only to estimate the parameters. So in this case, for example, we are using 50 permutations, so of course, time complexity increases by 50. So the price you pay to avoid the asymptotic test. In our case, if you look at the outline of the algorithm, so you are in fact need twice that much permutation samples. You are doing this for sample n or for sample n over 2, so the time complexity is 2 times more than for permutation test of Tsamardinos and Bourboudakis. Okay, but judging from the power and results from the powers, it's worthwhile to do that. Okay.
Thank you very much. I don't see any more questions for Professor Milinchuk. So I think then we can move to the second talk by Wouter Edeling from the Centrum Wiskunde in Informatica in the Netherlands.
Hi, my name is Wouter Edeling. I am a postdoc at CWI, and today I will be talking about deriving reduced subgrid scale models. So this is joint work with Dan Conlin, and we are part of the VECMA project, which stands for Verified Exascale Computing for Multiscale Applications. And here our overall goal is to develop a UQ toolkit for these types of applications. In CWI, we are mainly concerned with geophysical flow problems in this context. So imagine you have some atmospheric flow model. So at the picture you can kind of see a cloud deck with underneath Holland. And so if you have an atmospheric model for these types of problems, your individual grid columns, which are blue in this picture here, they tend to be of the size of, let's say, 50 by 50 kilometers. Now that leaves plenty of space for unresolved processes such as clouds. And so traditionally speaking, these are represented by deterministic parameterizations or turbulence models. But what Frederik Jansen, who is also a postdoc at CWI, did is he replaced these parameterizations by individual large eddy simulations. And so you can see some snapshots of these models here. So in that case, it's actually possible to locally resolve the clouds within a single column of the atmospheric model. But as you can imagine, these types of simulations can be quite expensive. So you can cover small spatial domains such as Holland, but if you want to do this, for instance, at the global level, that's just not going to be computationally feasible. So just to outline our approach within the VECMA project, let's say you have some multi-scale model with a large-scale solver that is coupled to a small-scale solver. Then the computational cost in general will be located at the small scales. So if you can do away with the small-scale solver and replace it with some fast approximation, a fast surrogate, then perhaps we can cover a larger spatial domain or do some uncertainty quantification. Now, in order to test this method, I don't want to use the atmospheric model I showed you because it would be too expensive. So instead I'm going to focus on a 2D ocean model. And in essence, it's just the 2D Navier-Stokes equations, but written in terms of the vorticity and the stream function, and there is an additional forcing term on the right hand side. So this is not as expensive as the atmospheric model, but it's still fairly expensive and quite complex. So I'm not going to solve these equations, instead I'm going to filter them. And so that's denoted by the bar. So the bar is a filtered quantity. But as many of you would know, if you start to filter equations like that, the nonlinear terms are not going to commute. So here J is a nonlinear advection term, and the filter J is not going to equal J of the filtered quantities. So if I want to equate that, I have to add a subgrid scale model. So this R, and you can see that R is then given by the difference of these advection terms given over here. I can plug that in the governing equations, and then I get the exact projected governing equations. But of course the problem is that this is only exact if R is given by this quantity over here, and this quantity is unclosed because this term depends upon the unfiltered omega and the unfiltered psi. So here is where you would normally add a turbulence model, but we're going to focus on making some data-driven surrogate for R. So I need to have some, let's say, some time-limited snapshot database of R, where I have snapshots of R in time. But given this condition, I can create a surrogate model that is dynamic. We're going to focus on stochastic surrogates as well, although I won't go into this much. The most important thing here is that I want to make a surrogate that extrapolates in some sense, in order to justify having to create this database in the first place. And in the case of geophysical flow problems, we're often focused on quantities of interest that are global, and by that I mean that they're spatially integrated. So you could think of the global energy, this E, so that's the spatially integrated squared velocity, or you can think about the squared vorticity, which is given by Z, so that's the entropy. And so in general I want to make a surrogate such that the statistics of these types of quantities of interest are well approximated. For instance, the PDF or the first two moments. Now, just to give you an idea of the difficulty, I made this movie here. And so on the left is the vorticity equation, so that's my large scales. On the right is my subgrid scale term, so that's the small scales. So, and I have to make a surrogate for this field over here. And just by looking at it, you can see it's quite small, fine-grained, but it's also a complex physical process. So making a full field surrogate for this is going to be quite a difficult task. We have tried this with some limited success, but today I want to focus on, let's say, a shortcut, because I can make use of the fact that my quantities of interest, for instance E and Z, they are time series. So they do not have a spatial component. And so then the idea is, if that is the case, I don't need the exact subgrid scale term, but I can replace R with a different source term that is still almost exact for my quantities of interest. And I can derive this source term based on the combination of data-driven methods and some physical insight. But the main thing is that if I do this, I'm going to obtain a very large compression in the size of my training data. And so in essence, instead of making a circuit directly for R, which is a full field dynamic quantity, I only have to train a circuit for a small number of time series. And so a circuit that is trained on these time series is what I call a reduced subgrid scale model. I start the construction of this new subgrid scale model by selecting some set of quantities of interest. In this case I have D. They're all spatially integrated, in this case over X and Y, and the integrand is some function of my primitive variables. And as I mentioned, I want this new eddy forcing, or this new subgrid scale term, I want that to be a good circuit for my quantities of interest, which means that the difference between the reference value of Q and the computed value of Q has to be small for all t during training. Now I can actually enforce that by looking at the governing equations of each Q. So I can rederive this. It will have a bunch of source terms, some dissipation, some production, and there will be one that is related to the subgrid scale term of the 2D Navier-Stokes equations. And so the effect that my subgrid scale term has on these Q is determined based upon this particular source term. So this is what I'm going to focus on. And like I said, I'm not going to use the exact subgrid scale term. I'm going to replace it with something else. And in particular, I'm going to replace it with this expansion over here. And so tau I, those are the unclosed time series. So that's the part that I actually have to learn. But pi, those are fully resolved fields. So this takes care of the spatial component. And I can derive them by assuming a basis and then computing the coefficients based on an orthogonality condition. So if you remember the governing equations I showed you in the previous slides, I can take this subgrid scale term, plug in this expansion, then I get just this expansion over here. But I don't quite like this, because now every quantity of interest will have d different subgrid scale terms. And I would like to have the situation where I can train tau I on tagging qi, and train tau I plus 1 on tagging qi plus 1, etc. And so that means that I have to choose my basis function here in such a way that all these terms will drop out except one. And so that's just an orthogonality condition. So if this is true, then this term over here will be reduced to a single source term, and so I can focus tau I on qi only. And once I've done that, the only thing that's left to do is to actually extract the value of tau I from the reference data. So again, I'm writing my ODE for Q. Again, I'm writing my goal, which is that this difference has to be small. So if I denote this difference to be delta Q, I can just equate this this source term to delta Q. And by doing so, I am imposing a linear relaxation towards the reference value. And I can extract this delta Q from the data. I'm equating that to this source term over here, which means that I can solve for tau I and find this expression. I can do that for every quantity of interest in my set, and I can plug it back into my expansion. And this is my final expression for the reduced subgrid scale term. Again, this is fully resolved. It has a spatial component. This is just a scalar, and this is a time series that I extract from the data. Now, what does this look like in practice? So consider the situation where you want to track the energy and the entropy. The reference evolution is given by the blue lines for the energy on the left and the entropy in the middle, and the red dots is the projected to the Navier-Stokes equations with my new subgrid scale term. Now you can see that it's not exactly perfect, especially for the energy. There might be some discrepancy, but again, if you, let's say you integrate this for a long enough time, you can see that the statistics of these two time series will be virtually the same. And that is despite the fact that my subgrid scale term, which is on the right here, it is very different from the exact subgrid scale term. But again, as long as it tracks these two time series, I don't really mind if it's not the same. Now, as I said, I can do this for a long amount of time. In this case, I did it for 10 years. And I can compute statistics. So this is the PDF of the energy, the PDF of the entropy. The dotted black line is the reference. And the orange line is my new reduced subgrid scale model. And you can see that the overlap is almost perfect between the PDFs. And just as a reference, I also added the PDFs of, let's say, a standard subgrid scale model. So you can see you don't need the exact subgrid scale term in order to get exact statistics, but it's important to realize that there's no surrogate yet, right? I've just did a data pre-processing step to compress the training data down to these two time series, and so that gives me a compression factor of, in this particular case, of 8,000. Now you don't have to focus on two quantities of interest, you can do a bit more as well. In this case I've added a third order moment of the vorticity, and that's given on the right here, and you can see that in this case I can get good statistics for all three. However, if I start to look at the breakdown per wave number, so the spectra, you start to see a bit of discrepancy. So the blue line is the reference, clearly, because it goes to higher wave numbers. And blue is again the standard model, and orange is my new model. And you can see that it doesn't really match the reference. So even though on average I'm going to get exactly the same statistics, it's not going to match per wave number. However, it's quite a flexible framework, and you can play around with it in different ways. For instance, here I'm adding a second subgrid scale term, or I'm adding a, let's say, a second quantity of interest. So the first one is again my global energy, and the second quantity of interest is just the energy at the cutoff scale, or close to the cutoff scale. And so I can train the model to track the overall energy. I can also simultaneously train the model to track the energy close to the cutoff. And when I do that, I get both a good global PDF, but also my spectra match quite well. And so just to conclude, if you're in a situation where your quantities of interest are somehow much smaller in size than your full domain, you might be able to apply a method like this, and then once you've done the additional steps, you only have to make a surrogate model for a quantity that is much smaller in size. And so as our next step, we're gonna focus on making stochastic surrogates, as I mentioned before. And specifically, we're going to make surrogates that are based on neural nets and that resample the reference data. And I'm just showing you an example movie of this type of surrogate. I don't have really time to go into it, but this is the output from a neural net. It's a, let's say, discrete probability density function. I can sample that randomly and get a random sample for my reference data. And so the next step is to use these types of stochastic machine learning based surrogates in the ocean model. If you're interested in these types of surrogate methods, we just put out this preprint. And if you want to know more about the stuff I talked about today, you can look at this reference over here. And with that, I'd like to thank you for your attention.
Thank you very much, Wouter, for your talk. I would like to invite everyone to ask questions in the Q&A function. Maybe in the meantime, I can ask Wouter about choice of the surrogate. You said in the future you will work with neural networks. What about Gaussian process, because it allows also to have uncertainties in the quantity you are simulating? Could you please give us some ideas about this?
Anna, I think your audio is coming in from two sources at the moment.
Yeah, I can't really tell I can't really understand the question. No.
Can you hear me now?
It's still a bit echoey, but yeah, a little bit better. Yeah.
And now? Is it better now?
Too much echo there, I think.
I'm so sorry for this. All right. So, Wouter, can you hear?
Yeah,
maybe I try to ask you a question and then you will have to chair the session later on. I'm sorry for this problem. But my question was about the choice of the surrogate. Why not try also Gaussian process?
Sorry, I really can't. Maybe just type it otherwise, and then I can see what you're talking about. If not, it's fine with me to just move on as well. Okay. Well, I have nothing against the GP. Yeah, there's a bunch of different surrogate methods out there. I kind of like the circuits we're developing now because you're resampling reference data, so you always get something that was observed at some point, and it also adds a stochastic component. Right? We like the idea of having stochastic surrogates, and I'm not sure if you're really gonna get that with the GP, are you? At least not in the same sense, I think.
Wouter, I think Anna was suggesting that you take over the chairing of this session. Would that be possible?
Yeah, that's fine.
Sorry to
let me see
spring that on you, but
yeah.
Yeah, I'm so sorry for this. Can you hear me now better?
Not.
No, we can't.
I'm so sorry. I already changed my handphone.
Better to mute yourself at this point.
No worries. I'll just introduce the third speaker from this session. So that is Xunshu Wan. And this talk is gonna be about doing, let me see. Yes, doing UQ on the molecular dynamic models. So if that speaker is set up, we can continue. Yes.
Good afternoon, everyone. The title of my talk is Verification, Validation, and Uncertainty Quantification for Molecular Dynamic Simulations. First, I want to talk about why we do molecular dynamic simulation. MD simulations have been applied in many areas. Here I will use its application in drug development as an example. Drug discovery is frequently described as searching for a needle in a haystack. We need to search from a huge number of samples of chemical compounds and hopefully find something useful. In wet lab, high-throughput screening is frequently used. Chemical compounds are synthesized and screened for their potentials. It is very expensive, labor-intensive, and time-consuming. Alternatively, virtual screening is a computer-based prediction of binding affinities for compounds to their protein targets. The virtual screening doesn't need to synthesize the compounds, and hence can be much cheaper. It can also screen a much larger chemical space. Here is our ongoing work in drug development for COVID-19. We use molecular dynamic simulations and machine learning to guide drug development. We first apply machine learning to screen a very large database containing hundreds of millions of compounds. We use docking and machine learning to find promising compounds, and then using MD simulations to further filter them, and to find leads which can be validated by assay. The process started from hundreds of millions of compounds to thousands of promising hits, and then to hundreds of leads. All studies use the most powerful supercomputers to speed up the drug development. We have had some national level coverage, including the Sun, Telegraph, and the Daily Mail. The supercomputers we have been using including Summit and Frontier at USA, and Supermark NG at Germany. Summit is #1 in the top 500 list, and Frontier and Supermark NG are also within the top 10 of the list. To make virtual screening useful, we need to make sure that the results are accurate, precise, and reproducible. That's why we need verification, validation, and uncertainty quantification. There are two sources of error in MD simulations, due to systematic and random sources. We are not talking about human mistakes here, which also occur very often. Systematic error results in an estimate of properties deviating consistently from its true value. Here are some of the reasons causing systematic errors. Imperfect design of models. Models are too simple that useful details are lost. Force field is not perfect to describe the system. Previous versions of protein force field, for example, may prefer some secondary structures over others, making the protein forming more helix or beta sheet structures than they should be. The method is not sufficient to solve the problem, or too many approximations included. The method may not properly implemented, the simulations may not correctly conducted, and the analysis may not correctly performed. All those could cause systematic errors. Random error is caused by the intrinsically chaotic nature of classic molecular dynamics. It produces random deviation from the true value. The error of a measurement are usually from both resources. Quantifying systematic errors require first bring the random compounds under control. When we perform a simulation, we will get a value which usually deviates from the true value. To make things worse, in many cases, we don't know what the true value is. We don't know how reliable the calculation is. When we perform another simulation, we get a different value. Which value should we trust? One of simulation is not reproducible and its errors are uncontrolled. That's why we need ensemble simulations. Here is a binding free energy calculation study, a peptide bound to a protein called major histocompatibility complex. We performed an ensemble simulation containing 50 independent replicas. You can see that the results from replicas differ significantly, up to 40 kcal per mole. Only combining all of the replicas together, we get a good sample of the conformations and have a reliable estimation of the binding free energies. Here is how we perform ensemble simulations. We have a series of compounds and want to know which one bind better to the target protein. For each compound, we perform an ensemble simulation and obtain averages. This leads to a more reliable results, which associate with errors. Ensemble averages put the random error in full control and make the results reproducible. There are some accelerated sampling approaches to enhance the dynamics and the convergence of simulations. Here is one of the methods, called replica exchange with solute tempering. It hits a local region and uses replica exchange to accelerate conformational sampling. Does an accelerated method still need ensemble simulations? We performed a few studies using REST2 method. We changed different settings to see how sensitive they are to the final calculations. The changes include the number of replicas in an ensemble, the length of simulations, the size of the REST2 region which is heated up, etc. I don't want to go into more details here. This study shows that the results from different replicas can vary significantly. This again shows that one-off simulations are not reproducible, and we need ensemble simulations to get converged results. Here is another study using FEP plus method from Schrödinger company. We performed ensemble simulations for a series of compounds with 30 replicas for each ensemble. In this study, we are calculating binding free energy differences between two compounds. That means we want to know which compound binds better to the protein. The absolute values for the differences, as shown in the figure on left, are smaller than 4 kcal per mole. The largest variation between two replicas for the same compound pair, however, is also 4 kcal per mole. It means the variance between two single simulations can be as large as the value we try to calculate. FEP plus method usually reports an M-bar error, which significantly underestimates the variance. We have applied ensemble approaches with different free energy protocols, including endpoint approaches and alchemical approaches. The calculated properties are relatives as well as absolute binding free energies. We have applied the ensemble-based approaches extensively to different molecular systems. Some of the simulations were performed with accelerated methods, some without. From our studies, it is clear that the one-off simulations are not producible. They all need ensemble approaches, no matter if an accelerated method is used or not. We have done extensive validation for the ensemble approaches. The studies were in collaboration with pharmaceutical companies for real drug development projects. Some of those calculations were performed blindly, meaning that we didn't know the experimental date before we completed our predictions. Those studies include different protein targets with highly diverse set of compounds. Here are the results from one of the studies. We compare the calculated results with experimental data. The figure shows the results from two different approaches, one called endpoint approach, meaning that we only need to simulate the two physical states, one for ligand bound with the protein and one for unbound ligand in solvent. Another approach is called alchemical method, which we change compounds from one to another alchemically and calculate the free energy changes during the process. From the figure, we can see that for both approaches, good correlations are obtained between the predictions and the experiments. In this talk, I discussed the VVUQ in free energy calculations. Verification in this case means we need correct method, models, and correct implementation. And the validation means we need to compare the predictions with the experiments and uncertainties, assessing the energies in the calculations. We show that the ensemble approach is required for molecular dynamics simulation, and rapid and reliable, accurate, and reproducible binding free energies can be obtained by using ensemble-based simulations. Here are the supercomputers being used for the simulations and the grounds supporting our studies. And I thank those people who collaborate with us in the studies. And finally, thank you for your attention.
All right, thank you for your talk. As always, you can ask questions in the Q&A. So in the beginning, you mentioned that you were using some machine learning method to, if I understand it well, to screen different compounds. Is that correct?
Yeah, that's correct.
So what type of method are you using there?
This is a study from our partner in America from Department of Energy. They're using docking and machine learning. Machine learning, some of the using this method to try to see which compounds are binding better, screen this database to select some promising compounds which bind to the protein.
Okay, and so that's how you test if a candidate is good, if it binds well. I'm not an expert in this at all, so.
The first step, many compounds cannot bind at all. This step just select can bind. It maybe they can bind. And this is the first step. That's why we need further steps to evaluate these binding predictions.
You can actually make the compounds you predict and then test them in real life as well.
Yeah, machine learning, we can scan a database from somewhere library, or machine learning can also generate compounds. So yeah, with these two methods can also be used.
And we've gotten one question in the Q&A. Someone asked, what is the computational cost difference between using normal MD and REST2?
REST2 using replica exchange, also hitting some region of the system. If the normal MD means we're using the same number of replicas, REST2 only slightly increase the computational cost if they have the same number of replicas.
Wouter, Jan has asked a question in the chat.
Okay, I didn't see that one.
Okay, yeah, I saw that.
Perhaps I can ask it personally. Okay, so I wonder, was this number of simulations in the ensemble influence the results?
If we have enough number of simulations, the result already converged. Increase this number will not change it a lot, but at least if you're only using 1 or 2 simulations, the influence you will see it can change quite big.
So what is the average number you are using in this case?
Can you repeat this question?
What is the number of simulations you are using in the ensemble?
We're using endpoint approach. We usually using 25 replicas. We're also using all-chemical method, which is more expensive. So that's why it's also more accurate than the endpoint problem, endpoint approach. That's why in the all-chemical method, we're using less number of replicas. We're usually using 5 instead of 25.
Okay, thank you.
Okay, thank you. I suppose we can move on to the next talk now. And that is Arunsalam Rahanutan. Sorry if I mispronounced it. It's from the Central State University. And he's going to be talking about Markov chain Monte Carlo methods for subsurface fluid flow.
Hi everyone. I am going to present Markov chain Monte Carlo methods for fluid flow forecasting in the subsurface. I am Arunsalam Raghunandan from Department of Mathematics and Computer Science at Central State University, which is located in Wilberforce, Ohio, USA. This is a joint work with Al-Sadiq Ali, Abdullah Al-Mamoun, and Philipp Pereira at University of Texas at Dallas. Let's talk about the motivation for our research. In subsurface characterization, we want to know what lies in an underground volume. We need subsurface characterization to make decisions regarding economic, environmental, or health and safety concerns. In oil recovery, we often want to forecast the output of oil production. In the case of an environmental contamination, we want to know the dynamics of contaminant concentration in groundwater. The prediction of movement of CO2 plumes in the underground is essential to maintain a geological sequestration site. A reliable characterization of a subsurface is one of the most challenging tasks. The challenges arise in several aspects. Nonlinear system of partial differential equations describe the movement of fluid in a porous medium. The partial differential equations are hyperbolic dominated, and we solve the problem on a large computational domain. We consider uncertainties in subsurface parameters, and in a Bayesian framework, we quantify the uncertainties using very limited data. Here is a simplified description of the problem. We consider a two-dimensional computational domain of an aquifer. An accidental contamination spill occurs at a spill site, and our goal is to characterize the subsurface using partial fractional flow data at the monitoring wells. For that, we consider a multi-MCMC approach in the Bayesian framework. Since we consider several shorter MCMC chains, we need to analyze the convergence of those chains. Available data comes in the form of fractional flow curve. Fractional flow curve is given by the function f. The function f gives the fraction of water in the contaminated fluid at any given time. Initially, there's no trace of contamination at the monitoring wells. However, as the time progresses, we can observe the traces of contamination at the monitoring wells. Now let's talk about how we can compute the fractional flow data by using a single phase flow model. By combining the Darcy law and the conservation of mass, we can write a set of equations that describes the movement of fluid in the porous media. B stands for Darcy velocity and P denotes the pressure. The permeability field depends not only on the spatial location but also on the random variable. Sources and sinks are modeled through appropriate boundary conditions. If we consider first two equations, we have an elliptic problem, and the last equation is hyperbolic. Here we have a set of multiphysics multiscale coupled partial differential equations. We consider an operator splitting technique to decouple the elliptic and hyperbolic problems. To solve the hyperbolic problem, we use an explicit high-resolution, locally conservative central scheme. A mixed finite element approach on graphics processing units is considered to solve the elliptic problem. Now, let's talk about subsurface characterization. If you know the permeability distribution, then we can use the numerical simulator to produce the simulated fractional flow data at the monitoring wells. However, in our problem, we know fractional flow data at the monitoring wells, and we want to characterize the permeability field. Here we have an inverse problem. Now let's talk about how we can use a Bayesian framework to attack this inverse problem. The Bayes theorem states that posterior is proportional to the product of a likelihood function and prior. We assume the likelihood function takes an exponential form, where f sub psi stands for the simulated fractional flow data at the monitoring wells. In order to get the simulated fractional flow data, we need to solve the system of multiphysics multiscale partial differential equations several times. Many samples yield the same or similar fractional flow curve data. Therefore, this is an ill-posed inverse problem. We need to specify the prior distribution, and let's talk about the prior distribution in the next slide. Let's consider a Gaussian field, which is characterized by the covariance function. In our study, we consider an exponential function for the covariance. L sub I stands for the correlation length in the direction I, and sigma sub I stands for the strength of heterogeneity. We said the permeability is equal to exponent of the Gaussian field. Now, if we consider a computational domain of several thousand elements, then we need to populate each element by a random permeability value. In this case, we have a huge parameter space. We need to reduce the dimension of the parameter space. For that, we consider Harhonen-Levy expansion. The KL expansion relies on decomposing the Gaussian field using basis functions satisfying the following eigenvalue problem. By solving the problem numerically, we can find a infinite series representation for the Gaussian field. Now, if we consider dominating eigenvalues, then we can have a truncated series. Thus, we can achieve the desired parameter space reduction. This figure shows the KL expansion for a given set of correlation lengths and strength of heterogeneity. The eigenvalues decay very fast, and it is enough to consider first 20 eigenvalues to capture the general trend of the KL expansion. Now let's talk about the Markov chain Monte Carlo methods in detail. We want to sample from the posterior distribution. For that, we construct a Markov chain such that the posterior is the equilibrium distribution of the chain. This approach is inherently a serial process with low acceptance rates. There are several proposed alternatives. One of them is two-stage MCMC. In the two-stage MCMC, we introduce a coarse-scale filter to increase the computational efficiency and the acceptance rate. One could parallelize a single MCMC chain by prefetching technique. Another straightforward approach is to use several shorter MCMC chains. In this talk, we consider several shorter MCMC chains for two MCMC methods. The first one is a two-stage MCMC. The second one is a differential evolution adaptive metropolis MCMC, which is an extension of a differential evolution MCMC. This slide outlines the algorithm for the two-stage MCMC method. Given covariance function R, we generate the KL expansion. For the proposal selection, we consider a random walk sample. By using a set of theta values, we generate the permeability distribution on the fine scale. To compute the upscale permeability on the coarse scale, we consider an upscaling technique. Once we have the upscale permeability on the coarse scale, we solve the forward problem to get the simulated response at monitoring wells. By using the simulated response, we calculate the acceptance probability. If the proposal passes the coarse scale level, then we go to the fine scale. Again, we repeat the simulation on the fine scale. We compute the acceptance probability. Based on the acceptance probability, we decide if we want to keep the proposal as a candidate for the underlying field. In the dream MCMC method, we use a sophisticated approach for the proposal selection. The proposal has an inbuilt mechanism to adapt the scale and orientation of the proposal distribution during the evolution of the posterior distribution. For the convergence analysis, we consider potential scale reduction factor and its multivariate extension. The PSRF takes into account only a subset of parameters, whereas the MPSRF incorporates the convergence information of all the parameters and their interactions. To calculate those parameters, we consider posterior variance covariance matrix, within covariance matrix, and between chain covariance matrix. By using those matrices, we calculate the potential scalar reduction factor and its multivariate extension. When the chains converge, the MPSRF will get closer to 1. Now let's talk about the simulation study. We assume that the aquifer is saturated by groundwater without any contamination. A contamination enters the spill well at a rate of 1 pore volume at every 5 years. We run MCMC simulations to characterize the permeability field. On the top left corner, we have the reference permeability field, and other 3 figures show the contaminant concentration profile at different times. Here we have the PSRF and MPSRF curves, and we can see the dream converges much faster than the 2-stage MCMC. However, both methods need more iterations to reach a complete convergence. Now, if you look at the fractional flow data, they look very similar for both methods. However, when we look at the variance plots, we can see there are significant differences in both MCMC methods. Let me present the concluding remarks. Using a GPU-based single-phase flow simulator, we have compared 2 frequently used MCMC methods. We have confirmed that the dream converges much faster than the 2-stage MCMC. The ensembles of accepted fractional flow curves share essentially the same average behavior. However, significant differences have been observed in the time-dependent variance curves as well as in the posterior distributions. As a future work, we intend to combine both methods in a 2-stage version of Dream MCMC for porous media flow problems to achieve good convergence while reducing the computational cost. Thank you.
Thank you for the nice talk. There's no questions as of yet, but I was wondering, so this 2-stage method you were talking about, is it similar to one of these multi-level methods that we heard about? Where you have different, because you make use of different resolutions somehow, right?
Hi, everyone. In the 2-stage MCMC method, we use a coarse scale filtering to filter out the proposal. that will be rejected at the fine scale simulation. So we can say the idea is very similar to multi-level methods that have been discussed before.
Okay. And there at the end you showed some variance plot. I didn't quite get them. So it's the variance of the posterior versus time, or?
So we just look at the variance plots at the different times to see the comparison for both methods. We particularly looked at some interesting times, such as breakthrough times.
Yes. And so as of now, there's no way of telling which one is better, or?
Our studies suggest that the DREAM performs better than the two-stage MCMC method. It performs very well as far as the convergence is concerned. And however, both methods require more simulations to reach a reasonable convergence so that we can use the accepted sample for a reliable prediction.
I see. And what I always wonder when you do Bayesian inference is if you calibrate for one particular case and you use, let's say, the same model but with slightly different boundary conditions from some other small change, you think you can reuse your calibrated results in a, let's say, extrapolation?
Yes. The Bayesian framework is a general framework, and it can be applied to more problems. And I think in literature, we could see the application of Bayesian framework for different kind of applications. But we mostly studied the Bayesian framework in the context of porous media applications.
Okay, but I was talking about, let's say you still have porous media application, but you just change the boundary conditions slightly, or you have.
Yes, I think we have to make very minimal. In some cases, it can be no modification, the Bayesian framework to use the methodology that we described in this talk.
Okay, thank you very much. If there are no other questions, I think we can go to the next speaker, which, if I'm not mistaken, is Laura Lyman from Stanford University. And she's going to talk about ways to, I think, to reuse old samples from polynomial chaos methods.
This talk is a prelude to a submitted paper written by Professor Gianluca Icarino and myself, Laura Lyman, whose details are here. Please enjoy. A subset of uncertainty quantification addresses the following types of problems. Suppose we are using a deterministic differential equation to model some phenomenon of interest, and this is an equation or system of equations that we cannot solve analytically. That is, there is no obvious closed-form solution, so we are dependent on computational techniques. Say I wish to express some source of uncertainty in the model by introducing a random variable, for instance, in the initial condition. In this context, the solution to the differential equation is now random. A polynomial chaos expansion, which I will sometimes abbreviate as a PCE, represents the random variable as a series of countably many Hermite polynomials of independent Gaussian random variables, and a truncation of such an expansion is used as an approximation. What is incredible about the PCE is that it helps facilitate the transformation from a problem with randomness to one that amounts to solving a deterministic set of PDEs, and the size of this set is determined precisely by the number of terms in the truncation. The research presented here considers the following. Given a solution UM0 to a PDE system of size M0 arising from this PCE setup, can we use it to produce the solution UM to a system of size M greater than M0? That is, can we reuse already obtained information? If so, how does the computational cost compare to using standard numerical techniques? To address these questions, we consider the following problem. Let script D be the Cartesian product of two intervals in the spatial and time domains, and let C be a standard normal, one-dimensional random variable. Here, psi sub I denotes the ith probabilist's Hermite polynomial. The PDE considered is Inviscid-Burger's equation, since it showcases nonlinearity in a straightforward manner. Only now, the initial condition incorporates the random variable Xi to express our uncertainty about the solution U's initial amplitude. Substituting the truncated PCE into Burger's equation, multiplying through by a fixed but arbitrary Hermite polynomial, and integrating with respect to the measure induced by Xi yields the following expression. This is a deterministic system of M+1 nonlinear and coupled PDEs. We will refer to it as an M system. These double and triple products denote the expectation of those polynomial products with respect to Xi. One can start noticing similarities between systems with consecutive M values. We would like an algorithm that uses these similarities to our advantage. In the paper itself, I demonstrate that a certain matrix, denoted here by L sub M, helps characterize these similarities. It plays an important role in understanding the difference between M-1 and M systems. And for Hermite polynomials, it is easy to show that L sub M has this particular structure. In fact, the matrix is actually sparse. There are several bands of 0 entries. However, for different types of orthogonal polynomials, which would emerge necessarily from choosing a random variable Xi with a different distribution, the structure of this matrix will change, though we believe sparsity will be preserved. We proceed to the details. Let the vector UM be the solution to the M system, so note that it has M+1 component functions. Let UM-1 similarly be the solution to the M-1 system. Let me emphasize, these solutions are different. Even ignoring the size differences between these vectors of functions, their corresponding component solutions, U sub k, do not match. That being said, these corresponding components can be used for approximations. From here, we explain a draft of the algorithm. Let U hat M be our approximation of UM. Bluff, by collectively setting our approximations of the component functions, the U hat M sub k's, over these k values, equal to UM-1. In other words, we know the solution to the smaller system does not work in the larger system, but we're going to use it anyway as an approximation, for now. But remember those size differences between the solution vectors? We still need to solve for the final component, U hat M sub M. That is, we have the additional equation in 2, which is simplified further in 3. So plug in our approximations U hat M sub k's into the right-hand side of equation 3, and solve for U hat M sub M using standard numerical techniques. This is not a huge deal since it is solving a single PDE rather than a system of them. Note that the L sub M matrix mentioned previously appears in equation 3 as well. At this point, we have an approximation to the M system solution. We could stop here, but unfortunately, this approximation is rather poor. To reiterate this draft of an algorithm, say we know U1 and would like to use it to solve for a U hat 2, an approximation to the solution of the m equals 2 system. We set the approximation to the m equals 2 system equal to the solution of the m equals 1 system. Then we plug in all of these approximations into the right-hand side of the blue equation, and we solve for the last component function numerically. We can then use this newly found U hat m to resolve for some of the U sub I approximations via their corresponding equations in the M system. This is the fix phase. So continuing with our example, we substitute U hat 2 into the right-hand side of the purple equation to resolve for the U naught approximation, or we similarly can substitute into the right-hand side of the red equation to obtain an improved approximation of the U sub 1 component. The fix phase improves the approximation because before the fix, U hat sub 0, for instance, was determined from its m equals 1 system equation, rather than from the correct equation appearing here in purple. We could resolve for all of the U hat sub I, that is, we could fix all of the component functions, except this is as expensive and essentially equivalent to, in a convoluted manner, to just solving the full M system directly in the first place. So instead, we resolve for the worst approximation. By that, I mean the U sub I such that its corresponding solution in the smaller system is a very poor approximation of it. In general, we can extend this logic to fixing the C worst approximations, where C is a fixed correction size parameter that can be tuned to our liking. And these C worst approximations are guessed by examining the absolute row sums of a certain matrix, which I denoted L sub m before. And our paper demonstrates how these guesses, in this numeric example, are actually spot on. This whole aforementioned process will be referred to as one-step bluff-and-fix, or one-step BNF, to distinguish it from its iterative version. Now, let's look at the results. Recall that we are solving one-dimensional Inviscid-Burgers equation with a random initial condition. The solid lines depict the true solution component, U5, for m equals 5 at various time points. These time points are demarcated by the lovely colors. By true solution, I mean the solution obtained by solving the entire coupled system of PDEs using a standard, what we call monolithic method, in this case, a Runge-Kutta stepping scheme. The dashed lines show the solution produced by our algorithm. The left-hand side figure demonstrates a correction size C of 1, and the right-hand side has a correction size C of 2. So we can observe that by correcting or fixing only the solutions of 2 PDE, which involves solving less than half the total PDEs we would solve otherwise, we can produce a solution consistent with the monolithic method, solving the whole M system directly. This is very exciting. Now for brevity, only 2 figures are shown, but in our paper, we demonstrate that a correction size of only 2 for M values ranging from 3 to 8 is sufficient for having average absolute error under 6% and average relative error under 3% for every single solution in question. In that document, you can see precisely how those error metrics are defined. This table shows the computational cost of one-step bluff-and-fix for correction sizes 2 and 3. Each measurement was averaged over 100 loops to provide a confidence interval. And we can see consistently that bluff-and-fix requires less computation time than a monolithic numeric method, again, whose placeholder in this case is Runge-Kutta 4-step. That being said, recall that bluff-and-fix assumes that the solution to the smaller system is readily available, and any additional time that was needed to obtain this black box smaller solution is not accounted for in these runtime measurements. However, these concerns around timing in a more all-encompassing and inclusive manner are addressed when we time the iterative version of this algorithm, which only assumes that we know the solution to an M0 system for some small baseline M0 value. And the time used to retrieve the solution to a system that small, say for M0 equals 2, can likely be considered negligible. In this context, it was on the order of milliseconds. As you can imagine, for the iterative version, we are continuously inputting a system's approximate solution into one-step bluff-and-fix for finding the approximate solution to the system created with one additional PDE. We then continue in that manner. Now we found that using a monolithic method to solve only an m=8 system is faster than using iterative bluff-and-fix from a baseline m0 = 2 solution. While iterative bluff-and-fix is less efficient in that sense, it does have the advantage of producing approximations to all of the m systems along the way, and does so far faster than a monolithic method solves all of the m systems, one by one. In general, it could be beneficial to know the solution to an m system for a consecutive range of m values, because then one could observe when the difference between consecutive system solutions is small, which provides a rough sense of the m value sufficient for solution convergence. To recap, we have presented a promising algorithm for utilizing the solution to a polynomial chaos m-1 system arising from Invicid-Burger's equation to approximate the solution to the corresponding m system. The algorithm was expanded to an iterative version, which utilizes the solution to some baseline m0 system to approximate the solution to a general m system for any m greater than m0. Bluff-and-fix is shown to be effective in producing accurate solutions even when the correction size parameter c is small, for both its one-step and iterative versions. And while iterative bluff-and-fix initiated at some baseline m0 can be less efficient than solving the whole m system directly, it has the advantage of producing approximations to all of the m system solutions along the way. It does so faster than the monolithic method solves all of those full m systems, one by one. For future work, one immediate extension is to apply this algorithm in settings outside of Invicid-Burger's equation. In principle, there should be no issues, though the way in which the algorithm will change is in how it selects which use-by are prioritized for being corrected, because that ordering is dependent on the row indices for which a certain matrix L sub m has its largest absolute row sums, which follow a simple pattern in the case of Hermite polynomials. Namely, the row sums are non-decreasing as you move down the matrix. However, that ordering is entirely dependent on the orthogonal polynomials being Hermite, and accordingly will change if the random variable c in the initial condition has a different distribution. That being said, flexibility for such differences in this L sub m matrix is built into the algorithm in the paper in further detail. Further, we believe that the L sub m matrix will continue to exhibit sparsity, making future trials equally efficient. On that note, another area is examining different distributions for the random variable and try, say, using a generalized polynomial chaos expansion. However, in that case, we have to be careful, because the PCE convergence is dependent on this fundamental result from Cameron and Martin, which implies that a countable sequence of polynomials in independent standard Gaussian random variables is dense in the set of random variables with finite variance that are measurable with respect to these Gaussian random variables. So, for a generalized polynomial chaos expansion, we have to pay attention to the convergence of the second-order stochastic process in question. Thank you so much for the opportunity to share, and I hope you enjoyed this talk. Please feel free to contact me with questions, and I look forward to our future discussions. Thank you.
Thank you, Laura. A very nice talk. We have a question in the Q&A. Someone asks how we can use this approach for a steady state problem.
Oh, hi. Thank you. Can you hear me?
Yeah, I can hear you.
Great. Yeah, that's a great question. So for a steady state problem, I imagine what you would do is, as long as you have a similar PC or a similar PDE setup, it would be okay. But in terms of the details, I would have to think about that a bit more. So again, that's a good question. And if you reach out to me over email, I can probably give you a more precise answer.
Thank you. And so you kind of mentioned this in the end that you're testing this on arbiters. One other question, I'll give that preference. So Philipp Pereira asked what would be the expected gain for multidimensional problems.
Yes, that's a great question. So for multidimensional problems, you'll see that the size of M is going to increase in a huge manner, even just going to two-dimensional Gaussian random variables by having a truncation size on these multi-indices of, say, 4 or 5. Even then, you're dealing with so many coupled polynomials. So that's the expected advantage, that this will be useful for when you have very, very large systems of PDEs in higher dimensions. That being said, you are still restricted in the sense of having your random variable be Gaussian, 2-dimensional or 3-dimensional Gaussian. And there's also a lot of interesting work about how to handle the case of when those 2 or 3-dimensional Gaussian random variables have some correlation. So that was sort of a tangent, but the expected gain is that this will be much more efficient when you have a very, very large system of PDEs, which would arise from this multidimensionality. Hopefully that answered it.
Thank you. You kind of mentioned this in the end, you're testing this on different problems. So how would the method change? You'd have to derive a different M systems, I would suppose, right?
Yes, that is correct. However, any simple nonlinear terms, such as like a U multiplied by different spatial or time derivatives, those would have the same structure. Okay. So this is more of a prototype, but otherwise you derive a different M system, you might get a different matrix, or say a sum of matrices, but I believe everything should still go through. That being said, we're still working on having a broader array of numerical case studies to back that up.
Thank you. And I was also wondering, so you're reusing, let's say, computer results from previous iterations. So how does your method compare to, let's say, a standard hierarchical sparse grid method for stochastic allocation in computational efficiency or something?
In terms of that, that's actually a great question, and I'm not sure because I haven't looked too much at what was it you said, high dimensional sparse.
Yeah, hierarchical sparse grids, you can add samples as well to an existing sampling plan, let's say.
Okay, gotcha. So one way that this also differs from classical sampling problems is that we're assuming that this PDE involves a function that's very expensive to evaluate also. So we're going to try to avoid sampling if possible. But that's also an interesting question, and I don't know too much about that subject. So maybe I'll ask you after this.
Well, thanks again for the nice talk. And yeah, I guess it is time to go to the last speaker, if I remember well. Yeah, and so the last speaker of the day is Mikhail Gasanov, and he's going to be talking about doing sensitivity analysis for soil parameters.
Good afternoon, dear colleagues. My name is Mikhail Gasanov, and I represent the Skolkovo Institute of Science and Technology. Today I want to present our research, sensitivity analysis of soil parameters in a crop model supported with high-throughput computing. Plant growth and development models are important for both scientific study and farmers, as the use of decision-making systems based on crop models allows farmers to reduce fertilizer consumption and improve crop rotation planning. We suggest that using sensitivity analysis can help farmers better understand what factors affect crop yields. The main factors that affect crop yields are weather, soil conditions, landscape, and fertilizers. We have analyzed the performance of Monica model. This is an agro-system model consisting of submodels such as plant growth model, nitrogen cycle model, crop rotation model, and soil physics model. significant number of parameters and complexity of the model make it possible to perform sensitivity analysis to select the most important ones. In Monica model, there are more than 200 parameters. One of the main parts of a model, the soil model. In the model, the soil block is defined as a setup of layers with different thicknesses. The total depth is 2 meters. A user can set up the depth of the layer and its main parameters. We rated the sensitivity of the model to changes in soil indicator in different layers. We are interested in first, which layer is most important for plants, and second, which soil parameters are most affect the yield of these crops. And main goal is sensitivity analysis of Monica model supported with high-throughput computing, and some objectives: estimate optimal number of samples for sensitivity analysis, determine which soil layer plays the most important role in the yield production, define which soil parameter is the most important in topsoil layer, and speed up the model simulations with high-throughput computing. From various approaches for sensitivity analysis, we choose the Sobel approach since it allows us to evaluate the combined effect of parameters on model result. And to perform sensitivity analysis, we use the Celib library for Python. And Sobel sensitivity analysis provides some pluses. It's global sensitivity, but there are minuses. It's computationally cost. We can consider the result of model as the sum of influence of parameters and the sum of interactions of these parameters with each other. Each variable contributes to the overall variance. We can take into account the contribution of each of the variance causes the change in each of the parameters to the overall variance. Sensitivity indices are defined as the variety of the partial variance and the total variance. Analysis of sensitivity indices provides sufficient information about the structure of corresponding function. For functions of an additive structure, only the low-order sensitivity indices are important. In extreme case in which there is no interactions among the input variables, all higher-order sensitivity indices are equal to 0. In the general case, all global sensitivity indices can be important. However, for 5-dimensional problems, calculating all of them are impractical. For this reason, Sobel introduced sensitivity indices for subsets of variables and the total sensitivity index. The important indices in practice are first total index and total sensitivity index. Their knowledge in most cases provides sufficient information to determine the sensitivity of the analyzed function to individual parameters. Some extreme cases. In case where our first sensitivity index is equal to 0, it means that its parameter doesn't affect output of our model at all. In case where our sensitivity index is equal to 1, it means that result of our model, output of our model, depends only on this parameter. For the experiment, we chose a real field in the Russian region where farmers cultivate crops such as sugar beet, barley, soybean. We measured various agrochemical indicators and parameters, analyzed limits of these parameters for this soil type, its chernozem. For each of the parameters, we looked at how its changes in each soil layer affect crop yields. For example, we see that changes in organic matter content in all layers affect crop yields. For example, changes in the sand content affect only the top layer. A significant number of simulations are required to obtain acceptable confidence intervals. Conducting this number of simulations takes a long of time. For example, running 2 million simulations on a single core took about 1 month. We tried to speed up this process. To do this, we generated samples for the model using Sobel quasi-sequence. For example, for 9 parameters and sample size 100,000, we got a matrix size of 2 millions by 9. Then we divided this matrix into parts. The number of parts depends on the number of cores in the cluster. For example, we used 100 cores. we got the size of batch equal to 20,000. Then on single core, we run parallel models with different input parameters. We joined the obtained results in a single vector and performed sensitivity analysis. Since the parameters in the top layer are most important for crops, we continued research only with this layer. We evaluated changes in 6 different parameters for crop yield. The graph shows the sensitivity indices and their confidence intervals for different sample size for sugar beet. As you can see on the graph, to get reliable values, the sample size must be at least 1000. Only 2 of 6 main parameters affected yield variability: clay content and bulk soil density. The yield of barley was affected by changes in the organic matter content and soil density. Reliable results were obtained only as the sample size of 5000. The graph shows results for the entire crop rotation. Here we can see year and type of crops: sugar beet, barley, soybean. Gray circles indicated the indices of the first order. The gray lines on the graph shows a second order sensitivity index, which explains the combined effect of 2 parameters on yield. White circles indicate the total index. We can note for soybean the presence of interaction parameters between each other. We see the presence of total index for organic matter in soybean. This indicates a complex joint effect of this parameter and other parameters. For barley, we can identify a significant interaction between organic matter and soil density. We can also observe changes in importance of parameters for same culture. We see that the importance of organic matter in crop rotation changes for sugar beet over 6 years. Here and here we can see different values for first sensitivity index. It means that with time there are changes in soil which leads to different effect to yield. Our result indicates that for each studied crop, a different set of soil parameters affects the yield. The transformation of organic matter in the soil during crop rotation modifies the importance of these parameters for sugar beet productivity. The result shows the presence of collective influence of model input parameters on crop productivity. And thank you for your attention. Yeah, and good luck. Stay healthy.
So thank you for a nice talk. I think thus far there are no questions. There was one from the previous talk. So I liked your plots that you showed the let's say the higher order interactions of the soil indices. And I was wondering if you know of a way to plot, let's say, even higher order interaction between 2 variables. It's maybe a weird question, but it's something I happen to be thinking of at this time.
Yeah, thanks for your attention. Yeah, we plot total index, but yeah, for second interaction we used just gray lines in last plot. Yeah, yeah, it was such approach.
Yeah. Yeah. And is there any way for you to validate your method? So if you can actually go and find some data to see if these parameters really are most important?
Yeah, these parameters are important from the point of view from soil sides, from soil view of some approaches, really important parameters, and we try to estimate in real fields. Yeah, and next step we want to compare from other experimental fields in real places in Russia or some other places. Yeah, we try to compare with real nature effects.
Okay, thank you. Oh wait, my daughter is coming home at this moment, so it might become a bit noisy.
Thank you.
If there are any other questions
in the chat.
Can I ask a question?
Chat, okay.
Because I haven't got quite, I'm not sure whether I got it, okay? What parametric model do you use to model the dependence between the predictors and the target?
Input parameters were some soil parameters like organic matter, clay, sand, etc., pH, and output parameter was crop yield. It's amount of, for example, sugar beet, soybean.
Yeah, this I got, but what was the parametric dependence between those things?
Yeah, we have not discovered, we haven't used entire parameter inside model, such as some parameters for processes. We used only input parameters of conditions of something like weather conditions, etc.
Okay, because it seems to me that the problem we are dealing with is standard selection of variables problem. So have you tried, for example, selection of predictors in this case by some standard methods?
Oh, no, we have not tried to do. Yeah, I will write and think about it. Thank you for this.
Okay, thanks.
Yeah, thanks.
So I'm guessing that concludes the session for today.
I think is there a question from Anna in the chat, or was that asked already?
Yeah, yes, there's another question. Anna asks if you have measured the uncertainty in the model.
Okay, should I answer? Oh, I can answer here, yeah, or in chat. No, we did not this due to the previous publications from guys who developed this model. They described this model uncertainty in their work, and we cited this and discussed it in paper.
So I guess we're done for today now. You want to say something here about tomorrow, about when it starts?
So I've got the I've got the agenda for day 2 up now, and as you can see here, it starts at 11:25 Central European time, or 10:25 in the UK. So we're looking forward to seeing you all then. Thanks everyone indeed for tuning in today. We had really great attendance, both here and on the YouTube page. So yeah, thanks especially to all the speakers and the chairs as well. Thank you to everyone.
Thank you.
All right, I guess we'll close the meeting.
Thank you. See you tomorrow.
See you tomorrow.